Hello, hello. Yeah, hello and welcome to AltLayer's RaaS Day, short for Rollups-as-a-Service Day. RaaS is a virtual event with the goal to bring together experts in the rollup and modular space and to talk about the present and future of rollups, but from a rollups-as-a-service perspective. That is a world where we have many application-tailored rollups. We have an exciting lineup of talks, but let me kickstart this event by giving a talk on why build Rollups-as-a-Service platform in the first place and how AltLayers is contributing to the space in general. So why build rollups? In particular, why build rollups-as-a-service solutions, such as AltLayer? Now, if you look at the space today, right, it's quite well established by now that modular design philosophy is the only one that can come and scale applications. So that's capable to provide applications the right kind of DA bandwidth, the right kind of block space bandwidth. And so chains that are monolithic in nature, in particular, for example, Ethereum, they have started to adopt this modular stack and basically focus on settlement and DA needs for applications. While the main component, which is the settlement layer, one of the components, which is the settlement layer of the modular stack, has started to move out of Ethereum, right? And we have started to see all sorts of execution layers, also known as rollups these days, to pop up. And in fact, if you look around, you could see in the space today different types of rollups depending on that have different features. For example, you could have rollups that are based on ZK based, so for example, validity proof based rollups, or you could have, for example, optimistic execution model based rollups. You could have these rollups that run different runtimes. For example, you could have EVM based rollups or WASM based rollups, Solana EVM based rollups, and so on. And some of these rollups have different purposes as well. So you could have a general purpose rollup, for example, Arbitrum, Optimism, ZK Sync, and others. You could have application-specific rollups that you could build using, let's say, OP Stack or Arbitrum Orbit, and so on. And they could be deployed in different contexts. For example, it could be a layer 2. For example, you could attach them to base chain, for example, Ethereum for DA needs, or it could be implemented as a layer 3 on top of an existing layer 2. But basically, the idea is that because execution has moved out of the base chain, now people have all sorts of flexibility because they are no longer limited by the constraints that a base chain provides or restricts you. And so people are building different types of execution layers that have different characteristics. So you can mix and match different features of your execution layer that best suits your application business needs. And so this is not surprising that when you look at the space today, you have all sorts of execution layers or rollups out there in the market today, ranging from persistent application, general purpose rollups like ZK Sync, Arbitrum, Optimism, but also very specific application-specific rollups like OP Stack-based rollups and so on. And so what has happened is because of the different execution environments or the different execution needs or different execution characteristics that have come up, we are seeing a fragmentation of the entire execution space today. And as a result, if you are a new application developer and want to build your own application specific infrastructure, so your own application specific execution layer, you'll have a hard time in some way because you have to deal with all the heterogeneity that comes from this fragmented execution space. There's a lack of, for example, a single development framework that you could use to build your own application dedicated infrastructure. And even though there are some SDKs that are offered, sometimes they are very low level. So it requires still quite a bit of understanding of how rollups work, which might not be the expertise of some of the application builders out there. And so the goal was to kind of build something that could unify the entire space in some way, right? When we started, we were thinking about, okay, how could we build a universal execution framework for all Web3 execution needs? And so it's a question that we kind of know the answer to, right? Because if you look at the space in the Web2 world, you have this giant Amazon Web Services. And so if you're a developer and you're building anything, right, from a startup to even a medium or big, large scale venture, you outsource your compute or storage capacity to Amazon Web Services because it's much more convenient, it's cost efficient, and also it kind of takes away all the hassle of maintaining that infrastructure yourself. And so the idea was to kind of learn from what AWS has done for the Web2 space and kind of take it a little bit forward and move it to the Web3 space. So can we do this? And the answer is yes, we can do it. Let's assume that you were able to build an AWS for Web3 of some sort, right? Then what would happen, right? So one thing is it could reduce cost for all developers. So right now, if you're going to build an application dedicated infrastructure today, it will take you millions of dollars to go and build it. If you're not using something like, let's say, an SDK that is very tailored to application specific infrastructure. It requires a lot of dev resources, right? And this is a good example of this is, for example, DYDX, right? DYDX was decided to build an application dedicated infrastructure. They announced it sometime mid last year. And it's almost about a year now, and it's still not out there yet, right? Because it takes time to go and build application specific or application tailored infrastructure in the blockchain in the blockchain world. And so if you had something like AWS, then you could rapidly innovate. So you could very easily go and deploy a fully customized infrastructure, and you could host your application on that infrastructure. And when you feel like this is something that you really need, you can customize in all sorts of ways. The second thing is you can scale. So these infrastructure can scale depending on based on application that you have. And so this leads to And so the goal was to kind of build something like AWS, but in the Web3 space. And so the idea was to kind of build something what we call today as Rollup-as-a-Service solution. So Rollup-as-a-Service didn't exist a couple of months, when we started back in 2021. But now it has become quite a popular theme outs, and a lot of interesting projects are building in the space around Rollup-as-a-Service solutions. So what does it offer you? So a Rollup-as-a-Service platform such as AltLayer allows anyone to go and deploy a fully customized application dedicated rollup within minutes. And it should be doable by any non-technical team member. So imagine, for example, you're a business person or a marketing person in a team, and you would like to have, or at least experience, or even deploy or innovate using an application dedicated infrastructure. You should be able to do that, and it shouldn't take you months or years to be able to deploy that. So the goal was to make it as easy as possible for anyone to go and deploy these application tailored rollups. And so that's what the goal of, sorry, my slides are jumping. So the goal was so if you had something like AltLayer's Rollup-as-a-Service, what could you get from this? So one is, because as I said, it's designed as a no-code framework. So anyone with zero coding experience should be able to go and launch an application dedicated infrastructure by themselves. And so it makes it much easier for anyone, really. And so the second thing is, once you have it, when it becomes easier, it also means that it becomes low cost. And it's also fast to deploy, right? And what's really interesting, and I think it's one of the core component, is that when you have infrastructure like this to deploy a rollup for yourself, then if you are an application builder, then you can go and focus on your core expertise. So imagine, for example, you're a game developer, then you can go and focus on game development rather than worrying about, how do I go and manage my infrastructure, and how do I go about maintaining nodes that I have been running for my rollup here. And so all of that goes away because you're basically outsourcing all of that component to a Rollup-as-a-Service provider, which basically gives you a managed service of that kind. And so where do we stand in terms of Rollup-as-a-Service providers? So we are the only ones. AltLayer is the only one that offers a unique kind of rollup that we call ephemeral rollups, and I'll tell you a little bit more about it in a minute. And so it's a rollup that is basically disposable in nature. And so you can spin up this rollup, you can use it for as long as you want, and when you feel like you're done with it, you can take it down. It's one of the only RaaS providers today that runs with decentralized sequencing. So this is something that has been a point of debate in the last couple of weeks or even months, where you want to make sure that you don't run with a single sequencer, because it can create liveness issues, can create issues where if your sequencer goes down, you will have to find ways to get your transactions processed. The second and third thing is we are the only ones that have working fraud proofs on the testnet at the moment, and we hopefully will go in the mainnet very soon. So our dashboard, which allows people to go and deploy these rollups, already live. So you want to play around with it, go to dashboard.all.technology. There are several, I would say, tiers depending on, these are pricing tiers, but there's a free version that you can go and try. This allows you to deploy a rollup that will last for about 2 hours. When you feel like you're done with it, you can take it down. There are two kinds of rollups that we offer at the moment. One that we call ephemeral rollups or flash layers. So as I mentioned, these are rollups that are disposable in nature. The second one is what we call persistent rollups. So these are rollups that are basically something like Arbitrum optimism, but for dedicated applications. So it doesn't go down for immediately; it stays there forever. And the last part is rollups that. So by the way, these two rollups, the flash layers and the persistent multi-chain rollups, these are both built using our own tech stack. But we're also in the process of integrating external SDKs. So for example, Arbitrum Orbit, which allows people to go and deploy Arbitrum-based L3s. And the idea is to kind of offer people a framework, a dashboard from where they can go and deploy Arbitrum Orbit-based L3s. So we are adding support for third-party rollup SDKs as well. And so let's come back to these flash layers or ephemeral rollups. So these, as I said, these are rollups that are disposable in nature, and they're ideal for applications that drive a decent number of transaction volume, but in a very short span of time. So imagine something like a mint event, which could be extremely popular and hyped, and you want to make sure that it doesn't create a gas war-like situation if you want to host it on a general purpose chain. So take, for example, Yuga Labs, right? For example, so if you're doing Yuga Labs and you want to do a mint event, you know that your project or your mint event is going to be super hyped, and you want to make sure that that doesn't create a gas war-like situation. So you would spin up this rollup that would be disposable in nature. So you do your mint event. So once you have spun up your rollup, you do your mint event on the rollup. And once you feel like you have sold out all your NFTs and there's nothing left to do, and at that point, you can basically take down this rollup, and all the assets that were minted on the rollup will go back to the base chain. And at that point, you can basically take down the infrastructure, and all the assets move back to base chain, for example, Ethereum, and any node infrastructure, for example, RPC endpoint and those sort of things will go away and will be taken down. And so it's a very resource optimized version of rollups. The second, and as I said, the benefits are multiple. One is, as I said, if you are minting NFTs, for example, if you're using for a very short span of time, it allows you to kind of have a dedicated block space, but in a very kind of resource optimized manner. People would be familiar with user experience, will have familiar user experience in the sense that if you are your users are familiar with EVM, you could have EVM runtime on the rollup side as well, and it's very your assets go back to the base chain. So for example, if you're an NFT project, it's very important for you to have liquidity, and so you want your assets to go back on Ethereum so that you can trade. Your users can go and trade on OpenSea and enjoy all the liquidity benefits that Ethereum and the base chain provides you. And so the second part, this was the flash layer. So these are rollups that are disposable, and now I'm talking about the persistent rollups. So these are rollups that stay there forever. So they don't go down, they don't get taken down, they stay there forever. And these are ideal for anything that has a longer term kind of perspective. So imagine, for example, a DeFi project or a GameFi project, a SocialFi project. So these projects would be ideally should be on a persistent rollup because they'll prefer to have a longer term infrastructure. AltLayer has been there for quite a while now. So we have been experimenting AltLayer's tech in a variety of settings, in particular NFT mint events and gaming. So for example, we hosted twice already, and I think we are hosting one more event of Dark Forest soon. And so Dark Forest, every time we did host a Dark Forest, and we received about 200K transactions a day from about 300 to up to 800 players. So our tech is already being used for different activities, ranging from games to SocialFi to NFTs. There's some other usage metrics more on the tech side. So we ran a campaign a few months ago on flash layers. So we allowed people to go and deploy flash layers, and we asked them to go and do transactions on those flash layers. And during that campaign, we received about 100 million transactions on those flash layers. We'll come back to it in a minute, but we also have a network called Beacon Layer, which basically acts as a decentralized sequencing layer, and Yaoqi will give a talk about this later. And that has already been live on testnet, and that has done about 250,000 transactions already. We also have a multi-sequencer testnet, so there's a testnet that has multiple sequencers. They run a local consensus protocol among themselves, and that has also been live, and it has done close to about 1.5 million transactions already. So as I said, this is Rollup-as-a-Service Day. Our idea was to bring together experts in the rollup and the modular space to discuss and share insights on the latest technical developments and economic points of view. We have an exciting lineup of speakers and talks. This will range from shared sequencing to role of restaking. So Sreeram from Eigenlayer will be coming up next after the talk. We have talks on MEV, PBS designs, and economic designs for rollups. So this will be mostly talks to start with. We have a panel towards the end with Stephanie from McCorry, Patrick McCorry from Arbitrum, and Medha from Variant. And really at the end, we'll have a Q&A session with myself and Yaoqi if you have any questions around rollups in general, rollup-as-a-Service platforms, but also AltLayer in particular. So thank you very much for your time and attention, and enjoy the talks.
Hello. Good morning, everybody. Welcome to this talk on Eigenlayer, which is a data availability mechanism for rollups. In this talk, I'll try to motivate why we think this is an interesting mechanism. The talk is subtitled Hyperscale Open Innovation for Rollups. And Amrit gave a great talk just before this on AltLayer. And first, thanks to Amrit and Yaoqi for inviting me to this great day, the Rollup-as-a-Service day here. So what I'm going to talk about is how do you design a data availability layer that supports this kind of an aspiration that AltLayer presented, which is you want to support a large amount of throughput. You want to bring an insane amount of activity into the crypto ecosystem. So that's why we call it hyperscale open innovation for rollups. Firstly, I want to thank several of my team members who've contributed to this. It's always a joint effort, and thanks to all of them. Okay, let me jump into the applications. So we want to start this with, we're talking about hyperscale open innovation, and the question is, why would somebody be interested in this? And I want to start with a motivating thing. If you want to try to measure applications in the crypto ecosystem, you can kind of do this on two axes. One axis is what throughput do they consume, and the other axis is how much value per bit is transacted. What is value per bit? Like per bit of information that you're sending through the system, how much is a single transaction worth hundreds of dollars, or it's worth like a penny. And okay, so why is this important? If you take this, where we are operating in blockchains today, very clearly we are in the top left quadrant here in the figure, which is we're transacting systems, mostly financial and NFTs, which have high value per bit. These objects that you're trading or sending are worth a lot, but it's not a lot of throughput. So that's the axis on which blockchains today are operating. But where we want to be, so we want to enable new and interesting applications like gaming, social, high throughput DeFi. Not only we want to go to the high throughput regime, but also we want to get to the low value per bit, like a tweet. How much is a tweet worth? Maybe it's worth a cent, maybe it's worth nothing. So you want to go to that regime. You are talking about a very different kind of system architecture, which would get you there. But even if the value per bit is low, because the throughput is high, the product of these two is what the total value transacted through the system is. So if it's value per bit times bits per second, right? And so that's value per second. So that's this curve, right? Okay, so we want to get to this regime where you have very high throughput, but low value per bit. But the fundamental thing is, therefore, the transaction cost per bit needs to be small. Okay, so if you look at transaction cost per bit, there you can look at what are the fundamental contributing factors to this. I think there are three basic contributions to the transaction cost. Number one is the capital cost, right? The capital cost is basically you need staking. If you want security, you need staking. And if you have staking, then there's a certain opportunity cost of capital. So that's the first contributor to the capital cost. The second contributor to the capital cost is operating cost. You have to actually run the system. You have to download the data. You have to do all these things. And then the third contributor to cost is actually congestion cost. And essentially what we've done is to think about like how do we reduce these three axes? If you look at the third one, the congestion cost is basically just if you look at the congestion cost, it's fundamentally coming from everybody who's transacting creates an externality on all the others. And if you're creating congestion, you need to pay for it. So right now, pretty much all the blockchains fundamentally price for congestion. So you're basically running at congestion cost. So let's look at all these three costs and how we think about at Eigenlayer of reducing these costs. For the capital cost, if you want a certain amount of stake, really, and if you have $1 billion staked and you have to pay off the opportunity cost of the capital, you may have to pay a 10% APR to actually compensate that. A 10% APR of a $1 billion, we're talking about $100 million annually in fees that needs to be paid for it. So one way we can reduce the capital cost of staking is by having shared security. You have the same pool of security supply not only to one application, but to many, many applications. Same economy of scale that really powered general purpose proof of stake blockchains can actually power other things as well. So that's the capital cost. If you have shared security, the principle that Eigenlayer builds on is called restaking, which is the idea that if you stake in Ethereum, you still have that capital that you can actually make additional credible commitments with. For example, you download and run and validate a new system, you can actually promise that you're running that system correctly. Okay, so we have capital costs, we have operating costs. If you have, every node needs to download and store the data, that actually adds up quite a bit over the entire system. Today, actually, the operating cost is non-dominant. Like even for a pretty expensive system like Solana, you have like thousands of nodes. Each node maybe annually costs like $10,000. So you're talking about the annual operating cost is $10 million. It is high, but it is not as high as the capital cost because you have several, 5 or 10 billion worth of stake. That means you're paying off like $1 billion in like the staking APR. Okay, so you have the capital cost, you have the operating cost, which may not be dominant, but as you increase the throughput, it'll start to become dominant. And finally, you have the congestion cost, and the way to reduce congestion cost is actually by enabling shared throughput. You actually build high-performance systems so that there is very little congestion to begin with. And you also build an economics where you don't have this unpredictable pricing of, oh, I don't know when the price is going to go up or down. And this unpredictable pricing actually leads to a large number of problems. Amrit in his talk earlier pointed out how these blockchains can actually learn from existing cloud systems like AWS. And I think we want to do something like that here, where, for example, in AWS, you can actually reserve compute for a long enough time, and you know that there is no congestion because you have reserved instances. There's also another concept called a spot instance, where you can go and buy an instance at the moment, but if there is congestion, that spot instance may be very highly priced. So, okay, so that's the core thing. We want to think about the fundamental cost basis of the system and make sure that we are actually designing a system which is very, very low in the fundamental cost per bit analysis. Okay, so you just saw the rollup architecture earlier, so I'm not going to go over this, but the core idea is that right now, rollup sequencer takes the data and then posts it on a data availability layer. Why do we need to do this? You need to publish, for the computation to be transparent, you need to publish the inputs to the computation. Because if you have the inputs to the computation, anybody can replicate the computation or continue the computation onward. So, there are ways to slice and dice this. So you could either publish the inputs to the computation or the outputs to the computation, depending on whether you're running a optimistic or a zero knowledge roll or a succinct validity rollup. But you do need to publish the inputs or the outputs of the computation on a data availability layer. So that's what does a data availability layer do? It enables anybody else who wants to know the inputs or the outputs to this computation to come and acquire it. Okay, so what properties do we need from a DA layer? Okay, actually, I'm going to just swap to a different presentation. Okay. So here we go. I think the animations probably work better on this. Okay, what properties do we need from a DA layer? We need the DA layer to be hyperscale. Okay, what do we mean by hyperscale? We want the bandwidth of the system to grow linearly with the number of nodes. The more the nodes in the system, the more the throughput that it should acquire. And what do I mean by nodes in the system? The nodes which are serving for data availability. The more the nodes, the better the system should be. In fact, it should be, the most ambitious goal would be exactly linear. You have n nodes, each of them have C bandwidth. You multiply the two, n times C should be your system performance. That's the most ambitious, right? You're aggregating all the bandwidth fluidly. But there's at least this factor 2 loss. Why? Because, we want to operate the system even when as long as the majority of the nodes are honest. So you do take a, factor 2 loss, but not that much more. Like that's what hyperscale is basically exact linear scaling for a DA layer. Okay, so that's the scaling. What about the cost, right? If you compare to a system like AWS, which is a single node downloading and storing data, maybe there's like a couple of copies or 5 copies which is storing it, and you want to get to that kind of a cost basis. Even though you want your system to have thousands or maybe hundreds of thousands or even millions of nodes, the cost basis should not be as though every node needs to download and store the data. So just to pick on the first point here on hyperscale, for example, what we're expecting is as the number of nodes increases in the system, today, most of the systems don't have linear scaling. They actually have no scaling. The more the nodes in the system, the capacity of the system remains the same. But what we're looking for is the more the nodes in the system bandwidth scales linearly, but the cost does not scale at all. So that would be an insane system, right? Like you have more performance as you get more nodes, the cost doesn't increase, and the security increases. So you're just like slicing the trade-off perfectly in your favor. What would be the latency limit? If you're looking at an AWS system, you send a request. There's, the request goes to the server, and the server says, yes, I stored the data. So that would be like a round-trip latency. And you'd want a system which operates at that kind of like a performance so that your rollup nodes are not stalling on some data availability layer waiting for 12 seconds or sometimes even 12 minutes for finality. It should be verifiable. Nodes, anybody who wants to verify that the nodes in the DA system are doing their thing, you should be able to verify it without having to download all the data. So this is the property we call verifiability, which is a simple light node can download and verify all the data. And finally, you want to have it be customizable. Customizable basically means like somebody wants a different quorum, somebody wants to use their own token, somebody wants a different kinds of properties. We want to be able to allow for all of these different kinds of properties. So this would be an ideal DA layer in our view. Hyperscale, bandwidths, not a limit, low cost, low latency, verifiable, and customizable. And so we're building a system called EigenDA, which is built on top of Eigenlayer. Eigenlayer is this core platform which is based on restaking. So the idea of Eigenlayer is you stake in Ethereum, you set the withdrawal credentials to the Eigenlayer contracts. Eigenlayer is a set of smart contracts on Ethereum. So you stake in Ethereum, you set the withdrawal address to the Eigenlayer contracts. And in the Eigenlayer contracts, you set your own wallet address as the withdrawal address. So what you're adding is really like a step in the withdrawal flow. And what this does is it really allows the system to enforce a system of like checks and balances where, like, if you're not operating for the services that you opted in correctly, then the system can enforce a penalty on you. So that's the basic structure of Eigenlayer. Basically, we call it restaking, which is you stake in Ethereum and then you set the withdrawal credential to the Eigenlayer contracts, adding a step in the withdrawal flow, but then enabling trust transfer to all kinds of other systems, including like a data availability system. Okay, how is EigenDA achieving this hyperscale property? The core idea is using erasure codes to distribute the information so that no one nodes need to download all the information. So you encode it and send it to all these nodes, and each node only downloads a little bit, but they also come with cryptographic proofs that they've been encoded correctly, so you don't need to worry about it. So we use KZG polynomial cryptography. This whole architecture of the cryptography underlying EigenDA is basically built off of the Ethereum roadmap. In the Ethereum roadmap, we have this thing called dank sharding, which is a mechanism to actually scale the data availability bandwidth of Ethereum. EigenDA is basically like an opt-in system of dank sharding that we've built. And because it's out of protocol, there's a lot of degrees of freedom that we have, which actually lets us optimize even more than dank sharding. So the dank sharding throughput is roughly 1 megabytes per second, 1.3 megabytes per second. We are already at 10 megabytes per second with EigenDA. And whereas the node bandwidth requirement to run an EigenDA node is actually much smaller than all the other systems. Okay, so really this is one of our vision for Eigenlayer is that anybody can come and build these new features on top of Ethereum security or borrowing at least aspects of Ethereum security. And EigenDA is basically, and what we want to do is to enable people to experiment with new kinds of distributed system technologies that can then be built on top. And the best ideas can then be internalized back into Ethereum over a longer time scale. So EigenDA is our first kind of product on top of Eigenlayer, which basically tries to achieve this. Awesome. So let me skip ahead to some of these other properties. I mentioned it's low cost, it's low latency, but I think one of the most important dimensions that we need to consider when building the things like rollups is how does it interact with the economics? And if you look at the rollup economics today, there is a bunch of problems with the rollup economics. And the first one is the rollup's dominant cost is DA and DA cost is high, right? And if the DA cost is high, basically you have a problem, like you cannot make it cheaper than the DA cost. So that puts a floor on your cost basis. And the second problem that we find is the DA cost is uncertain. So you don't know because the DA cost changes based on congestion. Also, you have same site externalities. Amrit in his talk was mentioning about Yuga Labs. For example, if there's a Yuga Labs rollup and you have another, you're chugging along doing your own like other rollup, and suddenly there's a Yuga Labs mint and the DA layer is congested, and then now like your DA cost becomes uncertain, maybe it blows up by 10x, and you cannot satisfy your users, and that's really problematic. So the DA cost being uncertain is actually like not very good. And finally, rollups, unlike an L1 can fix a certain amount of inflation as the rewards for data availability inside their own system if you're an L1. But if you're a rollup, you can't pay in your own token for data availability. Even if you allocate a treasury from your own token, you still take exchange rate risk of, I need to exchange my token for ETH, and maybe the ETH price goes up and you need to kind of eat it on your rollup. Okay, so rollups with EigenDA can completely transform all these economics by getting the best benefits of shared security while retaining a lot of degrees of freedom. First thing is, with EigenDA, the DA cost is low. Why? Because the cost basis underneath EigenDA is low. And really, by optimizing on all three axes of the capital costs because of restaking, the operational costs because of the better like distributed systems architecture, and then finally for congestion costs because throughput is high, there is not congestion. So you actually get the underlying cost basis is low. Not only that, there is no uncertainty in the cost basis. You can actually go to EigenDA like you reserve a spot, a reserved instance on AWS. You can actually reserve, hey, I want 10 kilobytes per second bandwidth for the next 1 year, and you can go and reserve that on EigenDA. Because EigenDA has plentiful data bandwidth, we are able to actually do this. And many systems many rollups can come and reserve this kind of bandwidth. And what you get is actually positive same-side externalities. The more rollups come, the capital cost of the system is split among many more rollups, and the cost per byte actually goes down rather than going up. Finally, we allow rollups, when they're doing long-term DA reservation, to actually pay fees in their own native token. What this means is a rollup may come and say, hey, I want to bootstrap my system, and I want to give like the Ethereum stakers, 5% or whatever of my token economy as a DA fees for the first year, but also that helps me bootstrap the DA and bootstrap the rollup. This is something that you can actually do on EigenDA. Okay, so that concludes my talk. Basically, the core idea here is by optimizing the underlying cost basis of how you build a DA, you can actually achieve all the favorable properties: hyperscale, low cost, low latency, verifiability, and customizability on a common data availability layer, which is built on top of shared security from Ethereum.
Hi everyone. Hi, so this is Tomasz Stanczak from Flashbits. So I'll be talking today about cross-domain PBS interfaces for SUAVE. Thank you so much for invitation. Thank you everyone who's listening or who will be listening the recorded version. Let's go. So maybe first introduction of what's my story with Flashbots. Joined Flashbots in 2021 as a mate, which means like individual contributor, full-time. Worked on the late MEV GAF spec, so really just specifying what was built by the great early engineering design team from Flashbots. Then working on the early MEV boost design, so the design of the PBS for the proof of stake Ethereum. Then later focused on the product management of the early Flashbots relay in the time of the MEV GAF, and then the Flashbots block builder later took over by others. Then worked on some of the SUAVE architecture components. So think of SUAVE as like many modules, like EDS components, working together towards the single unified auction for value expression. And I work on some of them, and some of the research I'll present today. It's based on the recent ones that when I have been exploring the decentralization, shared sequencers, decentralizations of the sequencers on L2s mostly, and the cross-chain MEVs is something that Flashbots has been interested for a long time. We've published some of the research and kind of introduction to the cross-domain MEV in the past. So check out what Flashbots posted on the research basis in the past. And maybe as a disclaimer, so this is part of the build in the open of Flashbots. So it may present some ideas that are at the early research stage. They may not be fully reviewed by all the strategy teams at Flashbots, and this means that in some areas it may not be yet fully aligned with the Flashbots values, or even the quality of design of the research might be lacking. Nonetheless, I think that's worth to present it as an invitation to collaboration on the ideas presented, and also to work together towards the full alignment of how we want to present all the products at Flashbots, and how do we want to achieve full alignment, as always, eliminating, democratizing, distributing MEV in a permissionless, transparent way for Ethereum and other chains. So when you think about illumination, it's we bring transparency about the past. So explaining what happened on the chain, explaining through various tools and write-ups, explaining what happens now by the real-time dashboards, monitoring tools, solutions, and explaining also what will happen in the future by educating, researching, and providing fundamental research for the blockchain community. Democratizing like the permissionless access for solo stakers, for solo searchers. When you think about MEVKF in the past, this was all about enabling solo searchers to access the market without any big OTC arrangements. Nowadays, through the MEV boost, that's democratizing for allowing solo stakers to access that market without having to access to join pools. And distributing. So for the solutions like MEV Share nowadays, but also through SUAVE, our like ultimate goal, distributing MEV to where it originates from, to the users, or also together in collaboration with solutions from EF like MEV Burn, distributing it across all the Ethereum holders, and also like the holders, like the almost like builders of other chains, or whoever the users are. So all these free ideas also behind what I'm calling here as a MEV garden. So we say, let's move away from the dark forest of MEV to MEV garden. So we want to start introducing solutions that are, or continue introducing solutions that are very clearly divided into components, as modular way. They create a space that is adapting to all the different market conditions and different stage of growth of various builders, participants of that market. And obviously designed for the pleasure and utility of users. So maybe one aspect of it, the bright place that defines transparency, the transparency of rules and arrangement for sure, but not the transparency of what users want to hide. So privacy in all of this for sure. So some space for privacy in this garden is very important for the users to decide what they disclose about their trades and what they do not within the SUAVE ecosystem. All right, so with our design goals, to repeat some of these ideas and to introduce some new. So we want to support, well, first of all, what we are building with MEV Garden. We are building a solution for connecting block proposers with block builders, but in the cross-domain market. So the same as you say, PBS in Ethereum connects the Ethereum proposers, Ethereum validators with Ethereum block builders. We want to do that for L2s, for different domains, for multiple L1s, working together and potentially enable block building for multiple chains at once. So the builders to be able to make proposals, make bids about synchronized blocks together. Now, what we want to achieve while designing the solution, we want to support multiple solutions on sequencers. So however the design is, whatever the design is coming from L2s, from L1s, about how to sequence, whether to share sequencers, whether to provide the native sequencers only, whether they are ready to decentralize or not yet. All of that should be ideally connected to the solution, to SUAVE. We want to make sure that it's all permissionless and transparent in design. So any shared sequencer should be able to join the system without any whitelisting, without any permissions from trusted operators. So maybe unlike the nowadays solution of PBS, where to some extent you think that the relays are whitelisted by participants, the design goal here is to allow anyone to join. Be in line with Ethereum protocol direction. So we do origin from Ethereum space, and we do think that Ethereum is defining much of the innovation and defining how MEV is built into protocols. So we want to make sure that we don't design something that will be at odds with the designs coming from the Ethereum Foundation or from generally Ethereum community. We want to respect the market space of various players. And this is very similar to the first goal of supporting heterogeneous sequencer space. But here we say that not only we want to support it, we want to say that we build for other builders to connect, to co-design the solution. And again, this is an invitation to research together for sure. they should be stepped towards SUAVE. So even as we talk here about something that we call MEV Garden, it's not really like that's important, this name, because it should be simply a component of SUAVE and a step towards SUAVE. So it shouldn't be an alternative to SUAVE. It should be inconsistent with SUAVE. Anything that we design here should be part of this great vision of Flashbots that is this unifying all the expression of value within the context of MEV and builds the permissionless fair financial markets on and off chain. And the last part, which is particularly important because I would say it's not fully resolved in this design, it's ensuring equal rights of solo stakers and large operators, equal rights are more like equal opportunities, because rights are the same, but the opportunities are there for the large operators to have a bit of advantage, and hence the solution might be centralizing. Not very much. You'll feel that this is not a big concern, maybe not comparable to the one that we've seen in the PBS space before PBS was introduced, but nonetheless the one that is necessarily has to be solved before we say that the solution is consistent with the values of how Flashbots designs products. And a bit of a glossary, maybe the basics. So we do separate the roles of sequencers, proposer, builders, and relays. And particularly, I'm pointing out that the sequencers and builders separation. So sequencers are those here in this context. Sequencers are those who pick the transactions and order them. Builders are the ones who really take what sequencers prepared and wrap it up with the metadata and construct blocks out of it. So maybe further filter the data. Those two roles not necessarily have to be separated in the actual designs, but they might be. So we'll be separating those. And proposers are the ones who pick the blocks from the best blocks provided by builders and propose them to the market, right? So announce them to the chain, as it is nowadays with validators on Ethereum or in other situations. And domains is this concept that was introduced by the early cross-domain Flashbots research. So domains are either blockchains or centralized exchanges or any space which provides the opportunities for MEV creation for the state that is less or more discrete and changes over time. So when we talk about cross-domain, we can imagine that might be between the centralized and decentralized exchange, not necessarily two decentralized exchanges and not necessarily two blockchains. And the most important innovation here, not too complex, I hope, is the idea of global time, or maybe not too complex to understand, but possibly complex to implement. So the global time and synchronized proposals, we want to introduce the notion of looking at all the blockchains, all the domains together, and ordering the events there, and having a consensus on how those events were ordered across this non-unified time of different chains. And when we think about global time, the ordering of events, we show that we want to sequence events from multiple domains. It can be, as in this example, Ethereum Starknet Polygon blocks happening one after another. What we want to achieve is to say that the Ethereum block 100 happened before block 23 on Starknet, and we want all the participants of this market to agree on this ordering of events. So you have to find some solution to that, and we can propose something, but this not necessarily is easy. Might be. I think that open actually for discussion. So one of the examples that could be a set of chain observers, kind of oracles, or simply nodes that are trying to achieve a consensus that look at different chains, that are forced to observe chains and push the information about the blocks appearing as soon as they appear. So for the observation of the exchange of messages, we can do some kind of attestations to what we're observing, the same way that Ethereum is attesting to the blocks appearing and being observed in the P2P network. The same way we can build something here. Obviously, observation of multiple chains with various speeds. Think about Solana versus Ethereum and so on. This might be quite challenging, but we do want to have a simple chain of events like this. So there should be no processing, no excessive EVM operations. We just want the ordering of events. So you can imagine a construction like this built on some modern mempool solutions with modern, like the basic normal plus ball shark solution, for example. So saying, yeah, we want to have thousands or more events every second, but not necessarily any calculations based on that. It's just a blockchain of records of what happened when. Why do we need that? We'll explain. So we need the ability to prove something for slashing and relate that to the announcements of the shared proposers or show it. So I want to define also something that I call here synchronized proposals. So when we were designing some of the early cross-domain solutions at Flashbots, we were saying that we can't do the beads on the success of transactional cross-domain execution. So we can say that as a searcher, I promise to pay if something happens transactionally, and then someone can claim that bid, claim that payment. So as a searcher, I say, if you manage to execute transactionally on Ethereum and Starknet, then I'll pay you X if those transactions land on chain. And I don't know how you do that. You have to judge if you can do that. And if you do that, then actually the chain, the SUAVE will allow you to claim the payment. Now, the thing is, what I wanted to introduce with MEV Garden is also the possibility to make some kind of credible commitment or promise about the synchronized proposal. So if you're an executor on multiple chains, how can you promise to me that you actually can do that transactionally so I feel a bit more confident about bidding? And how can I potentially slash you if you don't deliver on that promise? So I'm proposing here just like 3 different definitions of that synchronized proposals. Not because I think there are only 3 or exactly 3 or that one of them is perfect, but just that in the context of our discussions in research, we realized that this is not just like very, very clear definition, that this is what synchronized means. So I'm proposing 3 examples, but what really is the final definition of synchronized proposal is a bit open. So here I'm saying the universal strict would be like we have a set of domains that we're looking at. Here in the example, it's Ethereum, Polygon, Starknet. There are 3 different domains. And I'm saying that the 2 blocks are synchronized only if they are like generally happening in a sequence after another, but there's no other block belonging to any domain in between. So in this example, Ethereum X is synchronized with Polygon Y. These are 2 blocks that are sequenced one after another. And the same for the last 2 blocks. But I already say that Ethereum X is not synchronized with Starknet Z because there's some Polygon block in between. Now, very often when we talk about cross-domain MEV we think about 2 domains, we don't care about what happens on other domains. So here we are very, very strict universally across all the domains that we could take ever into consideration in our global time assessment. So it might be really too strict. And we say that if there's any other event from any chain in between, then it's no longer synchronized. Like someone might have executed some kind of MEV extraction that changes the state of the cross-domain execution in a way that I am no longer too confident that transactional execution on Ethereum and Starknet will be good enough because something on Polygon might have changed the opportunities. As I say, it might be too strict, but we present it. The domain strict, probably closer to how I would think about it. It says that everything is synchronized as long as there are no other blocks belonging to the same domain in between. So I'm saying here that, for example, Ethereum X with Starknet Z are actually synchronized even as there is block Polygon Y in between, because I don't care about the domains outside of the domains that I'm considering in my cross-domain proposal, synchronized proposal promise. But I would say that the Polygon Y is not synchronized with Ethereum X plus 2 here. Why? Because there is some other Ethereum block. So I want to say that synchronized blocks are only the ones that within the same domain are after another, and there should be anything in between. And even less strict synchronized proposal definition is the one that says, well, there might be multiple blocks belonging to the same domain, So like Ethereum X is synchronized here with starknet Y+1, even as there is a starknet Y block in between. But what I'm blocking, like what I'm removing from the definition of synchronized is that there shouldn't be any other like pair of synchronized blocks in between. So Ethereum X here is not synchronized with starknet Y+2 because there's some other pair of starknet Ethereum blocks synchronized in between. So I'm saying that, well, I feel that I can extract something transactionally as long as there is no other opportunity to extract something transactionally in the same domains, which would totally lock me out of the ability to execute MEV extraction in a predictable way. As I say, this is not super strict definition. You can think of your own how you would like to say that something is synchronized. Why do we need those synchronized proposals? We'll start talking about the messages being exchanged between builders and proposers. So in Ethereum PBS, we have the builders, we have also the proposers, so the validators, and they talk to each other through the relay. And in the current design, the relay is the trusted party in between. The ePBS, so enshrined PBS in Ethereum assumes that the relay disappears, that actually solution doesn't change much because you still have the builders and the proposers collaborating. But instead of using the relay, there is some set of attestations and staged attestation and P2P communication that allows agreement on what the best bids between the builders are and how to keep the proposers to their promise and potentially slash them on non-execution, on non-delivering the promise. So we remove the relay, you remove the trusted component from in between. And we remember that design goal from the beginning of the MEV garden, which says, well, you should be in line with Ethereum protocol direction. So now we say that whatever communication between the proposer and builders about the synchronized proposals I would like to have, the messaging between those two parties, between the cross-domain builders and cross-domain proposers, the messaging should be not necessarily through the relay. The design should allow for the P2P-based communication. And I think we should intuitively see that, that there should be requirement for the relay that might be slightly more difficult because you don't have the same level of attestations. But with the global time, that we mentioned, it should be possible. Now, this cross-chain PBSs, as we introduced this cross-domain proposer-builder separation, we add in communication from proposer to builders, not only from builders to proposers like nowadays. So nowadays we have builders announcing their bids, announcing the best blocks, then it goes to the relays, or for the P2P communication goes to the proposers select the best block and announce it. And here we say that not only this direction, but also proposers communicate with builders back. They announce that they're about to propose something in a synchronized way. So we have those synchronized proposal announcements, and they should be ideally delivered and announced and included on the global time. And why on global time chain? Because you need to potentially be able to slash the proposer on failure of delivery, failure on the promise, right? So you're failing to deliver the promise. And why do we use this communication? Why we use the global time chain? Just to make sure that it can be permissionless and transparent. So the proposers can join and announce whatever they want, and they should be slashable. So there should be some deposit. You can imagine that it might be in the form of the Eigenlayer deposit. So the restaking, and anyone can join if you can verify that they actually made a deposit. It's transparent. It's included on that chain. This is an example of a proposal where I say I'm announcing a proposer, and there is a specific slot, like some time that I sequence, and I have a set of domain proposals that define the domain and domain slot ID, so some number on chain. And when I estimated my expression of global time or something, so sequence or date time when it would happen, and I say that maybe I'm proposing according to some rules of synchronization. So I'm saying that there is like universally strict announcement that I will propose on Ethereum and Polygon, for example, at the same time. And I say that maybe a minute ahead. So now the builders have this announcement. They can check that it exists on the global time. And then they start preparing the bids, and they know that I'll be slashed if I don't deliver. So they start to be a bit more confident to set the blocks. So if me as a proposer, if I accept the blocks, then I have to deliver those. And the same as I include my announcements on global time, also the beads with the headers can be announced on global time, and my commitment to the headers can be announced on the global time. So we can have the same properties of the commitments as in Ethereum PBS, where I say I'm about to publish that block, so I sign that header. So you give me the body of that block, the details of the block, the transactions, so I can actually announce it. And if I don't announce it, I get slashed. What can be the types of proposers? So as I mentioned, we want to respect all the players in the market. So whether these are shared sequencers, native sequencers, they can all participate in those announcements. Shared sequencers should be much more confident about doing any shared proposals. They may be absolutely sure, like 100% probability that whatever they will announce, they will not be slashed. In some cases, they might be randomly being chosen on different chains and sharing that with other sequencers that are competing with them. In those cases, they will maybe judge whether they want to risk slashing or not. Like, what's their level of confidence in particular unit of time that they'll produce the blocks that will be synchronized, that will be next to each other, that will be sequenced in the global time. And again, like whether these are centralized or decentralized sequencers, they can all make these announcements. Nobody is whitelisting them, nobody is blocking them. They should be allowed. So here you have an example of this global time when actually I'm indexing events and somebody announces that they're about to propose synchronized Ethereum N, startnet N+1, that they approve some bid for these two blocks with some hash. And since they approved and announced, both of those events can be slashable against their deposit through Eigenlayer or some other solution. And if it's slashable, then the bids can be protected the same way as they are nowadays protected with the slashing condition on Ethereum. So this design goal, it should be a step towards SUAVE. So as I mentioned, on SUAVE, we have designs for these bids to be payable on successful execution, but we didn't have maybe the design on how to slash on a promise and the executor telling that there is some specific probability of execution. So me as a searcher, as a cross-domain searcher or builder, I can feel a bit more confident. So it adds a piece of SUAVE like on the side of proposers, making similar commitments like on the side of bid makers, on the searchers. So now we have both sides actually trying to communicate of how much they can achieve and what kind of promises they make. And that last call that I mentioned that it's not resolved, and notice it here. So if I'm about to make announcements about the synchronized proposals, then the larger my stake is on two different chains, the more likely I am to have synchronized proposals. So the more often I will be benefiting from the extra bids, extra payments to me from the searchers. If I'm a solo staker, then I cannot do that on multiple chains because I'm probably not staker on multiple chains. So I would have to team up with someone or just give up and join the large operator, large pool that can actually synchronize this across many chains that they are operating. So there should be a solution when me as a solo staker can dynamically exchange messages with some other solo stakers and together make commitments to the synchronized proposals. So what is required? First of all, we need to define this communication between proposers, something that is reliable, and again, it would have some promises. But then the question is about the splitting the payment from the cross-domain block builder, cross-domain sequencer. About how exactly I'm paying to the proposer on chain A and chain B. So this should be doable. This should be the easier part. Maybe slightly harder is the slashing target. So if I don't deliver my promise, who is really slashed? If I'm teaming up with as a proposer on Ethereum, if I'm teaming up with a proposer on Polygon, who will be slashed if we don't deliver that promise? That's a good question. So that's why this has to be answered. So within the roadmap, think about this collaboration of the multiple proposers has to be resolved, and also making sure that this design really answers the questions from the shared sequencers and whoever builds sequencers. So it all has to work together to satisfy the goals of how Flashbots builds the products. It's very early, it's building in the open. It's just a research, potentially components would be dropped, never delivered, or maybe something that would be fundamental component of SUAVE. Thank you so much.
All right, sorry, just getting up the slides here. Okay, can everyone hear me? All right. Okay, great. So I'll be talking about Espresso and the role of a decentralized sequencing layer for rollups. And I am Ben Fisch. I'm the CEO and co-founder at Espresso Systems, and I'm also an assistant professor at Yale. So first of all, one way to think about what rollups are able to provide for the ecosystem is horizontal scaling. And so we can think of this as every application that couldn't exist on a layer 1 blockchain can actually run its own rollup. You can also have applications that support other applications on top of them, like VMs or ZK EVMs being run by companies like ZK Sync or Optimism or Starkware, etc. But we can think of this as essentially a way of sharding computation across applications, so that the layer 1 nodes only need to verify these do this lightweight verification of either fraud or ZK proofs, but the actual execution of transactions for a given application is done by the application itself, okay? And it's a slightly different way of thinking about the role of a prover. You can just think of the prover as being associated with the application. The provers of Optimism are associated with Optimism, which really is an application that represents a VM that hosts other applications. The other key thing about why rollups actually help scale blockchains is they leverage heterogeneity, right? Rollups wouldn't help as much if all nodes in the system were of equal computational power. They're leveraging the fact that they're actually, especially in the case of ZK rollups, increasing even the work of some nodes, the powerful nodes that are doing the computation and producing the proofs, while making it easier for the weakest nodes of the system to verify the results. So the layer 1 nodes can be very weak, and we don't get bottlenecked on the weak nodes. Whereas at the application layer, the nodes that are actually executing transactions for a given application can be very powerful, and we don't need to have as many of them. They don't need to be as decentralized, in fact. The problem is that today, because rollup servers are playing such a monolithic role, they end up controlling too much. Right? So the application layer is not just executing transactions, but it centralizes the entire process of deciding which transactions to include and in what order. And this loses the whole set of properties that blockchains were achieving in the first place by virtue of their decentralization. So it can lead to censorship, lack of neutrality. It can lead to monopolistic pricing by the servers that are carrying out this entire centralized process. Essentially, the way that rollups look today with centralized servers that are doing both the proving and the entire process of deciding which transactions to include, the L1 is just now auditing the integrity of what are essentially Web 2 applications. Right? So we've removed the major role of the decentralized layer 1 to decide and manage the process of which transactions get included and in what order. And they're now just verifying and following along what each of these Web 2 applications are doing. And that's not a good situation to be in. So the solution is to separate ordering from execution. And the simplest way to think about this is that the architecture that would save us from this situation is if users would submit transactions directly to a decentralized L1. The L1 would only order and make available the transaction data. It wouldn't actually do any of the it would not execute, right? And then the application layer would just read from the layer 1, and every application-specific server would execute the transactions for that given application and prove the result and the state update to the layer 1. So this has also been called based rollup, which is a relatively new term, but in many ways this is sort of the purest of ideas for rollups, where the layer 1 is still doing most of the job. It's just that the rollup is only doing the execution. Users are submitting transactions directly to a consensus network that in a decentralized way is ordering them and making them available. Rollup servers just read from this, do the computation, and produce an update. Now, there could be a reason to separate out this transaction ordering and availability layer into what we might call a layer 1.5, which would sit between the layer 1 nodes and the application layer servers that are executing transactions. And what might be some reasons to do that? Well, first of all, protocol modularity. And it just as protocol modularity for data availability makes sense, right? The protocol that we designed to optimize for ordering and availability of data may not need to be the same that is running the L1 and handling the smart contracts and the bridges and verifying the proofs. I'll talk about protocol modularity on the next slide too, when we can, and in light of things like Eigenlayer, we may not even need to think about this separate layer as a separate physical layer. It may just need to be a separate logical layer. And second is there's an opportunity to make different design trade-offs from the L1. So for example, we could design this ordering and availability layer to have higher throughput and lower latency, but sacrifice on things like dynamic availability, which in the case of Ethereum is one of the main properties that Ethereum's consensus protocol achieves at the sacrifice of other properties. So as I mentioned, we can think of this layer 1.5 that's doing transaction ordering and availability as not necessarily even a separate physical layer. It could be run through services like Eigenlayer that enable this by the same set of physical nodes that are running the layer 1, or at least you could subsidize the participation of the physical nodes that are running the layer 1. But logically, it is separate, and it could be a separate protocol that operates differently from the layer 1's main consensus protocol. A second problem of the layer 2 ecosystem, the rollup ecosystem, which has less to do with the lack of decentralization and more to do with the sort of a fundamental trade-off that happens when you shard computation, is that the liquidity or interoperability becomes fragmented too. So applications on different rollups are now isolated from each other, whereas when they were all running on Ethereum, they were not isolated from each other. And this makes various things like atomicity, flash loans, etc., very, very complex to impossible. So bridging becomes complex. Certain forms of interoperability are now lost. Liquidity is fragmented. So we can ask, to what degree does sharing a sequencing layer, and when I say sequencing, since this is an overloaded term that some other people in the industry may use differently, but when we talk about sequencing as just the layer that is in charge of determining and finalizing the ordering and availability of data, does sharing that layer help with interoperability? Okay. So I will discuss 3 advantages of doing so. The first has to do with partially simplifying cross-rollup bridging and atomicity. The second has to do with mitigating systemic security risks of bridges for the rollup ecosystem overall. And the third has to do with cross-rollup building. So let's talk first about partial simplification. So in general, bridges require 2 atomic legs. You have an asset that is locked on some rollup A, and then a representative would be minted on some rollup B. So let's consider scenario 1, where rollup A and rollup B are utilizing different sequencing layers. Okay, in other words, different consensus protocols for finalizing their transactions. In that case, in order to implement a bridge, rollup B would need to verify both the inclusion of the lock on rollup A and also its validity. And verifying inclusion means that rollup B you would need to implement in rollup B, in the bridge contract on rollup B, some way of verifying the consensus of rollup A. In scenario 2, with a shared sequencing layer, part of this goes away. Right? So now rollup B only needs to verify the validity. It needs to verify the validity, and that could be not by executing the transactions itself, but more likely by verifying a proof from rollup A, whether if it's an optimistic rollup, it would be receiving it and waiting for the challenge period and then possibly verifying a fraud proof. But if not, then it would be, if it's a ZK rollup, then it could be verifying the ZK rollup proof directly. That still needs to happen, but it no longer needs to implement anything to verify the consensus of rollup A because they're sharing a consensus. And essentially, the lock and mint transactions are just in the same transaction bundle that was processed by this common shared sequencing layer. So the second thing I want to talk about are security risks of bridging. In general, we can ask, what actually goes wrong when consensus protocols are compromised? Right? How can an attacker profit by attacking a consensus protocol and reversing the finality of transactions? Of course, that's an inconvenience overall, but is there a way an attacker can profit, which thus gives it an incentive to attack the protocol? Often, the way in which attackers profit is through some form of taking advantage of a bridge that exists. Bridges offer the clearest example of profitable attacks. An attacker can lock an asset on chain A and then mint on chain B, reverse the finality of the lock on chain A, and now it has doubled its holdings. The common example of you could send an asset to a centralized exchange, withdraw fiat, and then reverse the send is actually an example of a bridge. It's a bridge between a blockchain and an external system, which is part of the centralized world, but it's still an external system, right? Sending money to Amazon to purchase a good and then reversing the transaction on the blockchain is another example of taking advantage of a bridge, because it's a bridge between Amazon's system and the blockchain. If everything stays within the blockchain, it's harder to profit from reversing the finality. So, of course, there are always going to be opportunities for profiting by reversing finality. But if you have many, many rollups that all have bridges between each other, then it massively increases the profit opportunities for the attackers of consensus protocols that are controlling the transaction orderings in these different rollups. And when rollups share an ordering finality layer, the attacker cannot profit in this way. Reversing the lock on one side of a bridge will also reverse the mint on the other. And finally, I want to talk about the advantages of cross rollup building. So when rollups use different sequencing layers, then a builder who's trying to build blocks simultaneously for multiple rollups faces complications, high risk, and generally slim chances of success. For example, it would be difficult for a rollup to make some kind of economic commitment to its user that it would get slashed if it doesn't include both legs of some kind of arbitrage transaction, because it's always possible that one of the blocks that it proposes gets accepted and the other one does not, because it's dealing with two different consensus protocols. Now, with a shared sequencing layer, because the consensus simultaneously proposes and finalizes without executing, but proposes and finalizes a super block for all the rollups running on it, and through proposer-builder separation, a leader in consensus may accept from a builder simultaneous blocks for one or more rollups. And therefore, a cross-rollup builder can guarantee any user-desired atomicity from flash loans to arbitrage, and it can post bonds that which would get slashed if it violated its promise of some form of atomicity to the user. And shared sequencing enables an honest builder to be certain that if it behaves correctly, it won't get slashed. So finally, I want to conclude with some open questions and challenges of shared rollup sequencing. One challenge that arises is around revenue sharing. So how is revenue shared among rollups that share the same sequencing layer? It's very straightforward for basic fees. All the fees that users are paying on transactions destined for a particular rollup can be attributed to that rollup. It's very easy to attribute what the marginal contribution of a rollup is to the profit generated from basic fees. And in fact, the fees can even just be directly encoded and paid directly in each rollup itself. It doesn't even need to go necessarily through the sequencing layer. And the rollups can pay a commission to the sequencing layer. There's many different ways that could be handled. That's not a hard problem. The much harder problem is figuring out how MEV gets shared. There's maybe less of a concern for rollups that want to mitigate MEV, and I'm going to talk about MEV mitigation on the next slide. But setting that aside, let's say that rollups do want to profit in some way from MEV or get a share of the profit from MEV. Well, the marginal contribution of each rollup to MEV is not transparent. In fact, MEV, there is no real public deterministic function that you can just run on a given ordering to determine what the MEV is. Rather, MEV is typically based on private information available to various actors in the system and is only discovered by running auctions and figuring out what different actors will bid. It's very hard to, you might think we could simulate the auction with each rollup independently, but it's very hard to simulate an auction truthfully if it's not being run for real. So this is a hard problem, and I'm leaving it as an open question that needs to be solved. The second open question that I think is very important and interesting is whether shared sequencing layers can be MEV mechanism independent. So there are many different approaches to addressing MEV and it can be a matter of philosophy, right? From optimizing it and democratizing access to MEV to preventing it entirely, whether you believe that's possible or not. So there are many examples of approaches from auctions to first come, first serve ordering protocols, threshold encryption protocols, time delayed permutations, etc. Some involve various assumptions, such as honest majority assumptions. So the question here is whether a sequencing layer that is shared by multiple rollups can be agnostic to the MEV mechanism favored by each rollup. It could be quite simple, I think, for threshold encryption, because the rollup could introduce its own separate threshold encryption set, and all the inputs that come to the shared sequencing layer are threshold encrypted. But it may get more complicated when we start considering other types of MEV mitigation approaches. So I leave it as an open question whether shared sequencing layers can truly be MEV mechanism agnostic. In any case, these are all problems that we are working on at Espresso Systems. Espresso is developing a shared sequencing layer for the rollup ecosystem, specifically focusing on Ethereum today. So thank you very much. That concludes my talk.
Hello, everyone. I'm Ed Felten. I'm co-founder and chief scientist at Off-Chain Labs, the company that developed Arbitrum. And I want to talk to you today about Arbitrum Orbit, the next step in scaling Ethereum. Orbit allows you to launch your own Arbitrum chain and to customize it to meet your needs so that you can have the freedom and the scalability that comes from supporting your own chain. So let me start by talking about rollups, going back to the beginning of Ethereum scaling. Rollups, of which Arbitrum 1, of course, is a famous example, are the leading approach to scaling Ethereum. And rollups have a bunch of advantages. They have low-cost transactions. By moving most of the cost of a transaction off of Ethereum onto the rollup itself, you can reduce transaction cost by a lot. When done right, a rollup can be fully trustless, with security rooted in Ethereum and interactive fraud proofs. The interactive fraud proofs are very important because they're the guarantee of security. And the Arbitrum stack is the only optimistic rollup stack that has working interactive fraud proofs. And then, of course, a rollup properly done is also drop-in compatible for Ethereum with full support for EVM equivalents. Arbitrum currently offers two chains that are managed by the Arbitrum DAO. Arbitrum 1 and Arbitrum Nova. And although they rely on the same core technology, they have slightly different technology and security models and therefore different cost. Arbitrum 1 is a general purpose optimistic rollup. It runs on the Nitro tech stack, which is fully EVM compatible, has been live on mainnet for about a year and a half now. Has been for about 6 months now. Call data in Arbitrum 1, the call data of your transactions, is posted directly onto the Ethereum L1, which guarantees that it's available for everyone. Gas savings, well, depending on what you're doing, it's often 20 to 50 times cheaper than L1 Ethereum. Your transaction result is provided to you in less than 1 second, and it's used widely for applications like DeFi and NFTs. Arbitrum Nova, on the other hand, is a general purpose chain using what we call the AnyTrust technology, also based on the core Nitro tech stack, full EVM compatibility. The difference from Arbitrum 1 is that with Nova, instead of posting the call data on Ethereum, it's instead sent to a special data availability committee. The result is a big savings in cost, even compared to Arbitrum 1, depending again on use case, 30 to 150x cheaper than L1 Ethereum. The average transaction response time is still less than 1 second, and it's often used for applications like gaming and social. So let me talk a little bit more about Arbitrum 1. And again, I'm deep diving into these technologies to show you what's possible with the Arbitrum technology, because you, as a user of Arbitrum Orbit, will have the ability to launch the same technology that's powering Arbitrum 1 and Arbitrum Nova and have your own version of these sorts of technologies. So Arbitrum 1. Arbitrum 1 really was the initial Arbitrum chain developed initially by Off-Chain Labs, and it's in alignment with Vitalik's vision of a rollup-centric Ethereum roadmap. Basically, Arbitrum 1, as I said, your transaction call data is posted to Ethereum. L1 to L2 bridging is done via a bridge contract that can self-enforce the validity of transactions. The security mechanism uses fraud proofs so that if malicious behavior takes place, security is still guaranteed by the Ethereum L1. And it provides a very strong guarantee. It's not subject to the kind of 51% attack or even 34% attack that some side chains have. Arbitrum 1, by its nature, is able to withstand the corruption of a large number of validators. In fact, you need only one validator that is correct and behaving honestly and is available in order for Arbitrum 1 to guarantee security. That's the key advantage of optimistic rollup technology if you have fraud proofs, as Arbitrum 1 does. The Arbitrum 1 ecosystem is very large, more than 2,000 dApp integrations. You can see a lot of logos here, lots of different dApps, especially in the DeFi and NFT space. Currently, over 1 million ETH reside in the Arbitrum bridge. That is more than 10 other major chains combined. You can see on the right-hand side an illustration of the dominance of Arbitrum 1, and the ETH flows over on the left. And I'm showing you this not just to show you that Arbitrum 1 has a huge market share, although it does, but just to show you that the community of L2 application developers have voted with their feet for Arbitrum 1 over alternatives, because the Arbitrum technology provides a level of performance and reliability that they really like. So if you look in terms of measures of value locked, Arbitrum 1 has, depending which day you check, $5.8 billion worth of value locked, and roughly 65% of the roll-up market share. Arbitrum 1 and Nova. Arbitrum Nova, because it uses external data availability service, it's able to offer much lower cost per transaction even than Arbitrum 1. And so it's been very attractive for games. And you see some of the games that are built in Arbitrum here. Let me shift gears, talk a little bit about Arbitrum Nova. Arbitrum Nova, as I said, uses the AnyTrust technology, which is also available to you as an Arbitrum Orbit developer. The Arbitrum AnyTrust technology indeed is very attractive if you want to run your own chain because of its low cost. So the way Arbitrum Nova works is the transaction lifecycle is a little bit different from Arbitrum 1. First, the Arbitrum sequencer will batch and compress the incoming transactions in order to be able to encode them as efficiently as possible. The sequencer then submits that data batch, whereas Arbitrum 1 would have put the call data after batching and compressing it onto the L1 Ethereum chain. Arbitrum Nova submits it to the Data Availability Committee, I'll call that the DAC, and then requests a data availability certificate from the committee. The certificate proves that the committee has collectively promised to store that data for you. And if you have a valid data availability certificate, that means that if even 2 of the committee members are honest, that you know you can get your data back. Once it has the data availability certificate, the sequencer posts that data availability certificate to Ethereum, thereby proving to Ethereum that that data that backs the next set of transactions on the Nova chain will be available through the Data Availability Committee. Now, if for some reason it's not possible to generate a data availability certificate, because who knows, maybe some of the Data Availability Committee members are down or not cooperating, then the chain will smoothly and transparently fall back to Rollup, post its data on Ethereum, and continue to make progress. So you get the advantage of having a very efficient Data Availability Committee when it's available, which on Arbitrum Nova has been always in the history of the chain. But if for some reason that's not available, you don't give up the safety of being able to fall back to Rollup. Okay, so let me talk about Reddit. Reddit has adopted Arbitrum Nova. Arbitrum won Reddit's scaling competition in 2021. This was fiercely contested among a bunch of different L2 scaling technologies. Reddit decided to go with Arbitrum for this. So Reddit community points are migrated on-chain on Arbitrum Nova with a wallet/vault that's built into the Reddit app. When Reddit stood this up, they migrated about 250,000 Reddit accounts onto Arbitrum Nova with their state at a total cost of about $1,700. Community points are live in 2 subreddits, and the Reddit community is quite large, 400 million users per month. And one of the reasons why Reddit chose Arbitrum Nova is the ability of Arbitrum Nova to scale up in order to support the level that is the ability of Arbitrum Nova in order to scale up to support the level of scaling that Reddit needed in order to know that they could bring all of those users into the Arbitrum Nova ecosystem. So the Arbitrum Nova Data Availability Committee has a set of well-known parties, including Reddit, Google Cloud, Consensus, OpenSea, and of course, we at Offchain Labs ourselves. And again, you need only 2 of these parties to behave honestly and provide data when they promise to, in order for the Nova Data Availability System to guarantee access to your data. Okay, so what's new in Arbitrum? The biggest thing that's new in Arbitrum is the EVM Plus concept and the stylus technology that implements it. So the way we look at it is EVM equivalence, the ability to run any program that could run on Ethereum, any contract or application, is crucial for Arbitrum. And we've supported that from the beginning. Now, but that's just a starting point. The stylus technology, which is currently in advanced development, expands Arbitrum 1 and Nova and can expand your Orbit chain to run smart contracts that are not written in EVM, but are written in other languages. It's compatible, stylus is compatible with Rust, C, C++ for writing your contracts. In fact, any language, any tool chain that can compile to WASM, WebAssembly, you can use that tool chain to write a smart contract that will run on an Arbitrum chain using stylus. So that opens up a vast set of languages and, just as importantly, tools for writing smart contracts. Now, I want to emphasize this is not a separate chain. This is not a separate silo within an Arbitrum chain. This is fully interoperable, fully composable with smart contracts that are developed using the classic EVM and Solidity development stack. What you get is that full interoperability. Users can interact with these stylus supported contracts. They can call back and forth with EVM Solidity contracts. Indeed, if you develop with stylus, your users don't even need to know that you are using stylus. They'll just get the benefit of your use of an advanced software development stack. Also, significantly, we expect contracts that use stylus to get a significant performance gain compared to EVM. And the reason for that is simply that WASM is designed for efficient execution, and it's possible to execute WASM much faster than you can execute EVM. So significant performance gain, again, with full compatibilities. So this is additive to the EVM ecosystem, hence the name EVM+. Okay, now let me talk about Arbitrum Orbit. Having talked about the main Arbitrum chains and the technology, let me talk about Orbit. Arbitrum 1 and Nova currently serve many thousands of applications, millions of users. They secure billions of dollars of assets. Yet some applications, perhaps yours, want to go a step further. Orbit lets you launch your own chain, which you can customize however you like, while retaining the time-tested security and scalability. Everything that you and others love about Arbitrum, you get to keep, but you get to have your own chain and customize it. Orbit is permissively licensed so that you can customize and launch your chain on top of Arbitrum 1 or Arbitrum Nova without needing to ask permission from anybody. So what does Orbit give you? Well, it gives you Nitro, the Arbitrum Nitro stack, which is time-tested, and extensibility. Not only will you benefit from updates that Arbitrum 1 and Arbitrum Nova deploy as they become available, but you can also implement updates that the Arbitrum DAO, for whatever reason, has not adopted for Arbitrum 1 or Nova. So you get not only the advantage of the current Arbitrum Nitro stack, you get the advantage of further developments in the stack, whether they're done by off-chain labs or by others in the community. So this gives you more flexibility than the public chains. You get increased gas price reliability. Many types of dApps rely on having predictable transaction costs. Because the Orbit chains are somewhat isolated from a gas cost point of view from the Arbitrum L2 and Ethereum L1 traffic, using an Orbit L3 chain means that you have more reliable gas prices, which means that your dApps users can rely on more reliable transaction costs. You get account abstraction. Account abstraction, as popularly implemented these days on Ethereum via ERC 4337, that is supported on Arbitrum. That's available to you right away. So you can use that. Predictable gas prices help make alternative cost models more feasible, such as subsidizing fees or indeed replacing transaction fees entirely by, say, some kind of subscription model or whatever it is that you want to do for your application. This helps you further abstract away the technical complexity of decentralization, helps you deliver more familiar experiences to non-technical audiences. All the flexibility of account abstraction is there. It's on Arbitrum 1, it's on Arbitrum Nova, and it'll be on your Orbit chain. There's also the ability to customize the protocol logic. Now, many people won't need this, but if you do need it or want it, you might want to modify the logic of your chain settlement, its execution or its governance protocols in order to meet whatever your specific requirements are. And you're allowed to do that. The license allows it, and the software is flexible so that you can make the customizations that you need. Orbit's L3 chains let you do that while still deriving security from Ethereum L1 through the Arbitrum DAO's governed L2 chains, Arbitrum 1 and Nova. So you get the ability to customize and also the security foundation of Arbitrum under you. There are a lot of decentralization options here. Arbitrum Rollup derives its security from Ethereum. You can choose to use Arbitrum AnyTrust with the assumption that you can trust the Data Availability Committee. Orbit L3 chains let you use either of those models. You can also introduce additional trust assumptions if you want in order to meet specific needs, or you can go with simply take the default off-the-shelf trust assumptions. This, again, is up to you. It's customizable. And of course, there's low upfront setup costs. Orbit L3 AnyTrust and rollup chains can be created quickly and cheaply because they're on top of Arbitrum 1 or Arbitrum Nova, which have much lower cost than launching on top of an L1. You're going to benefit already from the cost savings of Arbitrum 1 and Arbitrum Nova. Your chain, although almost everything that happens on your chain will be within your own chain's resources and economics, you do rely to a lesser extent on the underlying chain that you're built on. And by building on Arbitrum 1 or Arbitrum Nova, you get lower cost and more flexibility, and you benefit from that as well. Security, obviously, Orbit chains can be configured out of the box as either AnyTrust or rollup chains. They can be further customized as well, but you get the benefits of Arbitrum's security mechanism. You get working fraud proofs, not only working today, but a fraud-proof technology that has been live for a long time and has serviced many millions of transactions on Arbitrum. If you want, you can permission access to your chain. You have the option to enforce transaction submission or contract deployment restrictions. Whatever the goals of your chain or your business model is, you have the option of doing that. Now, I have to say there are some drawbacks to running your own chain. These are drawbacks of running your own chain no matter what technology you use. And I want to acknowledge them because although Orbit chains or running your own chain is attractive for many use cases, it's not for everyone. First of all, there is some friction at the chain boundary. You'll need to connect to a bridge in order to leverage existing DeFi infrastructure instead of natively having all of those teams build on your chain, right? So on the layer 2, Arbitrum 1 and Arbitrum Nova, there are many users, there are many applications already there for synchronous composability. If you build your own chain, that won't be there, and you'll have to get those people on board or else use cross-chain technologies, which are good and improving, but still that will not be without friction. There's also more infrastructure complexity if you're running your own chain. If you're using one of the existing large chains, then all that's provided for you. But if you have your own chain, you'll need to think about RPC providers, bridges, block explorers, exchanges, fiat on-ramps, and so on. All of that's already taken care of if you're using existing public chains. If you do it yourself, of course, you're going to need that. Although, of course, the whole idea of Rollup-as-a-Service is to provide that for you as a service and to reduce this drawback. Okay, so is Arbitrum Orbit right for you? Well, many apps are better served by public chains due to the widespread infrastructure support as well as the synchronous composability with other applications. But if you want the scale, the flexibility, the customizability, the ability to control economics and governance that come from having your own chain, Orbit will do the job for you and will do it well. Now, the emergence of Rollup-as-a-Service infrastructure is really important here because the rise of RaaS infrastructure support is going to shift this trade-off to make it more attractive to launch your own chain via Orbit for more use cases. So we're really excited about Arbitrum Orbit. We think it provides huge opportunities by bringing together the time-tested Arbitrum technology and the ability of the Arbitrum community to deliver reliable and efficient software, making this available to people who it wasn't available to before. We're excited about Orbit. We're excited about the growth of RaaS infrastructure and the RaaS economy, and we'd love to see you be a part of it. If you want to learn more about Orbit, you could go to this URL here, arbitrum.foundation/orbit. There's plenty of documentation there, including instructions for launching your own DevNet chain to test it out yourself on top of the Arbitrum Goerli testnet, with instructions in the future for launching on live on mainnet. You're going to hear more exciting announcements about companies and teams using Orbit. We would love to have you join that community. So please reach out if you're interested. Thank you very much. Thanks for your time, and enjoy the conference.
Hi everyone, this is Omar Yehia, the Head of Investments at Meta Labs, and today we'll be talking about the economic considerations of modular roll-up services. Now, normally I'd begin by trying to define what a roll-up is, but given what we've seen on Twitter recently, it turns out it's a little bit more difficult than what it seems at face value. Now, all one has to remember is that a roll-up tries to move parts of the execution from the base layer, from the L1, off-chain, while saying something about the guarantees of the data availability. And then it ultimately ends up posting a smaller version of the data that is required to reconstruct the state, or at least say something about the validity of the state back to the L1. So the raison d'etre of a rollup really is to guarantee the correctness of off-chain execution, as well as say something about the data availability behind that execution.
And a few other things to remember. The rollup nodes actually depend on the host chain in order to be able to update their state, because the host chain defines the state transition function, and as a place to nominally store their history, the history of the actual rollup. We know that the actual layer 1, its consensus, and therefore its security, does not in any way rely on the rollup, because it's not waiting on a block-by-block basis to determine what happens on the rollup. Instead, every once in a while, the rollup will post its state, which has to be consistent with the rules defined by the L1. And the bridge between them, if you were to use the word bridge, is the ability for the layer 1 to check the validity of the state transitions that are proposed by the L2 every once in a while. Now, usually people talk about this idea that the rollup, in a sense, partitions the host chain's consensus, or really its state, by allowing it to apply a subset of rules that only really apply on the rollup, so long as they are globally consistent with the rules that are prescribed by the L1. Now, because the rollup needs to know about its own state as well as the state of the L1 at all times, then the cost of running a rollup is strictly higher than running just an L1, because you're basically now having to take care of two different chains. So this must mean that there must be some utility that's generated by using a rollup that justifies spinning it up. Now, this might seem obvious, but since we're going to talk about the economics of rollups, I think it's important to highlight. Now, something to remember is that blockchains, by design, are extremely computationally intensive. It costs approximately 10 million times more to do a calculation per byte on Ethereum than it does on AWS. That is the cost of achieving the properties that are promised by a distributed ledger. And this is really the sole motivator of considering rollup economics, because a minor improvement in the execution environment can reduce the costs dramatically. And you can see that this gap is enormous. And so there is sort of a lot of margin to be gained by trying to cheapen the execution environment while preserving censorship resistance, decentralization, and so on. Now, the basic idea is that instead of submitting transactions or a series of transactions on the L1 and incurring the sort of base layer cost, you move this process off-chain, and there's a set of actors that are responsible for essentially doing this and then posting the results back on chain. Now, depending on the type of layer 2, whether it's sort of an optimistic design or a pessimistic design. Pessimistic here refers to validity proofs, of course. These operators behave in slightly different ways and use very different technological architectures, but the basic principle is sort of the same. And as economic agents, they have to think about the following question: how do I provide these services while pricing them in such a way that it is still profitable for me to do so, and while the user experience is at least as good as what they would experience if they were executing directly on the L1. Now, there's this concept of application-specific blockchains, which I refer to more generally as specialized execution chains, whether rollups or not, while using validity proofs or fraud proofs or whatever type of mechanism. They handle the execution in a modular way, and this modularity relies on a simple principle that you are able to share the security of the underlying L1, which has a cost, and perhaps there is also a way to communicate between these different layers with or without going through the base layer. Now, the utility of these modular setups lies in their ability to remove the constraints that are normally imposed on a network that's trying to bootstrap a cheaper execution environment, but also incurs fragmented liquidity, different UX, additional latency. And the premise is that these new primitives that are being built from a technological perspective allow these modular networks to build a stack that is vertically integrated and does not detract away from the user experience, and certainly offers a much cheaper execution environment. Now, when it comes to the economics of these layer 2s, the name of the game here is to achieve positive network effects for unit economics without materially sacrificing decentralization and certainly not security. And what I mean by positive network effects for unit economics is that you basically escape the paradigm that you're normally constrained to on the L1, where the more transactions that you have on a monolithic L1, on average, the higher the cost of a single transaction becomes. And that's basically a statement of network demand, right? For a fixed computational supply, as the demand for computation increases, the price increases. On the L2, and that is really the fundamental insight, there is this ability to batch transactions together, and then there is this economic regime where it is possible that as the number of transactions increase across the network, you can actually have lower costs. Right? It's simply due to amortization. Right? You compress some parts of the data that's required, and you do so by allocating costs to multiple users. Now, of course, if there's only a single user of the network, this is sort of moot. But in the case that you have many, many users, each with a small subset of transactions, then you can actually have decreasing costs. Now, by definition, again, the utility of the user of the L2 has to be strictly larger than the cost of running the L2 individually and the cost of publishing data to the L1, which I really term here as the cost of inheriting the security. There's sort of no free lunch. When people say that the layer 2 in some way inherits the security of the L1, what they're really saying is that there is a cost to publishing data back to the L1 as well as the cost to actually reading the state of the L1. Yeah. Why is all this important? Well, a layer 2 economically must be designed such that the utility of using layer 2 for a particular user is strictly higher than the utility generated from using the L1, and the same is true for the operator. We call a layer 2 economically sustainable when the utility of both the operator of the rollup and of the user is strictly higher than operating on L2 than it is on the L1. Now here's where we get into some of the architectural trade-offs or design trade-offs associated with these different agents. So in general, we have somebody who's responsible for the data, somebody who's responsible for ordering the data, somebody who's responsible for the state of the rollup itself, and then somebody who's responsible for generating some sort of proof that's associated with the validity or the correctness of the state transition. Now, again, depending on whether we're talking about a validity rollup or an optimistic rollup, the generation of the proofs is a sort of fundamentally different process. But when it comes to sequencers, in many ways, they're sort of the same. The sequencer is the agent that is solely responsible for ordering the transactions, and then they send that sequence of transactions to someone who ultimately uses them in some capacity to update the state. And the idea behind running a sequencer from an economic perspective is straightforward. Basically, the sequencer has to design, usually algorithmically, on an order of the transactions that is strictly different than the order in which the transactions come in, that maximizes some sort of revenue. Now, of course, there might be some cases or some instances in which the ordering itself is constrained by some sort of fairness algorithm. I mean, in the case of centralized sequencers, where the user simply trusts that the sequencer will order transactions, let's say, as first come, first served basis, the sequencer is simply paid for the fact that they do this. Of course, the sequencer runs a particular set of hardware, which requires some off-chain compute costs, and they at least need to cover those costs and perhaps make a small profit on top of that. The rules by which they order the transactions highly depends on the environment and also the actual designation of the agent as a sequencer. So in the case where you have a single sequencer, it's sort of trivial. This person is guaranteed, or this operator is guaranteed to be sequencing their transactions, and so their economics are sort of straightforward. Whereas there are cases in which the sequencer is decentralized, so that you have multiple agents that can perhaps bid or can be randomly selected to generate the canonical ordering of transactions. And it is in that case that the economics start to become non-trivial. First, because you now have to ask multiple agents to participate, knowing that only some of them might be able to propose the sequence of transactions. And so if that's the case, then there also has to be some sort of profit sharing scheme amongst them, so that the ones that are idle, or at least the ones that are not at the front of the line, are able to cover their opportunity cost, or at least their sort of hardware costs. Now, this in and of itself is an entire sort of area of research, but the thing to remember is that the sequencer, even if they were to try and be malicious, really at best they can only censor transactions, or they can slow down, or in some cases stop the operation of the rollup, but they can't insert malicious transactions, because the process to guarantee the integrity of the transaction is sort of completely separate from the sequencer function. However, what that means is that we still have to worry about censorship resistance and the liveness of the rollup. The rollup is useless if it is completely secure but doesn't do anything, and so you want to design the sequencer architecture so that A, it maximizes liveness, and B, it also enables multiple sequencers to come in, not only for the sake of decentralization, but actually for redundancy. And this is where the economics become very, very important. And there are different sequencer design approaches, some of which include bonding, or a proof of stake type sequencer, where the sequencer guarantees some ordering of transactions, and if that guarantee is sort of not upheld by the sequencer, then they are slashed. They can also guarantee certain transaction selection criteria. They can price their own transactions. They can use a global market for determining fees, or a local market for determining fees. And most importantly, as we mentioned before, they can also say something about the fairness of transaction processing. And what that means basically is that they commit ex ante to a scheme that orders the transactions, and you can go back in time and audit that and make sure that that's indeed what the sequencer has done. Now, the really interesting parts about the economics of running a sequencer is that now that you have basically separated the security of the underlying L1 from the execution environment, you now have opened up a design space of different types of economic instruments, like derivatives, that could be used to run a sequencer. A sequencer, in many ways, has to hedge against the fluctuation of their variable costs, and their variable costs are, of course, tied to the L1, and they're also tied to the transaction demand. And so you can easily see that having something like a collateralized sequencer obligation, which is an instrument that's sort of analogous to a debt obligation, but in this case, the debt is not monetary, but rather the users commit to using a particular sequencer, and their commitment has to be guaranteed somehow. And then the sequencer, in response to that, commits to some sort of soft finality and deposits collateral as a bond. And what that does is, instead of being subject to the fluctuations of the spot market, whether it's on the L1 costs or on the transaction demand costs on the L2, the sequencer has some sort of forecasting ability in terms of the demand for their services. So this becomes very interesting, because you can now have a set of sequencers in a competitive market go out and issue different types of instruments that are tied to their future performance. And these instruments can be priced based on their previous performance. So in the same way that you have credit rating agencies issue different analysis and ratings for the creditworthiness of different financial institutions or companies based on their balance sheets, based on their workforce, based on their previous performance. And that enables the marginal creditor to think about the risk that they're taking by allocating capital or committing to a long-term contract or some sort of service agreement with this particular provider, you can now develop a reputational system upon which you price the future performance or rather discount the future performance of these different operators. So that becomes quite interesting, not just from a pricing perspective, but also it makes the economic forecasting problem for the sequences themselves much more tractable. And this is particularly valuable in the case where you're using some sort of proof of stake based sequencer, where it becomes very important to know upfront what the cost of running the sequencer is going to be for a given period of time, because there is also the cost associated with hedging that exposures, particularly if the bond is not in a numeraire, but rather in a different currency, something like ETH, so that the operator can hedge their exposure to that currency as well. So now is probably a good time to talk about MEV. And what that generally refers to is the capacity to reorder transactions in such a way that the person who does the reordering, or the entity that does the reordering, benefits at the expense of another entity. And of course, from their perspective, this is a positive, and from the counterparty's perspective, that's a negative. But it's useful to make the distinction between basically the two different types of MEV. There's accretive, what I call accretive, and what I call parasitic MEV. Parasitic MEV is exactly what it sounds like, where the all of the agents external to the sequencer experience a net negative, or at least the vast majority of them, it's a net negative due to the reordering of the transactions. And accretive is sort of the opposite. Now, a good example of parasitic MEV would be something like sandwiching, right? On some sort of exchange. And a good example of accretive MEV would be something like interoperability as a service, whether it's with different types of rollups. Auction clearing is another good example. These are sort of accretive to all of the participants external to the sequencer. Now, my hypothesis there is that there is enough diversity already in rollup providers, and now I'm referring to different rollups and not even necessarily sequencers, that parasitic MEV, the operator has no choice from a social perspective but to rebate it or pass it back onto the user, because there is enough of a competition for rollup providers, let alone different sequencers, that will incentivize users to move away from the environments in which there are parasitic MEV. Now, obviously, in the case where for a single rollup you have a market for sequencers, that just becomes even simpler. In the case of accretive MEV, that's where the argument could be made that in the same way that a private company provides some value for a user, and it gets to keep a bit of that value in the form of profits, the operator or the sequencer that provides accretive MEV to the users will be allowed to keep that as part of their P&L. And that shouldn't be surprising because something like auction clearing obviously requires running some sort of algorithm as well as incurring hardware costs. So of course the operator should be paid for that, and the users would be happy to, so long as it's within their utility framework, to pay a little bit extra for the profit of the operator. Now, speaking of profits, we know that, as we mentioned before, a marginal improvement in the cost of execution off-chain can provide a dramatic improvement in the overall cost of execution because the cost of execution on the L1 is so high. But another thing to remember is that on the L1, the inter-machine workload variance is actually quite small. So by that I mean most validators are running similar workloads. And why that's important is that on the L2, the variance is actually quite large. And the reason for that is the same reason that we mentioned before, this idea of decoupling between the execution, its efficiency, and security. This leads to what I call a sparse market for L2 computation, in the sense that you now have a very wide spectrum and therefore economic opportunity for the operators to prove different types of transactions, different types of workloads, and sequence different types of transactions as well. So now the name of the game becomes what different optimization routes or strategies could be used to reduce the ultimate cost of running the L2, whether it's from the sequencer's perspective, whether it's from the prover's perspective, and so on and so forth. And this is where, of course, we have validity proofs that come in all different kind of flavors and forms. We have data availability solutions that change the architecture and therefore the economics of storing and querying state data, how you can become extremely efficient in terms of sampling some of that data to reduce the burden of storing the entire state, and perhaps maybe you only need to store a small subset of that state, which then leads to this interesting problem of state growth management. So L2s, while the way in which they operate is sort of fundamentally different from the L1 because of the decoupling that we discussed before, at the end of the day, the rollups themselves have a state that they need to keep track of, and the state will grow over time. It might grow slower than what you'd expect for a normal L1, but again, that sort of depends on the architecture and the operational model. But at the end of the day, they run into exactly the same state management issues as the L1 does. Basically, it becomes more difficult to sync the full history of the node because you simply have a large amount of data. So the name of the game then becomes, how do I incentivize external operators to efficiently store parts of the state and enable querying parts of the state? And how do I do so without burdening the rollup itself? Because if you need a rollup for the rollup, then we haven't really achieved very much. So instead, in your palette of resources and operations that one considers in designing a rollup, they also have to consider, how do you manage the state of the rollup so that you don't run into exactly the same problem that you would normally on the L1? And this is where the data availability problem comes into play, and ultimately the cost of verification of the validity proofs or of the fraud proofs, as well as the cost of publishing the data back to the L1, always provides a sort of ceiling for improvement, because you then rely on the L1 itself to improve in order for you to reduce those costs. So instead, you have to think about, okay, how does one improve state management on the L2 side and incentivize off-chain data availability using different types of models, volition, validium, and so on, and how that introduces coordination problems, latency problems, but also how that allows different rollup operators to bootstrap their systems from scratch. So now another topic that we touched on was how does one enhance liveness and finality on these layer 2s. And again, returning to this decoupling, we now have this interesting opportunity for different types of economic agents to come in and actually improve the liveness properties on the L2s without necessarily having to coordinate or having to participate in the day-to-day operation of the rollup. And here's what I mean by that. You can now have what I call dedicated fail-safe sequencers that are paid a small fee that is weighted towards liveness without actually processing any load day-to-day. They sort of behave as an insurance sequencer. And if you think about insurance contracts in general, you generally pay a premium for something that you hope that you will never use or never need to use. And that's interesting because in that model, you're basically paying for an agent to just sit there and do nothing. And so long as they can provide certain guarantees that in the event that something happens, that they're able to intervene, you're happy to pay that premium. These sequencers are basically being paid to be redundant and just sort of sit there. And the reason that's interesting is because you can pay these agents in a non-native token so that it's not tied to the security of the L1 in any way. The other interesting aspect is that we know, regardless of redundancy, regardless of decentralization, you can never guarantee 100% uptime. That is a real problem for L1s. But for L2s, you can also never really guarantee 100% uptime. But what you can do is actually make the net cost of downtime much lower when you use these sort of clever economics. So you can essentially socialize in the event of significant downtime, you can socialize the loss across a multiple set of insurance providers and that are willing to underwrite that process. Now, when it comes to finality, we know that it's ultimately determined by when the proofs are posted back to the L1, and then the last roll-up state that's considered to be valid is now sort of canonical and immutable. So the name of the game here becomes, how do I provide a market for finality? And that's simply determined by the transaction inclusion. And we know from a user's perspective that they can force inclusion in the L2 at the expense of some minimum cost. So assuming that they have no time preference, it is strictly cheaper for them to send their transaction to the sequencer. But in the case that they do have some time preference, they now have to weigh that against the cost of including the transaction themselves and the probabilistic guarantee by the sequencer that they're going to include the transaction. So in the same way that we discussed these issuance of these derivatives tying the performance of the sequencer to the native demand, we can also include a similar type of instrument that guarantees inclusion within n blocks or within a finite period, and these themselves could be priced. So not only can the sequencer guarantee or forecast something about their future costs and the transaction demand on the L2, the user can also, instead of using this very coarse gas scheme lever that they're normally used to using in mempools on Ethereum, they can now have an entire spectrum of inclusion guarantees, which gets us into the topic of transaction quality. And by transaction quality, I'm really referring to the spectrum between a pristine transaction, which is a single atomic transaction that is very cheap to execute and is included effective immediately, versus a series of complicated transactions that are expensive to perform and atomicity is not guaranteed. And most transactions, or most series of transactions as a subset, sort of lie somewhere in between. And again, you can now not only have a market for single transactions, you can also have a market for bundled transactions. And the reason you can have this is because you can now have these specialized sequencers that offer you these sort of services. You can have, in the case of multiple sequencers, where one of them specializes in DeFi-like transactions or in NFT-like, auction-like transactions, and so on, they can offer you these bundled services as the most market-efficient way of executing them. So you can see, just based on the discussion that we've had before, that the added benefit of having multiple sequencers is not just from a redundancy perspective, but also because vector of customizability of transactions that on the L1 were normally handled through off-chain agreements or through something like flashbots, whereas now you can have a much more general purpose, a much more robust way of doing so, and more importantly, you can price it. And so now, in an era in which applications will start to really think about how to subsidize or even eat the entirety of the gas transactions and just incorporate them as part of their P&L in order to improve user experience, they really need to be able to price not just single transactions and their latencies and atomicity, but also they need to be able to price bundles. Atomicity, of course, is sort of trivial in the case of a single transaction, but is very, very important in complex. So now that we're talking about pricing, there is one thing that I want to highlight, which is that the network fees on layer 2s fundamentally differ from those on the L1. And it's really for a very simple reason. The fundamental difference between L1 and L2 economics is that the native L1 assets command something that looks like a store of value supremacy, whereas the L2 simply does not. And the reason for that is quite simple. If you inherit the security as an L2 from the L1, you must be economically subservient. And what that means is that the security layer has to be guaranteed by an asset that is not native to the rollup. But what it does do is that it opens up the design space for off-chain data availability and other off-chain services, because now the rollup can serve as the vendor for these types of services. Which brings me to perhaps the most important question. How do these L2s, if they were to issue tokens, how does value accrue to these tokens? And more importantly, does one even need a token for a layer 2 system? And there are sort of two schools of thought. One school of thought says that simply because security is inherited from the L1, the L2 token can at best serve as a bootstrapping mechanism for the L2 ecosystem, but it is designed fundamentally so that it becomes less useful over time. Once enough activity is aggregated onto the L2 token itself, its value will sort of decay. The other school of thought is that the layer 2 itself, because it can serve as a vendor for these modular services that we described before, that it now effectively acts as the marketplace for all of these off-chain computational services. And so that can be accretive, not just to the L2 itself, but ultimately to the L1, to the extent that it enables more economic activity on the L1 than what you would nominally get without the existence of the L2. So then here the question becomes, can a layer 2 justify the existence of a token, not just purely based on the mechanics of running the rollup, but instead, can it offer value to the L1 that wouldn't exist otherwise? And with that, I will leave you with some open questions. And again, it was an absolute pleasure to be here. If you do have any comments or questions about anything that I discussed here, as well as these open questions, obviously, please do reach out. Thanks again.
Hello, everyone. So far, I hope you enjoy all the sessions around my sort of rollup and share sequencing, restaking. Meanwhile, also the economics around the RaaS systems. And I'm Yaoqi. Today, I'm glad to share a little bit about what we've done for the past 1.5 years to really help to connect multiple rollups and try to build something, I would say, brand new for this rollup space. We call Beacon Layer. Basically, it's an enshrined rollup interlayer for Ethereum and other chains. So as we go into this enshrined rollup, right, we need to talk about like sort of what are the existing rollup categories we have. So one is we call smart contract rollup or classical rollups, right? Like Arbitrum, Optimism, and the various ZK rollups like Polygon, ZK EVM, and ZK Sync. So for these rollups, right, we have sort of a sequencer network right now, mostly single sequencer. But at the same time, since we say it's a rollup, basically we derive the security from the L1, typically Ethereum, right? So we also place smart contracts like validity proof or fraud proof contracts and also bridge contracts on the L1 to allow user deposit and withdraw assets. And meanwhile, as we can see, right, most of these rollups, we also post the data, typically the comprised transaction data, to the L1 to make sure this data available on the L1. So later, if some users or people want to challenge the existing sequencers, right, so they can just download data and just do the verification on it. And beyond that, recently we also got a lot of progress from this Celestia and this sovereign rollup side. So compared to this classic rollup, right, basically we derive security from the Ethereum or the L1s, and also do all the DA and the verification on the L1. For sovereign rollup, typically like this Romint and Sovereign Labs. So what they do is like they have a separate sequencer network, and all the sequencing and the verification are done by the sequencer network. And beyond that, they also post the data to a typical DA layer like Celestia DA or the EigenDA. And in contrast to doing all the proof on Ethereum and on the L1, and also the bridge contract on the L1, for the sovereign rollup, basically you have more sovereignty. So you can have your own sequencer network, but at the same time, you don't really derive the security from a dedicated L1. So basically, you have the sovereignty to really handle all the staking and sequencing by your sequencer network. Meanwhile, you can also rely on different bridge providers. Probably some of them will give talks later this conference. And as you can see, right, classic rollup mainly depend on security from the L1s. And for sovereign rollup, we have more freedom to run the nodes and the sequencers and posting the data to a dedicated DA. And compared to the existing, these kind of two types of rollup, right, there's another new type recently being discussed a lot by Ethereum community. It's about insurance rollup. Compared to all the two types of rollup, right, for the insurance rollup, it's to another like sort of extreme. As we all know for Ethereum, right, the future for Ethereum scaling is really about this rollup-centric scaling approach. So in that case, as we can imagine for the next few years, once the rollups become more and more mature, so we can see Ethereum becomes the main settlement layer for all different rollups and applications. So that means you can issue tokens and transfer assets on Ethereum. And at the same time, Ethereum will also become the sort of the go-to DA platform. So for all the rollups, you post the data on the Ethereum, and Ethereum will host the data. So right now, for most of the existing rollups, like the classic rollup, we still place the smart contract for fraud proof and validity proof and bridges on Ethereum. So in that case, as we all know, right, since it's a smart contract, almost can be controlled by multi-sig wallet, right? So in that case, the security actually really derived from the multi-sig wallet operated by the developers of different rollup teams. To enhance or improve the situation, as I just mentioned, right, for the classic rollup, and some researchers propose the insurance rollup way. So in that case, as we just mentioned, right, for the verification logic, like fraud proof or the validity proof, and also bridge logic, previously they are in this smart contract. But in insurance rollup, we embed this logic into protocol. So in that case, as you can see, right, in the future for Ethereum, if we have hundreds of rollups, right, for this rollup, we can still have the execution in different sequencers, but regarding the proof verification and the settlement and also bridging logic, it can be in the Ethereum protocol. So in that case, for any major upgrade for each rollup, right, probably we require the Ethereum to do some soft or hard fork. So the benefits we can have, as I just mentioned, right, basically we can further enhance the security from like this smart contract security to the protocol security. For the attacker, if you want to compromise one insurance rollup, right, you have to compromise the protocol level, like this Ethereum protocol level. So it's super, super difficult compared to just need to target attack a bunch of multi-sig wallet holders, right? On the other side, right, since we can move sort of the logic from the smart contract to the protocol, sometimes we can use precompile, or even we implement at the protocol level with RaaS or Code. In that case, we can massively enhance the performance for handling this verification or bridging logic for the existing or the future rollups. In that case, as you can see from this diagram, right, user can send a transaction to the execution client. The client can be run either by Ethereum existing validators or by some other validators. But for the rollup block and the consensus client, they will be handled by the Ethereum validator. So in that case, we can really improve the security guarantee for all the rollups and also improve the performance for verification of these rollups. And meanwhile, for upgrade, right? Previously, typically we do something like we snapshot or the option voting or governance mechanism, right? People do this option voting, and if the proposal passes, and we can upgrade the version, for example, from 0.1 to version 0.2. But in the end, it's still a developer need to execute the proposal, right? By upgrade the smart contract on chain with his own admin key, or basically signed by some multi-sig wallet. Without the insurance approach, as you can see, right, it's a little bit dangerous since in the end, it's sort of controlled by the multi-sig wallet. But once we put into protocol level, and then we can light the protocol, I mean, all the users can directly vote via their sort of Ethereum level governance, right? So we can have a better security guarantee for the upgrade. But as we can see, right, there's so many benefits and advantages for insurance rollup, but why it's not that popular? I think the main sort of reason is that it's requiring the protocol changes. As I just mentioned, right, either for the sort of the logic implementation for the verification, or for the bridging, or even for the upgrading, right? Right now, mostly at the smart contract level, but once we move it into protocol level, right, it requires a lot of changes on the validators and also the sometimes a consensus protocol. So it's sort of like a major refactoring of the existing L1 protocol. And meanwhile, it's sort of like we push this L2's responsibility to the L1. So if someone remember Vitalik previously posted this post, right? So he's saying that I don't overload Ethereum consensus. So sometimes, like if we push too much logic into protocol, right, then the protocol, I mean the L1 protocol itself has to make the decision for your L2 or rollup protocols. In that case, it's sort of like we need to find a sweet spot or balance to really sort of have the good position between the rollups and L1s. If we put a lot of logic back to the L1 protocol level, and then it becomes a big burden. But at the same time, if we can offload some of the logic to the L1 without sort of challenging too much on the performance of Ethereum protocol, then it's also good, right? Because we can achieve better security and performance compared to the existing smart contract implementation. So since it's a little bit tough to modify the existing L1, but as I just mentioned, right, there are so many benefits to adopt this kind of insurance rollup approach. Since AltLayer, as you guys all know, right, we launched a lot of rollups, and the users can directly via our dashboard to launch your rollup yourself. So we need to manage this rollup. And on the back end, we have these automation tools and infrastructure to automate the entire process. But at the same time, we want to provide the best security and also the best performance for all these rollup. Since the L1 doesn't really provide the insurance rollup implementation at the moment, so we come up with the beacon layer. So as you can see, right, beacon layer, you can treat it as an interlayer, basically between the L1 and also the rollups. So beacon layer will help to provide all the benefits we just mentioned, right? The decentralized sequencing verification, upgrade, and also further with some social governance, cross rollup messaging via this beacon layer. So you can treat it as a really orchestration layer for the rollups. And the rollups will be all enshrined to beacon layer, but at the same time, we still derive security from Ethereum because all the fraud-proof bridging and all things still be deployed on the Ethereum. It's just like a beacon layer is sort of the way for you to do a double check and as an augmentation or instrumentation layer to provide further security guarantee and also further decentralization for different rollup systems. And we just know why we need this sort of a beacon layer, right? It's sort of like we want to have all the benefits provided by the insurance rollup, but at the same time, since L1s are not that ready, also we can have this interlayer to provide these benefits for the rollups at this moment. So what are the parts the AltLayer beacon layer can provide at the moment? The first thing is about decentralized sequencing. As we all know, right now, for all the optimistic rollups or ZK rollups, especially ZK EVMs, we are still adopting the single sequencer approach to really provide better performance and fast improvement on the existing development. In that case, we may have a bunch of drawbacks, right? As some people posted comments on various forums, like if it's still a single sequencer, it can censor user transactions. And sometimes, like, right, due to the massive participants from the community for airdrops or sort of these claims, sometimes we overwhelm the single sequencer and there will be downtime for the L2s or rollups. So then the sequencer becomes a single point failure. And beyond that, even we can say that right now, most of the sequencer run by the team, right? The team doesn't really have the incentives to basically run user transactions. But there is still a potential, like in the future, this sequencer can have the ability to front run or create bad MEV against the users. So what we provide via the beacon layer, the first thing is about decentralized sequencing. So we already have the multi sequencers for the rollup. So that means either via dashboard, and you can quickly spin off a number of sequencers for your rollup. So in that case, we can immediately avoid the single point failure, right? So since you have a lot of we don't say backup nodes, but it's just like you have a lot of alternative sequencers. Like one is done, you still have a bunch of them can really help you to produce the blocks and verify the transactions. And beyond that, since you have multiple sequencers and for the users, they have more choices to send the transactions. And in that case, somehow we can mitigate these kind of MEV issues. Beyond that, right, we, as we all know, like for rollups, we have a sequencer, also have the verification that basically before posting data to the underlying layer L1. With a beacon layer, right, since a lot of applications actually rely on some soft finality from the sequencer. For example, for most of the rollup, right, we finalize blocks within 2 seconds for soft finality. Basically, the sequencer generates the block within 2 seconds. But beyond that, we also have another finality called hard finality. The nodes, typical verifier or the prover need to post these comprised data to the L1. And then at that time, it's sort of we say hard finality, and some application can confirm the transaction on the L2 side. But for a lot of bridges application, right, also some middleware, they want to have a soft finality, but at the same time with a better confidence. So in that case, they need to run sequencer verifiers themselves to quickly verify whether the transaction blocks are correct or not. So in that case, as you can see, right, a lot of bridges to provide this fast liquidity across different rollups, so they have to run a lot of infrastructure nodes. And meanwhile, right, for a lot of exchanges, they also need to make sure the transaction blocks are correct before they confirm the user transfer across different rollups or across the rollup to the exchange server. On our side, right, as you can see, with the beacon layer, it's a relatively decentralized layer to do this verification before basically the verifier posts this data back to the L1. So you can really get a more confirmed finality from the beacon layer instead of running a dedicated sort of a node to do the verification yourself. So in that case, with this decentralized verification feature provided by beacon layer, right? So the applications or some middlewares, they can further reduce the cost of running dedicated nodes for a dedicated rollup. And beyond that, since all the rollups are opt-in for the enshrined to beacon layer, so as you can see, right, with the decentralized sequencing and verification, all the rollups actually can have some finality on the beacon layer before we have the finality on the L1. So in that case, for some application, they require this cross rollup messaging or cross rollup like this asset transfer. They can also rely on the beacon layer to give them some soft commitment before they really finalize their transactional data on the L1. So in that case, as you can see, right, the beacon layer can behave as a role to really help to interoperate across different rollups. So in that case, we can say it's sort of like we make sure the message across different rollup can be atomic, which means like when rollup A is the message rollup B, if the beacon layer pass the message and confirm the very beacon layer. So in that case, you can treat it sort of like finalized across these rollups. So it further helps different rollups to do quick messaging across each other. With a bunch of these nice features and benefits, we can achieve via beacon layer as this enshrined rollup interlayer. What kind of rollup architecture we have for the current AltLayer? As you can see from this diagram, right, we have a well-structured sort of structure compared to other rollups, or because we sort of provide this rollup for a lot of applications like games, NFT, and social applications. So they really need this structure as robust as possible. So as you can see, right before the sequencer, we have this aggregator. Actually, it behaves like a load balancer to handle massive traffic. Previously, we did some NFT mint. We got like over 30 or even 50,000 participants. We need to scale this aggregator or load balancer elastically to really handle these users before they crash down our sequencer. So in that case, the aggregator is a must. And after that, it's a normal producer sequencer to precise transaction, right? And after that, as I just mentioned, we also have this verifier system. But the cool part that the verifier is sort of like in the WASM block. So people can run it either in a PC, laptop, or server, and sometimes you can even run in your browser as a light client. So in that case, for a lot of applications, if you really want to make sure your transaction to be verified as early as possible, right? You can just embed this verifier into your application on the website. So when users send transaction, it can quickly verify all the transaction from the user side. And beyond that, I just mentioned, right, all the things approving system are still on the L1, but at the same time, we also have the extra security guarantee from the beacon layer. So regarding the typical precise to set up a rollup, And user can just send a request either via our dashboard or in the future via our public API to the backend. Of course, you don't really interact directly with the beacon layer. Typically, some RPC endpoint. And you send the request to beacon layer. Beacon layer will set up this dedicated rollup for you. It's quite customized. Like you can specify your DA, you can specify your L1. You can also specify a bunch of parameters you want, like block time and also the gas limit per block. After that, the beacon layer as a decentralized infrastructure, it will select some of the top reputation like nodes as sequencers for the rollup as the as sort of the first set of sequencers to service the user. And all these things will happen in the backend. Users or developer won't see it. It's just like the entire protocol is as decentralized as possible. And typically, as I just showed you, right, for the finality side, for most of the rollups, right, we have this soft finality and also this hard finality. Soft finality for the when the sort of sequencers finalize the block on the sequencer network itself, and the hard finality basically finalize when the verifier or this submitter or prover submit the comprised transaction data to the L1. And with the augmented, with being augmented by the beacon layer, right? We have this beacon layer to do extra verification for all the rollups. As you can see, apart from this soft finality and also hard finality, the beacon layer will do another verification called a proof of validity verification. You can treat it as this one-shot fraud proof, because as we all know, right now for most of the proof, it's a step-by-step proof with the bisection. But here, the beacon layer is strong enough to directly precise the proof for the entire period of time, period of challenge time, like basically for the verification. So in that case, you can treat it as a canary detection. When the sequencer generates blocks and before these blocks are submitted to the L1, and the beacon layer will do the extra verification and detect whether these blocks are correct or not. So that's why we call it canary detection. And once the beacon layer finds that, okay, your block is not valid, and the beacon layer will signal the challenger to do the challenge to the L1 much earlier than like this 7-day challenge period, or it can just happen within a few seconds. So in that case, as a canary detection, right, the beacon layer can quickly do the verification and further secure this security guarantee for the L2, but at the same time signal the challengers to do the challenge as early as possible. As a summary, right, compared to the existing L2 or rollup solutions, right, there these beacon layer, as you can see, we have like sort of two more lines of defense for the security guarantee. The first one, as you all know, right, if it's a single sequencer, then the soft finality will be a little bit weak. But since we run multiple sequencers, then soft finality at least much stronger than a single sequencer. That's called stage one, the execution level soft finality. Beyond that, as I just showed you, right, we have the beacon layer to do this canary detection for all the rollups where these proof of validity checks. So in that case, if all the checks pass, that means at the verification level, we are sort of quite secure. And for a lot of application and bridges exchange, they sort of can trust this level because a decentralized verification layer for them. And of course, on the stage 3, it's a typical hard finality. We also have basically we implemented all the verification in Solidity for the WASM instructions. So all the proof and execution for the blocks and transactions can be verified on the L1 if there's a challenge happens. And beyond that, beyond this decentralized sequencing verification, and also this message passing, right? We also have this staking and the slashing for the sequencers and verifiers. As you know, right? Once we have multiple sequencer verifiers and also the proof, sometimes we need to know who behaves good, who behaves on the good manner, and who behaves wrongly. In that case, we need to apply this penalty mechanism. It's called staking and slashing. So you can either do the staking slashing on the beacon layer, which is in an enshrined way, and you don't need to deploy smart contract. And, it's highly sort of secure with beacon layer. Or you can also do it on the L1 side, where the smart contract we already deployed for these different rollups. And beyond that, right, as we just mentioned at the beginning, the upgrading is very important, because we don't want the smart contract to be upgraded by a single admin address, right? So in that case, beacon layer will also handle the upgrade for you. So when you can let the community do the on-chain voting on beacon layer, and if the proposal is passed, and then we can sort of pass over the WASM binary basically for the next upgrade, where the beacon layer push to different rollups. That's how we really handle and manage multiple rollups and for their security batches, and also this upgrade for some major features. So everything is automatic via the beacon layer and push to different rollups. And meanwhile, you can also arrange like some on-chain governance beyond this upgrade. And since it's fully on-chain, you can just get all the traces for the votes, and everything is transparent. So as I share so much about this beacon layer, right, as the enshrined rollup interlayer for Ethereum, and in the future probably for multi chains, the end goal is really to provide the best security guarantee and also decentralization for the rollups as much as possible. For a lot of these customers and projects who embrace the Web3 as the future. So right now, what are the stuff you can do in the community? So you can participate in our beacon layer staking, and also this rollup staking. As I just mentioned, right, these features are quite advanced. You can just try it out right now. And meanwhile, you can also interact with this decentralized sequencing rollup. And we already run a bunch of these sequencers for the rollup and with proper proof. And beyond that, what you can expect to come soon. One is like soon you can start to use the Docker and some other tool to join our beacon layer via the no joining like page. And later on, you can also try out to do some challenge to these like sort of rollups set up by us or by some community members. And meanwhile, the RaaS dashboard will also support this persistent flash layer, and as Amrit and Ed just mentioned, right, the Arbitrum Orbit is also integrated into our RaaS platform very soon. And meanwhile, there's another very big partnership announcement coming soon, and just stay tuned. Yeah, thank you for your time, and hope you really enjoy this new concept of beacon layer. And meanwhile, hope you really enjoy your future sessions in today's conference. Thank you.
Hey. Hi, everyone. Nice to be here on AltLayer's Rollup-as-a-Service Day. Yeah, so hey, everyone. My name is Arnold, and I'm a full-time research analyst at The Block. So today I'll be giving a very short presentation about the overview of the rollup landscape.
So a quick introduction of myself, right? I'm a full-time research analyst at the blog, and I focus mainly on researching about blockchain scaling solutions. I have a background in chemical engineering at the Nanyang Technological University in Singapore. And for those of you who are interested, you can reach me via email, if you have any questions or you would just like to simply connect. So on today's agenda, we are going to start with a recap on rollups, which I think is something that most of you guys in the audience would already know. But because of the divergence in the rollup landscape, I think it is a great time to just go back to the definitions and how we classify them. And then I'll move on to the current state of rollups, where I cover a handful of relevant metrics before ending off with the future of rollups, where I give my opinions on how I think rollups might develop in the future. So without further ado, we can begin with a recap on rollups. So I said earlier that we should define what a rollup is, because I think the idea of a rollup is starting to be used as a common buzzword in the scaling domain. But a rollup at its core, right, should at the very least be able to abstract computation from the base layer while simultaneously deriving its security from that very same layer. And as we begin to see variations of rollups ranging from data availability modes to enshrined rollups, and even rollups as a service software starting to appear, I think it is important to remember the necessary features that rollups are supposed to have. There are two main types of rollups, right? Optimistic and zero-knowledge rollups, which uses fraud proofs and validity proofs, respectively. They are to be submitted on the base layer for them to be counted as a rollup, right? So with that, aside, this table here shows a quick overview of the existing rollups in the space today and how we can classify them. So, the top half, we have what we define as a traditional rollup, right, which are solutions that use on-chain data availability. And then we also start to see more varieties, more alternatives, such as Validiums and plasma chains that, they are commonly referred together as layer 2s together with rollups. But Validiums and plasma chains, they actually use off-chain data availability. So, with the whole concept of data availability abstraction coming in, it has kind of blurred the lines for layer 2 solutions. But I think this table pretty much sums it up, gives the clarity that we need on how we can define and differentiate the different scaling solutions today. So moving on to the main part of the presentation, we're going to be looking at the current state of rollups. We start off first by looking at the total value locked, or TVL, of rollups today. And I think one of the encouraging signs of growth in the rollup space is the fact that TVL has actually increased over 114% amidst the bear markets over the past 6 months, where it actually grew from 4.1 billion in TVL to up to 8.8 billion. However, we should know that part of this surge was actually due to the Arbitrum airdrop, as can be seen by the sharp uptick in March, right after the Arbitrum airdrop its token, right? Another interesting fact about the TVL here is that 86% of all TVLs across rollups are actually found on optimistic rollups. And this can actually be attributed, namely to the ease of deployment, as well as the convenience of the user experience on optimistic rollups, and that can onboard and retain users a lot more effectively than ZK rollups. Additionally, we also know that the 4 optimistic rollups, as seen in the previous slide, they actually have launched their own native tokens to incentivize liquidity in their own respective ecosystem. So naturally, this helps them capture a larger market share of the entire rollup domain. Now, if we were to look at the daily number of transactions on rollups, because it provides a proxy for the adoption, we notice that it has actually grown by over 153% over the past 6 months, comparatively to the number of transactions on Ethereum, which has only grown by 44%. This means to say, that rollups are actually starting to account for more on-chain activity than on Ethereum. And one of the really encouraging signs here is the fact that optimistic rollups are now processing more daily transactions combined than Ethereum, at least over the past 3 months, ever since the Arbitrum airdrop. And although this figure has fallen off since the airdrop height, I would say that generally rollups are still showing signs of gaining significant traction in terms of adoption, because we can see that although the hype has passed, the overall transaction growth is still generally on a slight uptrend, especially for both optimistic rollups and ZK rollups. So the next metric here that is highly relevant is the amount of gas, right, that rollups consume, because essentially the gas that they consume is an indicator of how much block space that they are actually taking up on Ethereum, right? So as adoption on rollups increase, we should also see a corresponding increase in the gas consumption on Ethereum. And I think, from the charts here, we can see that, both optimistic rollups and ZK rollups, they consume comparable magnitudes of gas. And that is pretty peculiar, namely because ZK rollups are, touted to scale Ethereum a lot more efficiently than optimistic rollups, right? So, where is the advantage here? It should be noted, right, that this advantage that ZK rollups have over optimistic rollups is only really significant at high transaction volumes, which is not really present today, right? Because ZK rollups only start to show that kind of scaling when there are more transactions being compressed into a single proof. But at low transaction volumes, the main bulk of the gas consumption actually comes from the transaction data, right? So in March, we can see that there's actually a huge spike in the gas consumed by ZK rollups. This is partly due to the Sybil activity on rollups such as ZK rollups, such as Starknet and ZK Sync Era, which have yet to launch a token. And a lot of these Sybil actors are, going to these rollups because they are transacting on them in expectation of a potential airdrop in the future, right? And from the chart, we can see that validiums, on the other hand, consume far less gas than both types of rollups. So validium is a type of scaling solution that uses off-chain data availability. And this also demonstrates, right, the impact of hosting transaction data on-chain on a rollup's gas consumption. And that, I think, is why we're starting to see a market for alternative data solutions. And the next metric here that I think would interest some of the viewers is the revenue of optimistic rollups. The reason why we're looking at revenue of optimistic rollups here is because the revenue for them is public data, so it's much easier to get an accurate account of this data. And here we can see, optimistic rollups are generating millions in revenue every month, right? Just so you know, this revenue is calculated by taking the amount of gas expenditure that is spent on the layer 2, right? We see Arbitrum and Optimism generating over 4.6 and 2.7 million in average monthly revenue. And these figures are continuing to trend upwards even after the Arbitrum airdrop in March, even after the recent Optimism token unlock, and even amidst the overall bearish crypto market sentiment. Right, so this actually indicates the relative independence for the demand of rollup block space with respect to the general crypto markets. Something that is interesting here would be the fact that both Metis and Boba, they appear to have fallen off and they're diverging in terms of their growth trends. And this shows how optimistic rollups, even though they offer similar user experience, similar services, but they are not all the same, right? And there are various factors that can account for this, such as first mover advantage, trade-offs in security, as well as the depth of liquidity in the ecosystem, which can significantly impact the adoption, right? Basically, launching a rollup doesn't guarantee that you will find adoption, right? it's starting to seem like almost like it's like a winner takes all kind of situation. But obviously, this can change over time. And this slide is just counting for the gas that is paid by rollups on Ethereum, right, for posting batches of transaction and transaction data. And we can see that most rollups are still profitable, including Boba and Metis, right? We see Optimism and Arbitrum generating 2.7 and 4.5 million in average monthly profits, right? And Boba and Metis are also relatively profitable. Obviously, this analysis isn't perfect because it neglects the cost of running a sequencer node, which may or may not be trivial. But these profits are also calculated in US dollars, whereas the actual currency being used is Ether, which means to say that these profits can fluctuate depending on when they choose to sell the Ether for US dollars. Right. And then we're going to move to the third and final segment of the presentation, where I give my opinion on where we might see the future of rollups gravitate towards. I think the first notable development here would be data availability abstraction, right? It's a pretty hot topic that has been talked about. We see solutions such as Celestia, Avail, previously known as Polygon Avail, right? As well as Arbitrum, Anytrust, starting to surface and see certain levels of adoption, right? These solutions offer an alternative environment for transaction data to be posted, right? Both Celestia and Avail, they are data availability layers, independent data availability layers, and they use data availability sampling to guarantee that blocks data is posted on is made available, right? With just a fraction of the said data being posted on chain. So effectively, what they do is that they reduce the amount of data that has to be posted on chain, and therefore it should reduce the amount of cost that a rollup incurs for posting the data on Ethereum. And then we have Arbitrum Anytrust, which basically uses a fallback mechanism, where it stores data off-chain that is secured by a data availability committee. And if the committee fails, the Anytrust chain will just resort to posting the transaction data on Ethereum like a normal optimistic rollups would, right? So these are some of the solutions that we're starting to see to address, the high cost of posting transaction data on Ethereum. And then the next unique development that I think would be the evolution of Rollups-as-a-Service, or RaaS for short, right? We have AltLayer, the host of today's event, as well as Caldera and Slush, being their own RaaS in their own terms. They each of them have their own unique focus and their unique features. So firstly, we talk about AltLayer, which I think one of the unique feature that they have is the flash layer feature, right? Where a developer can easily spin up a rollup to perform one-off activities such as an NFT mint before settling back on Ethereum or another layer that AltLayer might support. This is significant because it can reduce the stress of ad hoc events, right? Because we've seen how gas spikes when there's a popular NFT mint on Ethereum, right? And that can affect the experience for all other Ethereum users, not just the NFT minters. So having a flash layer that takes away this ad hoc demand can certainly reduce the stress on the base layer. Then we have Caldera. Caldera's focus is mainly to spin up rollups with alternative VMs, virtual machines, before settling them on EVM chains. So this should improve the accessibility for developers to build on EVM chains, because they can spin up their own preferred VMs as a rollup and then settle the outcome of that rollup on an underlying EVM chain. So this once again should bring about scalability for not only Ethereum but other EVM chains as well. We also have Slash SDK, which actually allows developers to spin up layer 3s on Starknet. And I should note that while this isn't exactly like a rollup, the idea behind spinning up an additional layer easily or conveniently does make it analogous to RaaS software. And I think the main point of all of this rollups as a service is to abstract the complexity of launching a rollup and make it more accessible for both developers as well as users to access rollup block space that is much cheaper than the block space on Ethereum. So I think here is a certainty that like rollups as a service have a huge potential to scale Ethereum in the future. And the last notable development here would be rollups building on other blockchains, right? We have Alpen Labs, which is trying to build like ZK rollups on Bitcoin. We have Dimension, which is rollup as a service platform as well, that is building rollups on Cosmos. And then we have Tezos with their own Enshrine rollups, right? So we start off with the Bitcoin ZK rollups, right? One of the challenges that they face right now is, the fact that Bitcoin lacks a lot of expressibility in terms of their programming language script. Also, Alpen is currently building in stealth, so there isn't really much information on their progress, but it is something to keep an eye out for, that Bitcoin may one day see rollups of its own. Then we have Dimension on Cosmos, which is, as I said, like a RaaS solution, but its main focus, unlike the previous RaaS that were covered, is more on interoperability. So it's meant to make like rollups speak to each other more easily to facilitate that cross-chain or cross-rollup interactions, right? Then Tezos have their own like Enshrine rollups, which basically means that the rollups are enshrined within Tezos itself. So they don't actually need to have like additional like layer to scale it. And this allows the Enshrine rollup to scale Tezos without needing to sacrifice a lot of security. Or basically it's inheriting all of Tezos security. And while these solutions don't necessarily scale Ethereum, I think they are highly relevant to understand and keep an eye out for, because they can provide a clue or valuable insights as to how the rollup landscape can develop on Ethereum. So that is something that is worth keeping an eye out for. Right, so just onto the closing remarks. I'm not too sure if there's been too much content, but like there are three main takeaways here, right? I think if you are to leave this presentation, the three main takeaways. Firstly, rollups, they are becoming an integral and inescapable aspect to scale Ethereum, right? We see more transactions on rollups combined than on Ethereum over the past 5 months. And this trend is, could continue, especially if the bull market returns and Ethereum becomes highly costly to use. Number two, rollups can be very profitable, right? We see optimistic rollups alone generating over 8.5 in aggregate monthly revenue. And this is just optimistic rollups, much less to say if we talk about ZK rollups or even Validiums, which have very low cost. I think scaling Ethereum is not only in the interest of the Ethereum community, but like those who scale Ethereum can stand to gain as well. And the third and final point is that the landscape for improving and enhancing rollups is very vibrant and it's diverging, right? We're seeing a myriad of solutions starting to appear, ranging from data availability, rollups as a service, and rollups on other blockchains becoming increasingly common. And this will all add to the diversity of solutions that we will see that will scale blockchains in the future. So with that, I think the overview of the rollup landscape, in short, is just full of activity, and this is amidst the DAO bear market. So I think that when the bull market comes back, it will be very interesting to see how all of these rollups continue to develop, how the technology will continue to grow, and more importantly, for those people growing the technology, what it means for their transaction costs, as well as those running the rollups, what it means for them to be a profitable business. So I do think that this is a very robust ecosystem that is ready for the bull market. And with that, I thank you for your time. And if you have any questions, you can reach me via my email or on Twitter. And I hope that my presentation was insightful and valuable to all of you out there. Thank you.
Hello everyone, I'm Julian Ma. I'm a researcher at the Robust Incentive Group within the Ethereum Foundation. We usually look at mechanism design for the Ethereum protocol, so think of problems like ERP 1559 and proposer builder separation. And today I'd like to talk about Ethereum's role in the cross-domain world. First of all, I would also like to thank AltLayer for hosting this session, and I hope it will be very informative. So if I'm thinking about Ethereum's role in the cross-domain world, the first thing that pops up to me is how proposer-builder separation is really a design philosophy and not necessarily what we think of it in its current form. So many of you will probably know its current form of MEV Boost, which is the out-of-protocol software that Flashbots developed and is currently used by large sets of the validator set, and it allows proposers to connect to builders who build the entire blocks, and then proposers reap the benefits of this. So it allows everyone to get the same benefits of sophistication. However, proposer builder separation is actually way broader than this. In general, it allows any outsourcing of protocol duties that proposers may have to third parties in order to fulfill these duties. So in essence, PBS, or proposer builder separation, means that a proposer who is tasked to perform certain duties by the Ethereum protocol may have a desire to outsource some of these duties for whatever reason this may be. So in the case of block construction, this might be because constructing a good block is very intensive work and it requires a high degree of sophistication. So what the proposer could do is they could draft up a contract that outsources this job to a builder, and where we see a builder as an out-of-protocol agent that's sophisticated and rational and has the ability to fulfill this job well. And then PBS really refers to the formation of this contract. So in MEV Boost, it may be that the contract has the form that the builder makes the entire block, but as we'll see throughout this presentation, and we've seen in the literature, there could actually be different forms of this contract. So as a quick recap to get everyone on the same floor, so where are we now? MEV Boost is the current out-of-protocol instantiation of PBS, so it's not actually proposer builder separation. Proposer builder separation or enshrined PBS is something that we're working towards. MEV Boost allows proposers to outsource block construction to builders, as we've just seen through this contract, and thereby gives all of the proposers the same access to sophistication. So this ensures that there's still decentralization of the validator set, because there's no incentive to co-locate with searchers or with builders, as we would have probably seen otherwise. However, it does come with a few challenges. For example, there are lots of trusted components now in MEV Boost, meaning that there could be some liveness issues or unbundling attacks like we've seen. And in the process of MEV Boost, they define a very rigid contract, which is the block auction. So as I just stated, the MEV Boost says that a builder can make an entire block for a proposer. So they don't give you the option, for example, to build half a block, to build blocks in different ways. They define a very solid footing for what the form of this contract must be. And then a logical question to ask is if this is the optimal form of the contract. This is something that we'll explore further in this talk. The idea about whether this is the perfect form for the format or not comes from Barnaby. He's the team lead at the Robust Incentives Group, and I've linked his post in the bottom left corner of the slides here. I'll also share the slides afterwards, and these are actually clickable. So if you're interested in any of the links here, you can click on the slides and go through the links yourself. So the idea that there may be a different format of the contract that might be more ideal for certain situations is referred to as the allocation mechanism of PBS. So what the allocation mechanism means is that the protocol facilitates certain proposer commitments. So for example, in the case of mevboost, mevboost facilitates that proposers commit that a builder can build the entire block. If we were to enshrine PBS, the Ethereum protocol would facilitate this commitment, but there could be other commitments. And then there's the market structure, which means that the proposed protocol provides safety guarantees around this commitment. So for example, that the proposer will honor this commitment, and also that the payments from, for example, the builder are enforced. Some other forms that could be interesting for PBS are actually related to cross-domain MEV. So what form of the proposer builder separation contract would be the best for a cross-domain world? This is what we'll be looking at as a protocol designer. So first of all, we need to consider whether this is even the protocol's concern. Putting stuff into the protocol is quite a heavy-duty task. It will take a lot of time, and once it's in, it's very difficult to change. So the protocol is a very rigid mechanism, and it's not easy to change. And also, it doesn't have a view of a lot of things. For example, currently, it doesn't see what the block production process is like. This is also the reason why mevboost exists, because the Ethereum protocol currently doesn't see how blocks are constructed. It's possible that proposers outsource this task to builders, and the protocol isn't aware of many other things. For example, the protocol isn't aware of what the state is on other domains, or whether there's even coordination between these kind of domains. And the question is whether the protocol should be aware of all of these things or not. An advantage of being aware means that there's less likely to be a principal agent problem. For example, in the case of where the principal, in this case the protocol, does not align with the incentives of the agents. So let's say that the agents are not aligned with decentralization or other factors like this. But an advantage of the protocol not being aware is that there could be out-of-protocol software spun up that would allow for coordination mechanisms. So we see a lot of experimentation in this field, and this is probably where other talks will be centered around today. Another question that we're concerned with within the EF is whether these kind of solutions should be enshrined or not, and also what the options are. So this is something that we'll go through. So why would cross-domain coordination mechanisms be a concern for the Ethereum protocol? Well, I'd like to define three things that I see as important. First of which is allocative efficiency. And with this I mean that is block space used to reach the social welfare maximizing state? For example, we could see that if we're not aware of any coordination of any coordination between domains, it could be that we use state in a way that doesn't optimize for what could have happened if we had the right coordination mechanisms. Which brings me to point 2. Are there actually applications that could benefit from cross-domain coordination mechanisms that we currently do not have? And my third point is informational efficiency. Informational efficiency refers to whether all available information is incorporated into the protocol or not. This is a somewhat softer point. So for example, you could see in arbitrage between a centralized exchange like Binance and a decentralized exchange like Uniswap, we could ask the question whether all of the information about price movements or about tokens in general is incorporated into the decentralized exchange or not. And this would probably mean some more effective use for users because they would be trading at the price where all information is incorporated and not at some more outdated price. Okay. And then a side question for this is can we achieve the same level of allocative efficiency, of coordination and informational efficiency if the solutions are out of protocol and if they're in protocol? We'll start with soft pre-confirmations, which is an out-of-protocol solution. And you can see again that this is a hyperlink, so you can click on it and it will redirect you to a slideshow by Alex Stokes, who has thought about this a lot. So soft pre-confirmations are an example of builder services, which means that a builder provides a trusted service to users to guarantee certain things. So in the case of pre-confirmations, they could either guarantee that your transaction will be included, maybe in a certain range of blocks, maybe in the next block that they win, or whatever inclusion guarantee that they're willing to sell, and a user is willing to buy, of course. And moreover, a stronger form of soft pre-commitments could be that they would give you a confirmation on the post-state of your transaction. So they could give you, for example, exactly how much balance you have of ETH and of some other tokens after this transaction. These could be very helpful things because it would allow you to act on this information, act on the fact that you know something is going to happen or not. The only problem, though, is that these soft pre-confirmations are based on a fact of, given that the builder wins the PBS auction, they will honor their commitments. So it could very well be the case that the builder doesn't win the PBS auction. And to prevent this, a user would actually want a guarantee, would need to go to multiple builders and buy these sort of pre-confirmations to get guarantees. And this may be this might need a coordination mechanism in itself, and could be very centralizing actually. So we might need something that goes beyond this. The advantage of having such a pre-confirmation, though, is that it allows users to act with this guarantee on other domains, and we'll see this power with an example later on. And then something that I'm very excited about is slot auctions, which is an enshrined version, which could also yield some pre-confirmations, basically. And again, this is a clickable link. So we've seen that the MEV boost mechanism determines a contract form where you can sell the entire block and people bid based on their block. So this is what we see on the left hand side. We see a block auction and builders, they bid and their bid is for this specific block. So the builder has built the block already, and if they win, this block will be included. A slot auction is slightly different from this in the sense that builders bid, but they don't necessarily build the block in advance. They would probably make some estimates of the value and bid based on this, but it could be the case that they would actually only build their block after they know they won. So this is a different form of the contract that we've seen, which is the essence of PBS, and this is also why PBS is really a design philosophy. Slot auctions fall into the allocation mechanism of PBS, and so they're quite different from block auctions. Again, for more depth, I would recommend you to click on the link here. Some of the consequences of slot auctions are that the difference between the commitment time and the execution time, which is the commitment time refers to the time at which you made your block. So, for example, in the block auctions part, we saw that the block was already made at the time of the bid, and the execution time refers to the time when the block is published. So now, because the auction has to happen between the time of commitment and the time of execution in a block auction, there's a large gap between this. And if the auction happens before this and your commitment time and execution time are then very, very close. And the obvious benefit of this is latency reductions. So we see now that in arbitrage between centralized exchanges and decentralized exchanges, latency becomes very important. And we've observed this in high frequency trading in traditional finance as well, obviously. This is one of the obvious advantages of slot auctions, but another maybe more subtle advantage is that block content can now be made conditional on guarantee of inclusion. So intuitively, this doesn't seem to make very much sense. So in principle, you always make your block contents conditional on inclusion, because if you're not included, the block contents aren't relevant. So they wouldn't be executed anyway. So you would make them conditional on inclusion. And this is something that some people have dived into, and there was a paper written on MEV invariance stating that the cake doesn't grow, so the MEV pie doesn't grow if Ethereum would implement conditional block building, basically, relative to centralized exchanges. And the caveat here is that centralized exchanges would also have guaranteed inclusion, and you can basically always commit to them. So instead of there being a blockchain where there is discrete commitment times, and there would be continuous commitment times. So an open question still is what would happen to the overall cake of MEV if you're dealing with two blockchains that both have discrete times and also both have probabilistic inclusion. So this is still an open question, so if anyone is working on this, I would love to hear about that. And then a separate question is whether we should enshrine or not. So currently there's been a debate about whether we should enshrine PBS or not. And there's an article written by Mike Noyder with some arguments in favor and some arguments against. Some arguments in favor are that out-of-protocol software like MevBoost could be quite brittle, and there could be some dangerous factors in this for the protocol. So, for example, he refers to the equivocation attacks that we've seen from the low-carb Crusader, and potential liveness issues with relays if their software isn't implemented correctly. However, a very important factor here that he also points out is that if we implement the wrong market mechanism and allocation mechanism, we could be sort of stuck with this because it would be very difficult to change. So if we implement the wrong contract form of the PBS design philosophy into Ethereum, so we move from a philosophy into one specific field. For example, we use the contract form that MevBoost imposed. It could be that this isn't optimal for our future. So it could be that if we use the contract form that MevBoost imposed, there's less coordination possible for cross-domain commitments, because we don't, for example, have slot auctions or other forms of PBS that would allow for more coordination. And to point this out, I'd like to use one example. So here I've taken a cross-domain arbitrage from the paper Unity is Strength, a formalization of cross-domain maximum extractable value. And we see that we need to do both on Ethereum and on Polygon. We need to do a swap, and this will net us some profit. So let's take this to an easier setting. Let's say that the total profit from this swap, in this case, it says something like $111,000 US. Let's say for a very simple case, it's just 100. And we need to pay fees on both chains. So in this case, we're first working on Ethereum and then we're working on Polygon. Let's say that we need to pay $30 US, so that's 30% of our profits to Ethereum to get our transaction included. We need to do this first, and then we can only move to Polygon, where we will see if our transaction can get included there. So now we paid 30, and then we move to Polygon, and there we don't only pay more than 70. However, the problem is that a rational arbitrager would actually be willing to pay up to 100, because the 30 before are sunk cost. So the best that you could do, if the Polygon validators are not willing to accept 70, is to bid up to 100. And this could actually be a difficult problem, because in this case you're actually running a loss if your profit is only 100. So the fact that you could potentially be running a loss, even though there should be some arbitrage opportunity, means that it could potentially not be exploited. What if someone is actually setting up these kinds of traps in order to get people to pay more? And similar problems. You could imagine that people just don't want to deal with this kind of stuff. So this is really where you see the power of pre-confirmations or slot auctions. What it could do is, for example, if you have the power to determine what's going to happen in the next state transition, you could you have the pre-confirmation basically, and you could act on Polygon first, bidding there, and only if this part goes well, you can do your transaction on Ethereum. Meaning that you don't have this problem anymore where potentially someone could hold out from selling an arbitrage opportunity to you on the second domain because they know that you're willing to bid more and they know that you're willing to run a loss. So this would prevent loss, and it would allow for some sort of cross-domain atomicity. And because of this, we see that there's a gain in informational efficiency if this arbitrage opportunity does become possible, because suddenly there's more information incorporated into prices on both domains. We see that there's an increase in allocative efficiency because the MEV that represents some sort of contention is now actually extracted, and block space is used to drive up this contention and gets us to a more socially welfare maximizing state. And this is possible because of the cross-domain coordination mechanism. So these are the 3 things that I pointed out before. So yeah, please keep that in mind if you think about cross-domain coordination. So should we wait and research this more? Well, there are some reasons to wait to prevent, to immediately go ahead and prevent some of these attacks. But implementing the wrong thing means that we could be stuck with the incorrect contract formats. And Pepsi, which is a post from Barnabé again, proposer and protocol enforced proposer commitments, really dives into this allocation mechanism and market design. So I'd recommend everyone to read that. And then finally, some interesting ideas that are there is the nuclear button idea that I heard Phil Dyan talk about, which decreases the investment efficiency of certain potential extraction techniques. Basically what it does is it says that since we could always implement some mechanism like PBS, it would be unwise for people to invest in certain very extracting techniques, because if certain very extractive techniques become very profitable, we would use this nuclear button and insert PBS. So these are some of the ideas that I'd like to leave you off with. And as a conclusion, we need to be very careful about considering whether Ethereum should be aware of cross-domain coordination. And this remains an open question. The out-of-protocol solutions may fix some things, like the holdout problem that I showed you before, which was also solved by the in-protocol solutions, but they require some trusted role and maybe some extra coordination mechanisms. But in general, allowing for cross-domain extraction might increase allocative efficiency of block space, informational efficiency of prices, and expand the possible mechanisms that we can use for our applications. So the open research question that we'll be working on is what the value of slot auctions are in the case of overlapping commitment times of blockchains and non-overlapping commitment times of blockchains, how soft pre-confirmations could actually work, and whether Ethereum should enshrine these cross-domain coordination mechanisms or not. So thank you very much for listening. If you have any questions, please feel free to reach out to me. And again, thank you for AltLayer for hosting this session. Okay, thank you. Bye-bye.
Hey there. Good morning, everyone. Thank you all for being here, and thank you guys for hosting me, AltLayer. My name is Rahul. I'm the co-founder of Connext. For those of you who have not experienced Connext yet, Connext is a protocol that has been around for a really long time. So the company actually started in 2017 when the crypto market looked very different. So we started out doing very different things. Always the focus was around building good, secure, scalable infrastructure with the end goal of onboarding more users onto Web3. So really that has changed over the years to initially focus on scaling and now focus on interoperability. And the interesting thing is scaling and interoperability are really like two in the same thing, because when you have scaling, you're offloading transactions to something else, whether it's a secondary layer 1 or a layer 2 or a layer 3 or whatever. But unless you have that interoperability, the scaling actually doesn't do anything on its own. So anyway, the title of my talk is the HTTP of Web3, and this kind of defines the future for Connext as well as the interoperability space as we see it. So just to kind of take a step back here, let's time travel a little bit back to the 1980s and see what the early stages of the internet looked like. So back in the old days of the internet, you had to do a lot of manual stuff and really like interact directly with infrastructure. So you had to know basically the subnet of some network that you wanted to connect to, use telnet to connect to a server. Then you had to FTP some storage off of it. And it really was a very manual process that exposed a lot of these layers to the end user. And this is because there was kind of a mishmash of different protocols and other kind of a lot of other things that you had to kind of think about and do manually. So then we fast forward to today. So today it looks very different. You have rich interactions that you can do with very different pieces of infrastructure under the hood. So let's say YouTube is an example. YouTube will send network requests to this very well-defined, very robust networking stack, and it will be able to query content from CDNs and deliver that to a user. It will be able to go to its storage locations and get data. It will be able to query other servers through APIs. So the whole stack has been very much abstracted, well-defined, and it's very expressive. And the reason for this is because of HTTP, right? HTTP is basically what made the web composable to some extent. So bringing us to what the Web3 is like in the 2020s. I don't mean to kind of pick on Aave here, but if you go to something like Aave or basically any of the Web3 dApps that are pretty big right now, have this property where you have an app that is multi-chain, deployed on many different chains, rollups, whatever, and you have to manually interact. You have to pick what kind of network you want to connect to. Then it's going to go to your wallet, and it's going to tell your wallet you need to change to this network, and you have to kind of manage all that stuff. So really, this feels like dial up in the internet, where we had to manually turn on our internet and connect to some website by SSHing into some server or something like that, or using telnet or something. So it's while it's very cool and there's very cool things we can do, and we all love Web3, this is definitely not the future, and this is not how things are going to look in the future. And not to mention, in this case, all the liquidity is kind of fragmented. You need to think about bridging funds from one chain to another chain if you want to use a product on that chain. So then we fast forward to how things look today, or sorry, not how things look today, but how things will look in the future. As all of us are here because of this Rollup-as-a-Service day, and AltLayer is kind of pushing this vision, I think we can all get on board with the fact that the main interaction that users will have in the future is with app-specific layer 3s. So I strongly am a believer that a lot of things will move to different siloed layer 3s where they can kind of control more mechanisms around things. So you'll have a swap layer 3, you'll have a lending layer 3, Uber and Airbnb eventually are going to become peer-to-peer applications that live on their own layer 3s. And then you'll have storage and decentralized compute that are also running as decentralized services. And our vision for the future is that all of these will be connected by an interoperability layer, which will make these interactions extremely abstracted from the users themselves. So then how do we get to this vision? Really, we need to define this kind of interoperability layer as a modular layer that is fully specified and standardized. So with this, then we can really start to build the infrastructure that makes this type of stuff possible. So let's go back to the internet and say how the networking stack looks in this modular vision. So the networking stack is already modular. So you have a transport layer, which is TCP. You have a security layer, which is TLS. And then you have this application layer. And this is important because the application layer is really what allows everything to be composable. It allows developers to build new apps. It allows content to kind of be linked to each other over the internet. And it allows users to not have to deal with any of this. They can just go into their browser and start browsing. So then how do we translate this vision back into interoperability and Web3 in the blockchain? So what we can do is we can kind of break the pieces down into like very similar looking pieces. So what you have is you have a transport layer, you have a verification layer, and you have an execution mechanism built on top. And let's dive in a little bit and explore what each of these layers do look like. So the transport layer is the very base layer of this communication between different blockchains. How do you bring a block header? It can be any payload, but let's just say it's block headers because as we'll go into later, this is the most efficient way to transmit data from chain A to chain B. You know, this may seem easy in like an all EVM world. You just have some kind of relayer that's just like reading data from one chain and putting it on another chain. However, this will get more and more complicated. And one of the things I really believe is that a lot of these app-specific layer 3s will end up moving away from EVM into, you know, more highly customized different versions of VMs that are highly tuned and efficient for their own use cases. So, you know, then you need these kind of adapters to basically bring this EVM-based process that we have right now to be able to be translated into any type of transportation. So what I'm saying is we already have an extremely well specified and battle tested transport layer protocol. It's called IBC. So those of you who know IBC, it's basically a Cosmos based system for transporting messages and doing this whole process of transport between different blockchains. If you've looked into it, it's extremely well specified. It has multiple clients running it. It's basically like extremely well documented, and it's battle tested because it's being used across many different blockchains for a very, very long time. And that's what you need with these type of infrastructure projects. So that's for the transport layer. So then we move on to the verification layer. So a verification layer works like, how do you prove that something, like whether it's a block header or something else, is valid from chain A to chain B? So this can happen in a various number of ways. The bottom line here is that verification mechanisms are going to be commoditized and be an open marketplace. So this is going to be like basically an open marketplace where different actors can compete on speed, cost, and chain support. And since basically, if you boil this down to the fact that you're just sending block headers from one chain to another chain, this is like a fixed piece of data. So the cost is not going to scale with the amount of data that you're sending. So it's really going to be kind of like a race to the bottom and an open marketplace. And the other thing to note here is that there's a lot of teams working on this right now. There's a lot of really smart people who are trying to solve this problem of securely verifying data from one chain to another chain using ZK proofs, using light clients, using message aggregation, etc. And these people are very focused on this singular problem. So they don't care about transport, they don't care about execution. All they care about is verifying that a piece of data from one chain is properly is valid and usable in other layers of the stack. So then that brings us to execution. So this is a very important piece of the puzzle. I do apologize because I had emojis and things that don't seem to be showing up on this presentation. So some of these diagrams look a little weird, but you know, I can point people to the slides later. So anyway, execution. So after a block header, we go through the transport process, we go through the verification process. Now on chain B, we have a block header that has been verified. Then how do you build rich interactions on top of that? So this is where we really get to the HTTP analogy. because really like doing something with this block header and root is the hard part. Once you have this, then you have a ton of infrastructure you need to build to actually like build apps, build cross-chain interactions. So the truth is application developers don't want to deal with this lower level stuff. They don't want to submit proofs. They don't want to read data, things like that. The data So then like, this is also where the costs in the flow are, because when you're consuming this data cross-chain, you're actually like consuming a lot of data potentially, because you're going to be sending like a big Merkle proof that needs to prove some kind of data and then building complex interactions on top. So the bottom two layers do not really have much value where, you know, users are going to be paying a lot of fees or something, like I said. So that's why these are going to be really like highly commoditized and really like kind of race to the bottom. But the application layer, the execution layer, this is where you kind of have a little more room for the flow. And really execution is what brings us cross-chain composability. Like without it, you can only consume data across chains. But really, when you have this, you can actually create applications, build rich interactions. So like to bring it back to the web analogy, the web is a graph of hyperlinks between content, and it's independent of the links under the hood. And that's really where we need to get to with this blockchain as well. So what we say is this execution layer is global state composability on the interchain. And what Connext is trying to do here is we're trying to focus in and build a really well-specified, generalized, extensible execution layer framework. So then that breaks it up here a little bit. So now at the transport layer, you have teams that are specifically working on this exact problem. Like Cosmos is doing all the work around building the base layer for the specifications around IBC. Polymer is a team that we're in touch with that is building IBC everywhere, basically. So we want to let them focus on that problem and, you know, eventually like build a client that will plug into that. Similarly, on the execution layer, you have these really great teams, some of which are mentioned here, which are, like I said, laser focused on solving this one problem. They don't care about anything else. Like we talk to a lot of these teams. They're not trying to build like full bridge functionality. They just want to build verification mechanisms that allow you to move things from one chain to another chain and prove them very specifically on the destination side. So at the execution layer, this is what we are focused on at Connext. We want to focus on building the ability for developers to interact with verified cross-chain mechanisms. And you know, if you look at this from the big picture, you'll see that a lot of bridges are trying to build this entire stack. So obviously, if you try to focus on too many things at once, you're going to end up like compromising on things and not really being able to deliver the entire solution to users. So that's why we're really trying to laser focus on this one part of the stack, which is the execution layer. So then when you have an execution layer, what are the things that you can do with it? So this is the most basic use case of an execution layer, or of the execution layer, is to do a write. And I'll call this a slow write right now, and you'll see why later. So what you can do is a user can make an X call, which is a call that is meant to go cross-chain from chain A to chain B. And this assumes that the block header has already been sent to chain B. So after some time of making this X call, this block header gets packaged up, it gets sent to chain B through the various transport verification mechanisms. And then at some point in the future, you have a block header that has been proven on chain B. So then your execution layer mechanism will do all the computation to send a proof that the user's transaction is actually within that block header, and then it will execute any type of data or call or, you know, funds transfer or anything. So the use cases for this are around things like secure cross-chain messaging, managing governance, things like that, things where you really need a very secure mechanism for sending messages across chain that may or may not include value. So the next part of this is a fast execution mechanism. So the reason I call this fast is because you have this verification process and this transport process, which can be actually very slow because, you know, when you're dealing with this type of system, there are going to be a lot of things that these protocols are going to do to reduce their own costs because, you know, at the end of the day, these are kind of like race to the bottom protocols that won't have much margin. They might be even public goods. So they're going to try to like reduce the cost as much as possible for that reason. So what that involves is a lot of batching. Then you have these things like ZK proofs, which might be really heavy and take a lot of time to run. So at the end of the day, you're going to have to, this process from sending a block header from chain A to chain B is definitely not going to be an instant process. But something you can do is you can have something called a fast execution layer. So what this is doing is this is listening for this event on chain A. And because it sees the event on chain A, it has a certain guarantee that this block header will eventually be received on chain B. So it knows at some point it can prove this. So then what it can do is it can actually go up front and send a transaction on behalf of a user. So let's use like an any-to-any swap, for example. So what that means is a user is going to maybe swap on chain A, then send the funds to chain B, and then do another swap on chain B. So what this fast execution layer can do is it can do the swap for the user and send the user directly the output of that swap. And then, you know, we'll have something in this execution mechanism to understand that this is what happened, and then have this fast execution layer be able to claim the funds back after this block header has been proven. So this is kind of like the use case where you get with many, like cross-chain bridging right now, where you want your funds immediately. You don't want to wait for some execution mechanism to happen. So this is what enables that. This is what enables an instant, like really nice, clean user experience. So cross-chain swaps, like any-to-any swaps are a really good example of this. Cross-chain zaps, you know, fund movement. And then the other interesting thing is you can also do things like verify a signature. So, you know, if you have a signature that can be verified from chain A, then you don't need to wait for the block header because you can already see that that's going to happen and verify that on chain B without needing to wait for a block header. So then the other really interesting mechanism is a read. So say you have these block headers that are coming, you know, they'll be coming on like various intervals. Then you want to prove some data against that on chain A itself. So really all you need to do, this shouldn't be an X call, this should be an X read. So an X read is where you're just going to still submit the same proof for a block header that you already have and prove that something has happened on chain B. So say you have an oracle that's like updating price data every 30 minutes or whatever, or every minute or however much they send their thing, then you have all that information in a block header that has been sent. So once that block header is received here, then you know you can read it immediately, and you can basically read data from any chain, anything that has ever happened on that chain. So other ways this would be useful: read gas price data, read token voting power as well. That's a cool one, right? Because you can basically read what your VE token balance or whatever is at any kind of snapshot in time after you've received the root on the chain that you have your DAO on, for example. So yeah, I've referred to this a few times, but XCall is basically how Connext is envisioning this whole execution layer process starting. So this is basically a primitive to facilitate asset and or data transfer across arbitrary chains. So it's designed to mimic Solidity's built-in call method. So what we want to do is we want to make the process for developers around making these really expressive cross-chain interactions extremely easy to build. And since it mimics Solidity's built-in call method, they don't really have to think about much or know much beyond what they already know in Solidity. And here is basically a snapshot from the code about exactly how you would do an XCall. So it's really simple. As you can see, the parameters are very straightforward. You have some kind of fee that you pay to the relayers for sending this amount. You have like a destination domain and target, token address, You have some safety fallback parameters around the message sender, the amount you're sending, slippage, because bridges will have some kind of slippage and things like that, and then you have call data. So this is basically the bare minimum amount of parameters that you can have to be able to make really nice kind of cross-chain interactions. So, one thing I'll get at here is that specification and standardization is positive sum. I think a lot of companies might view this as, eating into their bottom line, or this kind of like goes against what normal companies want to do, because normal companies, they want to control everything. They want to, close their APIs. If you look at like Google, Twitter, Facebook, things like that, like they're all charging for API access now because they're built like companies. They want to make profit. But if you look at what the end user wants truly open APIs where anybody can compete, use the APIs. Like if you look at the example of Reddit, this is a great example right now. So Reddit had all these different like clients and user interfaces built on top of it because it had an open API. But now that it's shutting down its API, it's been a huge backlash because, a lot of these apps are being forced to shut down because they can't consume the APIs right now. So what I'm saying is that like we want to get to a world at Connext where everything is specified, everything is standardized. This might make our own protocol like, less profitable, I guess you could say, because it allows competitors to just come in and build multiple clients. But that's not what we care about. We care about making it a better place for the actual end users to interact and, be in this world. So, just to reiterate that, Connext is not a company. Connext is a public good. Because we're building Web3 infrastructure, it needs to be something that is given to the public. It's given, deployed, and it is usable by anyone. So it operates on this standardized playing field where anybody can come and operate and build tooling around it. So, I like to say this a lot, but, at Connext, we don't want to compare ourselves to Apple, Google, et cetera, like that. We would rather hold ourselves to the bar that Ethereum holds themselves to. Like Ethereum is the ultimate vision of a public good that has been realized. And, if we could all be like Ethereum, I think we would all be pretty happy. So, just to wrap up and recap here, these are some thoughts that I want to give here. So standardization at all layers of the stack encourages competition and a race to the bottom, which is better for users, right? So obviously, if all the companies are competing in a perfectly free market, they are going to always undercut each other until they're making the minimum amount of profit that just allows them to survive. And that's how Web3 is built. Web3 is built so that there's no middleman, there's no rent seekers, there's no people trying to like take a cut. There shouldn't be any of these cuts. There should be, zero fees, zero like protocol fees should really be a race to the bottom and not even exist in a lot of projects. Right now, I think there is protocol fees, but that is something that is getting slowly undercut. Then, we need to break things down into modular pieces. So modular pieces allow standardization and specification, and they allow, like I was saying, they allow the best teams to focus on specific parts of the stack and really kind of compete on cost and speed and what matters to them. They get to focus on like one really small piece of the stack and really kind of build it out the best way they can possibly build it. Then execution application layers are what make protocols composable. So this is where we want to focus on at Connext. This is how we want to be able to interact with developers, interact with users, and make end user interactions possible and good. And then to end it all, Web3 infrastructure is a public good. I strongly believe that these are not companies that are being built. A lot of the other teams, some of the other teams are definitely acting like companies, trying to make profits, trying to figure out how they can increase the revenue as much as possible. But I strongly believe that Web3 infrastructure at the end of the day is a public good. And it needs to be compared to Ethereum. Like I said, Ethereum is the ultimate public good, and all of these companies should be striving to be more like that. So thank you all. That was the end of it. And yep, I will make this presentation available everywhere.
Okay, hello everyone. Hope you're enjoying the event so far. We have heard from some really wonderful people on topics spanning rollups, modular blockchain design space, network design and architecture, interoperability, and economic considerations of rollups. Some truly insightful presentations. What I want to do now is have a panel on the present and future of rollups. There's a lot to explore here from various angles, and so we thought we'd invite people of different diverse backgrounds to have a richer discussion on where we are and where we are going. So it's my pleasure to welcome three such people from the industry. Here we have Medha Kothari from Variant, Patrick McCorry from Arbitrum Foundation, and Stephanie Dunbar from Messari. Hi to all of you, and so happy to have you on this panel. So, thank you, Medha. Thank you for joining us and making time for this panel, given that all of you are from different time zones. So we really appreciate it, and so let's kick this off. Let's start with a quick intro. So, Patrick, would you like to go first?
Yeah. Hi, everyone. My name is Patrick. I think historically speaking, I mean, my research within my PhD in cryptocurrencies started in 2013 on Bitcoin, and then 2016, I ended up doing stuff on Ethereum. And then I guess for many years until 2019, I was a researcher, and then I left the academia and the university system to try to do a startup, as you do. The startup was acquired by Infura, and then eventually after Infura, I joined the Arbitrum Foundation. But during all those years of my research, I mostly focused on layer 2 protocols, or more specifically, how do we scale cryptocurrencies so people can actually afford to use them while still retaining all the nice benefits of a cryptocurrency.
Welcome, Patrick. Medha, you want to go second?
Yeah, sure. Hey, everyone. I'm Medha. So I'm currently an investor at Variant. We're a crypto-focused venture fund. I kind of started off my career in crypto back in 2017 as a software developer. Primarily spent most of my time in the Celo protocol. So I was building out a lot of developer tooling for that ecosystem, a lot of like smart contract SDKs, CLIs, things like that. And now at Variant, I spend a lot of my time looking at different infrastructure protocols. So definitely a lot of research into rollups and things like that. I'm excited to talk more about the panel today.
Thank you, Medha. Stephanie?
Hey everyone, I'm Stephanie. So I'm also a researcher, been in this space less time than you, Patrick. I jumped in about 2019. I was a technical writer focused on really any kind of emerging technology, helping companies kind of describe, their products and also write grant applications and things like that. By accidentally started writing about blockchain projects and then learned about, the public side of blockchain and, fell in love and went from there. I started my time in crypto, mostly in Ethereum, but with Ethereum staking. So not writing from technical documentation for non-custodial staking protocols. And then joined Messari about 2 years ago as an analyst, started on their diligence team. So was really focused on the nitty gritty details, both on the technical as well as the economic side, trying to become more well-rounded. And here I am on the enterprise research team. I mostly focus on infrastructure, layer 1, layer 2. Hard to pick a favorite, to be honest. I just love talking about, how all this fits together and, just what amazing things we can build with the technology.
Thank you, Stephanie. Now let's go with the first question. And this is a question that I think is very relevant given some of the debate that was happening over the last week or two on definition of rollups and what really defines a rollup. So Patrick, maybe you can start with, so what's your take on the recent debate? What defines a rollup?
Yeah, well, I mean, there seems to be two different camps, isn't there? Does rollup equal database, or no, does bridge equal database? And actually, most people think I have the opposite opinion. I actually agree with most of the debate out there, so I always think that's quite funny. I think the best way to describe that argument is to step back a bit and think, as an industry, what are we actually trying to build? And then how does this relate to rollups? So the entire point of a blockchain system is that a blockchain provides one purpose. I give you a copy of a blockchain, and you can compute a copy of a database. And that's all it does. This allows anyone to compute a copy of the same database. So then the question is, how do we all agree to the one database and to the one blockchain? So then anyone in the world can download the one true blockchain and then compute a copy of the same database as everyone else. And there's two ways to do that. One is you could deploy your own consensus protocol, build your entire ecosystem, build your peer-to-peer network, something that looks like Bitcoin or Ethereum, get all the participants together, get your honest majority, get all the stake in there to defend the system. So you could do that. That's one approach, build an entire ecosystem from scratch. And that's very, very hard to do. It's no easy feat. It's a Hercule feat. The other approach, if you want to, instantiate a new database, is to say, well, can we not just reuse that system that already exists? Could we pretend it's like a sort of like a public bulletin board where as long as we can post the data there, then anyone in the world can pick up the data. They can, parse it according to some set of rules, and then they can compute a copy of the database themselves. And that's basically the rollup. The purpose of a rollup is to create a database for whatever purpose that you want. And the way we all agree to that database is that we just post the data somewhere else, like Ethereum or Bitcoin, like ordinals. And then everyone can say, okay, well, I know the data is there, the data is ordered, I know the rules, I can process the rules, I can get the same database as everyone else. So at the heart of it, that's all a rollup is. It's just a database where the data is publicly posted. And we've known how to do this for at least 10 years. So the early examples were like Colorcoin and Mastercoin. I don't know if you guys remember that. It was the issue assets on top of Bitcoin. But the Bitcoin platform could not enforce the rules. It was just used as a data availability layer where we could post the data there, and as the software client could then parse that because the software client was aware what the rules were. So we've known how to do that for 10 years, and it sort of died off for a long time, maybe 6-7 years. But they originally got popular, and this sort of gets to the heart of the debate, because we now know how to build better bridges. And this is like the second half of the debate. So normally when you use a cryptocurrency system, let's just say I'm on Ethereum and I want to move my assets to Coinbase, there's a bridge in the middle. I lock my funds up, I give them the Coinbase, Coinbase protects the funds, and then it shows up in their off-chain database. So the whole point of the rollup movement today is to build a validating bridge where I can take my assets on Ethereum, move it onto an off-chain system, something like Arbitrum or Optimism or Starknet. But at the same time, when I move my funds to that system, I don't have to trust the operators of that system. The entire off-chain system could be fully corrupt, malicious, wanting to steal my funds, and the bridge will protect my funds. And that's basically at the heart of the debate. You have this off-chain database, and then you have this bridge that then protects your assets when you bridge onto this off-chain database. And all of the debate is really being focused on, does the bridge define the database, or does the community define the database? And that's sort of at the heart of the entire debate. But maybe that's a bit of a long answer, actually, so I apologize.
Well, I think
but that's basically what
it sets the context very clearly. And so Medha and Stephanie, what are your take on this? Do you feel like...
Yeah,
go ahead, Medha.
Sorry. I think Patrick had an incredible explanation of what blockchains and rollups really serve to do. And like adding on to that, for me, it really comes down to semantics. I think it really depends on what you think is scaling. In the most simple sense of the word, for me, scaling Ethereum means dApps being able to use Ethereum native assets, so like ERC20s, ETH, etc., on different block spaces. And essentially scaling expands block space by allowing new execution environments to be built on top of Ethereum, which can then be made available to all of the ETH-based applications. And I think rollups unequivocally do that. So that's kind of like the side that I land on.
Stephanie?
Yeah, I'm kind of in the same boat as well. I think at the end of the day, right, there's also that bit about social consensus that, the community could get together and they could then, move the bridge elsewhere. But I feel that would be, it's incredibly costly. And at the end of the day, you could say that there's social consensus behind everything, right? So I fall more in the camp that the bridge is really important and is, a big part of the rollup. But I do see the other side as well. But in terms of scaling Ethereum, I know there was, that argument about does Jersey scale New York? And I thought about that a little bit as well. And I also understand that perspective, but I think I was hearing in a Twitter Spaces about this idea that, well, if you add a new district in a city, that does scale the city. So I think that at the end of the day, although a rollup at this present point in time might not be scaling the base layer of Ethereum, there is the future in which we have dank sharding, other upgrades that will change in order to, do the Ethereum centric roadmap and move forward and scale the entire ecosystem. So when we get down to semantics, I can understand how rollups don't technically scale Ethereum at this given point in time. But if you look at the long term, I believe that it does. I believe that they do.
I mean, a follow-up question would be, again, about semantics mostly. Should we consider rollups as L2s or layer 2s? Patrick?
I think layer twos are a terrible way to describe all of this innovation. I mean, it's just a word that popped up because of the Lightning Network back in Bitcoin, and we've sort of hijacked it. And I feel like because of that, people get confused about what we're actually building. And as I mentioned, all we're really building are bridges to other blockchain systems. And so it just really comes down to what are the trust assumptions when you use that bridge, and what are the trust assumptions of that other off-chain system as well. So yeah, I use the layer two phrase because it's a buzzword that everyone understands, but I think it's a really bad buzzword because it's just confused. Because like even like layer two, you can like let's just say it's like Starknet's Palladium, where you have this trusted committee that keeps the data off-chain. Is that really a layer two? Or there's a trusted committee versus another bridge that just relies on a trusted committee to move the funds back and forth. So yeah, I think it's a terrible phrase because it sort of confuses people on the security of the system.
Totally agree. I mean, I think all of this is just serving to expand block space. So I tend to just use the word block space.
Stephanie, I suppose you as well.
I agree. I think it's so hard now because it's been in the popular discourse for so long that like if we start to change the words like too drastically, like as we've seen, it kind of gets everybody riled up. But I do agree. I think in the far future, this idea of the kind of parent versus child relationship is going to change as the ecosystem expands and we see more rollups. But it is hard to change the terminology at this given point in time.
Okay, so now moving away from rollup world and the modular world, if you go back to what people often refer to as the monolithic world, right? People, I mean, at least in the crypto community, right? It's pretty kind of standard now that they all agree that modular architecture is fundamentally a better design. But what are the benefits of a monolithic architecture that people working in the modular space should definitely acknowledge and maybe should learn from as well? Any characteristics? Go ahead, Medha. Yeah.
Sorry, I was going to say I can just jump in with one example and then would love to hear everyone else's. I guess one of the best parts of modular structures, in my opinion, is that you have specialization at each part of the stack, right? But with that, you're basically introducing all of these dependencies at every layer, and that increases kind of like the exploitation risk of every part of the stack. So in a way, monolithic structures, you kind of know exactly what you're getting. And I think because
as well.
Sorry?
And new trust assumptions as well. So for example, if you're using a new DA layer with certain trust assumptions, then you're kind of following that as well.
Exactly. Yeah. So I would say monolithic architecture definitely has like some level of trust minimization. And because there's less experimentation happening, I guess you could maybe assume that there's like less mistakes, or like there's one thing that people are working on. So those teams are spending years building out those layers of the stack versus, again, with kind of trusting different modular parts of the stack, you're trusting that each one of those are acting perfectly, and they might be totally independent actors. So
I think I would just add to that. I had a different thought in terms of what the modular world, I'm going to jump to my second thought. Something that I've been thinking about a lot is about infrastructure concentration in general. So although when you add different pieces to the stack, you have the potential for there to be failures of the different pieces, there's also kind of this unforeseen underlying stuff going on between any system, including monolithic structures. So where all the nodes located, where's the majority of the stake, how many clients are they using, and that's fundamental to any blockchain. But I think that people don't realize, like, I think that at the end of the day, it's when you're just scaling one system, like it can be just as dangerous as scaling, I think it's actually less dangerous when you have the different components, because you have the optionality and there's people that are going to be building different things and thinking in different ways and using different infrastructure. So I think that it can be seen as a benefit as well as a kind of a drawback, that there are different, pieces put together. It can lead to like some additional issues, but also protect against other kinds of failures as well.
Yeah, maybe just to jump in, I've been trying to think how to answer this one. It's quite tricky. Because I sort of, historically speaking, I lived through the block size wars. I sort of saw the conflict amongst the community. And at the heart of the block size wars was because we didn't understand anything about modular systems. We just assumed that you only have a monolithic architecture, and that was the only way to scale these networks. And so either you had then you had this trade-off in decentralization. Do you make the system more affordable with bigger blocks, bigger blocks, cheaper transactions, more users, but then you reduce the operators of the system and people who can verify the system. On the other hand, you have small blocks. I can run this in my Raspberry Pi and everyone can verify that it's correct. But then this is a very expensive chain. Is it a whale chain? And it's not decentralized in terms of users because it's only useful for whales. And that conflict was very toxic because we just didn't understand the design space of, there is a third way of actually just modularizing out these different problems. Maybe the benefit of the monolithic approach is really bootstrapping. Maybe that's the best benefit. You want to, most of the successful projects in our space got code out as soon as they could, and then they let a community emerge around it. If you try to start from the beginning to build your ivory tower, then you're going to fall behind the market because it takes 5 years to deploy, then no one cares after that point. So maybe the monolithic was useful for people to bootstrap a project, see if it works, then afterwards they begin to modularize it. But I think if you remain as a monolithic project, then you just end up in this toxic war because you can't achieve the stated goals of the project because it just doesn't allow you to achieve it. That's the Bitcoin problem, which is such a shame.
Talking about...
Yeah, I think that's good.
Go ahead, Medha.
Sorry, I was going to just add one more. I think that was a really good point. I think similar to that, different economic models might also lead to very different incentive structures. So imagine if each part of the stack has its own token. So the DA layer, execution, etc. So beyond the fact that coordinating all these tokens might add complexity, you also just have the fact that these tokens might have totally competing incentives. And so one of the benefits of the monolithic approach is that you don't have to deal with this at all. And it might be more capital efficient. This is a big question mark, but I think it's one thing to think about.
Yeah, and actually maybe just to jump in, because I know people are listening to this, when we have they may not actually know what a modular architecture is. So, there's basically three, I like to think of three different layers. You have the data availability layer, which is basically saying, here's all the data blobs, and here's the total ordering of the data blobs. Given the data blobs, hopefully we can then compute a copy of the database. Then you have the execution layer where we take the data blobs, we execute them, and then we actually, compute a database itself. And then the third one is sort of this settlement layer, which is the Ethereum layer, and then so I'll actually get that in a second. The settlement layer basically is the database that records all the assets. And it should really be minimal execute. Well, there's actually a debate whether the settlement layer should just be data or it should be data plus a little bit of tiny execution. So the Ethereum roadmap would be that Ethereum serves as a data availability layer and a settlement layer. Then the execution layer are the rollups. Something like Celestia would have just a data availability layer, then an execution layer on top, or a settlement layer on top, and then your execution layers, the sovereign rollups. Ordinals would be the same, for example. And so we're even in the modular space, we're debating on how modular it should be because you lose some nice benefits if you really do distinguish the data and the settlement layer. And that's something that's going to be tested soon with the launch of Celestia. So I'm really excited to see that happen versus something like Ethereum.
Talking about bootstrapping of, it's easier to bootstrap, it's a monolithic network or chain. Talking about that, it's I guess an equivalent of that would be an app chain, right? Model for example, in the Cosmos space. And Stephanie, you did write quite a few articles on this, at least one article I remember that I've read. What are your thoughts on rollups versus app chains, right? What are the benefits of building a rollup directly for your application versus building a monolithic app chain, for example, using SDKs like Cosmos?
Sure. So app chains, born out of the Cosmos ecosystem are this idea of having an entire monolithic blockchain for one usage. So you could have, Osmosis is a great example of, a DeFi specific chain. You could have another infrastructure specific chain. I think DVPN does decentralized VPNs. And so it's in the Cosmos world, it's kind of a collection of these, sovereign independent chains, and they're connected through, a message passing layer, which is IBC. So the difference between an app chain and a rollup, the biggest difference is obviously an app chain is a full monolithic structure. So you have all of the layers, put together. You have, a validator set, and that's, I think one of the biggest detriments to an app chain is, having to bootstrap that validator set, like we were talking about before. It's a Herculean effort, I think you said, Patrick. So super challenging, right? And you have to attract, a good number of distributed, individuals to operate your chain, and that can be really challenging. So the difference between, a rollup or an app-specific rollup and an app chain is that you have an app-specific rollup can be, specific to a certain type of, need, so DeFi or VPNs or whatever it be. But you're abstracting away, you're using different infrastructure for that base layer. So your DA and your consensus is, outsourced outside of your system. That way you can only focus on your execution environment. You don't have to worry about bootstrapping that validator set. And you just have a little more flexibility there in terms of, also you can, be a part of a settlement layer. So if you're, if you're an L3, sorry, I'm going to use the terms, an L3, on an L2, you share the benefits of sharing a settlement layer with other rollups. And that would be the primary differences. I think in terms of what is best built on a rollup as opposed to an app chain, I think it really comes down to, developer preference. Like what are you looking to do? Do you really want to build that base level infrastructure? Do you want to have that customizability right to the base layer? Or do you want to, outsource that and focus more on your execution environment and focus on the benefits of being, just specific, kind of the what's the word? The simplicity of just operating in that space. I think I'll pass it off to Medha. I think you probably have a lot of good ideas about what would be really specific examples of, an app or a rollup or an app specific rollup as opposed to an app chain. But for me, I just feel that it comes down to the developer preference, and you could go both ways. It's just about kind of thinking about your specific application first and then building from there.
Yeah, totally. I think Stephanie did a great job giving an overview of like why you'd want one over the other. I think for me, like an interesting use case that pops out for kind of the opposite, like why an app chain versus a rollup, is when you need to really have fine-grained control of like security in the consensus layer. So a good example of that would be like an application where like the regulatory boundaries are super, super strong. Like you need to know like who your validators are. You need to know what the rules are to like pass any sort of like transaction validation, etc. I think it makes a lot more sense to build an app chain rather than a rollup, because you can have control of every part of the stack, kind of like what we were talking about with the previous question.
Patrick, anything to add?
Yeah, I was just trying to like process what they were saying. They were all made really great points. Maybe the way I like to look at it is sort of, so I know we're using the term app chain, but basically what we're saying is we want to build our own entire network and then obviously pass messages using IBC, for example. And as mentioned before, that's sort of like a Hercule effort. Those systems are secure because you assume an honest majority of the participants are honest, effectively, and they're willing to protect the safety of the system and the liveness of the system. And that's a pain in the ass to do, to be honest. It's a lot of work to put that together. Where what's really nice about a rollup system is that what we're really doing is saying, all these systems do need this ecosystem, this honest majority, this consensus protocol to run the system. Basically, that always needs to exist. A rollup just takes something like Ethereum or Bitcoin right now, and they just take that as a black box and they say, okay, we've got this now. We can just use Ethereum. It already exists. It's done all the hard work for us. Then we deploy the bridge, and then the way the bridge can be set up is that we just need one honest party to protect the system. As long as one honest party can step up, they can stake, they can participate, then the entire queue and all the funds are protected as well. And so it really just comes down to this path of least resistance. Do you really want to deploy your entire whole network, or do you just want to set up a system where you need one honest party that could be anyone in the world at some point? Right now, obviously, it's still being built, but long term, it could be one honest party that steps up, even if the operators of the system are malicious. And so it just becomes this technology stack. Long term is like an SDK. I want to deploy a database. What do? I get the code. I deploy the bridge. Creates my database for me. I have a sequencer. May have one or two executors, but it's open, it's permissionless. Then anyone can step up to do the hard work if that's necessary. For me, it's just again least resistance. This is an easier stack to deal with, and you can imagine thousands of these emerging because it's just way easier for people to do. And now there's lots of rollup-as-a-service companies. Even AltLayer, again, is like a rollup-as-a-service company, because it's way easier for you guys to write software to deploy this versus creating unique networks for everyone. So it's just way easier to deal with. I don't know.
That's true. It's much easier to deploy a rollup as opposed to finding, I don't know, even 100 validators, let's say, if you want to have for your apps. It's pretty complicated and time consuming. And then, you have
exactly.
to incentivize them as
100
well.
And was this your point? Though that's a great point. If I want to set up an op chain, maybe I need to have 100 validators. I have to go source these people initially and bootstrap it, or you just have one on this party. It's just easier, isn't it? Just a lot less.
Indeed. Yeah, go ahead. Go ahead, Medha.
I was just going to add that, a lot of these, like a lot of the no code, rollup deployment interfaces, I think like the goal is to like get a rollup up and running in, 10, 15 minutes, which is just fantastic.
Yeah, let's talk about that. So, of course, AltLayer is building a Rollup-as-a-Service product, and there are other parties and vendors and builders out there that are building similar products. Some of them are, I'm not sure if they can be called Rollup-as-a-Service, but more like some people offer this SDK model, and the others offer kind of a managed service model, like a SaaS model. But the main question, like at least a common criticism that I often hear from some people, is that there isn't enough demand for application-specific rollups today. So what are your take on this? Do you feel like there's demand and it's just that you guys don't have it, or is it like it's still building and it will take a few years for the demand to really come to a place where it will be noticeable?
Yeah, I love this question. I think it's a bit of both. Like there's like the chicken and the egg problem. Like, yes, like right now, maybe the demand isn't there yet, but I think part of it is because it's not super easy to stand up a rollup right now. So like to Stephanie's point, the reason why like rollups as a service exist is because not every team has the developer bandwidth to like manage all of these things. And also like we shouldn't have to reinvent the wheel every time, right? You can't expect like a consumer founder to have to keep up to date with all of the research happening at the infra layer. It's like not a good use of their time. But I've definitely seen in my portfolio, for example, people are very much thinking about how to scale, how to like control their own block space, how to look at different things like MEV as a business model, et cetera. And all of those things kind of require specific knowledge at the infra layer, which if a company is willing to kind of stand up and make it easier for them, I think definitely people are going to use them. So I think abstraction is the key. So once these things proliferate and once people understand why they should be using their own block space and kind of controlling their own rollups, once that idea launches, it'll be a lot easier and that'll kind of increase demands for rollup as a service products. But I'd also love to hear your case for this, Amrit, since you're thinking about this every day. So at some point, would love to hear your thoughts.
Yeah, sure. I mean, I can go ahead. So, well, I do feel that there are certain types of developers, or at least companies and entities out there that definitely do not want to go and build everything from scratch, right? Even SDKs, because that's not their expertise. They like it or not, they still have to go and understand sequences and things like that, right? And so what they want is they want to outsource the entire stack to someone else and say, guys, why don't you go and manage this for us while we go and focus on our game development, for example, right? Because that's what their core expertise is. And so in those cases, we have seen people coming towards from the gaming industry, and people are building around experiments around SocialFi to come to us and say, okay, guys, we want to have our own chain, because historically too, right? Games have always tried to build their own infrastructure, right? Because look at Axie Infinity. Initially, it was on Ethereum, and they went to do their own thing. More recently, Ronin is a good example of an app chain for games. Game developers are definitely very keen on building app-specific rollups themselves or using infrastructure provider. DeFi has certain restrictions. Many of these people feel like they would miss on liquidity. It's not good to have sitting on your own rollup and things like that. Maybe that will change with better bridges and so on. I'll stop here, Stephanie, if you have anything to add.
No, I guess I would say I really agree with both of your points. And I also just think that, I guess to add to that, there's just going to be so many different people that want different things. And now that we make it easier, the more abstraction we have and the more, rollup as a service kind of products we have, the easier. I think before you were kind of talking about how there's the rollup SDKs and kind of the no code deployment. And I think I'm really curious to hear what Patrick says about this specifically, but my original post, I wrote a piece about rollups as a service, and I'd kind of grouped them all together. I put SDKs and sequencers as a service as well as no code together. But the more I think about it, and I think there was a debate on Twitter about it as well, I think that SDKs probably don't fall into that definition of rollup as a service, because a lot of these SDKs are, open source or with, permissive licensing, and they can just be used. And so rollups as a service providers can build on top of them. And I think, Arbitrum would be an example that, and correct me if I'm wrong, but the way that I kind of looked at it with the licensing model where, you can freely deploy anything with Arbitrum Nitro on top of Arbitrum. But if you want to deploy, a rollup with Arbitrum Nitro elsewhere, you're going to have to, make an arrangement with the DAO or get the DAO to, agree to that. And so I thought, there has to be some incentive for the DAO to want you to do that. So in some ways, you're kind of treating the use of the code base as a service. So curious to your thoughts on that, Patrick.
Yeah, that's great. I mean, that there's sort of two ongoing questions now, isn't there? So let me tackle that one first around the license.
Sorry.
I think that's important. No, that's really important. So basically, it really comes down to the heart of whether companies can offer rollup as a service, because if they can't get the license to the software, then they can't offer the service, can they? And this is something that the Arbitrum DAO really needs to deal with at some point. I wrote a blog post a long time ago before I joined Arbitrum, and what I was really looking at was sort of the licenses of rollups. Like the problem with, the business source license, and I'm going to say business source license for now, is a lot of startups don't want to go and interact with a company in order to get a license, so then they deploy, the actual type of software. That sucks from everyone's perspective. We don't really want gatekeepers to have to deal with this. On the other end of the spectrum is sort of the Apache license and the MIT license. Is that what you can also end up fostering is that someone might take your code and compete directly with you, and then harm the ecosystem in a sense. We sort of saw it with Sushi and Uniswap, and then Uniswap pioneered the business source license. That also sucks because if someone takes your code, deploys it, they don't feed back into your ecosystem, then that sucks for Arbitrum, doesn't it? Or any other network or any other project that's building software. So I really like to see the Arbitrum DAO deal with, and it's up to them to deal with it, is a ecosystem license. Or as long as you satisfy some criteria, maybe you share some of the revenue back to the DAO, then you're free to take the code and deploy it any way you want in a layer 2 format. We have some evidence that, at least for the Optimism upstack, like the base protocol, or Coinbase base, and the other, I forget the other company now that's doing it, but they've all agreed to do a revenue share with Optimism, or at least the Optimism Foundation, whatever legal setup they have. And that's cool, that that's something that could be incorporated into a license and then incorporate into the SDK, and then that's how they launch L2s. So I think that's definitely a problem for the Arbitrum DAO, and I would love to see them start talking about that, because it's their decision to do with the Arbitrum code that they want to do now. So that's maybe the answer to the license question. Then the other one is sort of the original question was sort of like, why should we care about these systems? What are the use cases? Are we just too early with them? And I like to look at, I think there's two solid use cases you can think of. One is we want users to interact on the rollup itself. And I think from a user's perspective, users don't care. Users don't really care who custodies their funds, but operators do. If I'm a trendy startup today and I want to compete with Coinbase, can I really replicate their operational security to protect billions of dollars? Now, that is how they protect their assets, even Binance as well. I think they have like $60 billion or something crazy like that. Setting up the human process to protect those funds is very difficult. What's really nice is rollup as a service, or as a software stack, is that I can take the code, deploy it, and then the software protects the funds for me. So as a trendy startup, I no longer have to worry about custody or protecting users' funds. I can just actually focus on the service that I want to provide. And I've seen this already with like Loopring, DYDX, and other exchanges like Rollups. And obviously Coinbase is now doing the exact same thing. They've realized, we can deploy a rollup and we don't have to protect our users' funds now. We can have Coinbase custody, then we can have a rollup that provides financial services like trading and swapping and loans, etc. So I think that's like one very useful. I think it's the operators that care more about that, because it's way easier for a startup now to compete with Coinbase. The second one it's more like it's more from the perspective of smart contracts that live on the blockchain already. So maybe they already live on Ethereum, but they want to get some external information. It's like an Oracle service, a bit like Chainlink or maybe the Subgraph. When you think about these bridges, At the heart of it is that they just pass messages. You can pass messages from Ethereum to the off-chain system, or from the off-chain system back to Ethereum. So in an ideal world, because I'm sure people know about Subgraph, where you can index data and then query it and get a result. It'd be really nice that if I was a smart contract living on Ethereum, I could ask the Oracle for data, the Oracle could respond to me, but I have confidence that a certain algorithm or process was executed on that data. So I can get confidence about how the data was manipulated. The source of the data obviously depends on, garbage in, garbage out. You always have that issue. But at least I have confidence about the execution on that data and that the result could be correct. Where today you just rely on certain parties to attest to the fact that it was done correctly. So there are two use cases I see. You could build a much better subgraph, or you could build a rollup that targets users, and that'll be more for operators probably than the users themselves. So sorry, I know that's a really long answer, but I think that's sort of how I look at it today.
Let me give the follow-up question to Stephanie, this one, because I think she mentioned about SDKs, shared sequencers, and so on, right? So do you feel like for some of these, for example, shared sequencing to be successful, you need a lot of rollups? Do you agree with the statement?
I think there certainly is. I think that the success of rollups as well as sequencers is obviously coupled, right? You can't really have one without the other. I mean, you can have a centralized sequencer, but which is also an option. But I'm sure a lot of projects are not going to go in that direction. They're going to want either their own decentralized sequencer set or a shared decentralized sequencer set. So I think that there's a lot of network effects. Like you get a lot of benefits when you share a sequencer set. You have if you share a data in a sequencer set, you have a lot of composability benefits in terms of bridging and atomic transactions even. So I think it will be really beneficial for some of these shared sequencers to have a lot of rollups they're plugged into, and it'll be mutually beneficial for both. The thing is that I don't think anyone has really modeled it out yet, unless I'm wrong. But there's probably going to be a limit to which you can share a sequencer set. Eventually, you're going to have too many rollups, and the load will be too much, if I understand correctly. So at the end of the day, I think that there is space for a variety of different shared sequencer sets, and it's also good to have that friendly competition. And it's a positive sum game in the end. You don't need to have just one sequencer set that everybody uses. But if you join a sequencer set, you want to be a part of that ecosystem and have those composability benefits. And so I think that, sorry, I think I'm kind of blanking on the original question. I think the question was whether they would be successful.
The question was,
I think you answered it very well.
No, right. So the question was mostly around, so you have these, I guess, services or service providers today, like shared sequencing networks or interoperability solutions out there. And of course, they can be successful with, let's say, a few rollups out there, but they become even more successful when you have more and more rollups, right? So, if, for example, the grand vision of every smart contract is a rollup, essentially, then you have these interoperability solutions or say shared sequencing really become the biggest, I guess, the leverage on these, the growth of rollups in general, right? So the question was that, do you agree with this, or do you feel like they can find other ways to tap into the consumer base and user base?
Well, I mean, teams are smart, and if they needed to pivot for some reason, rollups didn't work out, and they didn't want to be sequencers, they wanted to be validator or something else. I'm sure they could pivot and do so. But yes, at the end of the day, right, the shared sequencer networks need the rollups to be able to succeed. But I do really feel that the ecosystem benefits that you're going to get from these shared sequencers are going to really create all these ecosystems that we haven't even seen yet. So I'm super curious to see what happens. But I think that there's a huge need for it, especially right now as we get closer and closer to seeing a lot more live rollups.
Medha, any comment on interop and rollups?
Yeah, totally. I was actually going to mention this later, but I think I would really hope that there's more of a focus on this in the future. Like, I'd love to see kind of a greater emphasis around like interoperability and shared liquidity on all of these like shared rollup infrastructures. Because, for example, in an ecosystem like Optimism's OP stack, I think shared sequencing could really help something like interoperability, where you're making sure like basis ETH is like easy to access with just like normal ETH and all of the other like optimism chains, etc. Right now, that isn't like super easy actually. Like the bridging UX is not great. So I think that this is a place where a lot of really smart teams are working on shared sequencing, and I think this will help a lot. I also think around value capture, this idea will be really helpful. So shared sequencing kind of opens up a huge possibility around MEV. And so with more research on shared and decentralized sequencing, I think a lot of these L2s or block space companies will be able to think about value capture better, because right now, most L2 tokens like aren't really doing much yet. They aren't capturing value in a way that makes sense beyond like governance. And I think shared sequencing is kind of like a potential avenue, like a solution for that.
Patrick, any thoughts?
I think both the comments are really good. I'm just trying to think what I can add to it. I think it's really important to distinguish what the sequencer is supposed to be doing. Again, for people listening to this, they might not actually know what the role of a sequencer is, and lots of teams get confused about what it's supposed to be doing as well. So in a rollup, you have two different actors. You have the sequencer. They interact with the user, they take the user's transactions, they order the transactions for execution, and then they pass them on. So all they're doing is ordering. They're not executing. They know what the execution will be because they decide the order, but they don't actually do the hard work of convincing the bridge about what the database looks like. Then you have a set of executors. You take the order transactions, they execute them, and then they convince the bridge, oh, bridge, this is what the database looks like. So with that in mind, what's really nice about that architecture is that the sequencer potentially has nothing to do with the security of the system. If the sequencer goes offline, users can just take their transactions, send it to the bridge directly, it gets ordered for execution, then you assume there's one honest executor out there who picks up the job and obviously executes it. So that's cool, the sequencer can be one actor, and it doesn't necessarily impact the fundamental security of the system. Now, there's some of the things in the short term they could do, they could just promise to include your transaction and they don't. And that could have implications for these DeFi protocols. But what's nice is that you don't have to necessarily decentralize the set of executors. We don't need proof of stake Ethereum. We don't need 500,000 different sequencers. And then if you think about it from that architecture, the sequencer's job is to offer a fast path and the user experience, and to make sure that the user gets the best experience when interacting with this rollup. And that comes down to one part of that is latency. Who do I talk to? The user needs to know, where do I send my transaction? The basic problem. The second one is what's already been alluded here is composability. If there's two different rollups, let's say the user wants to, take their money on Arbitrum and then send it over the Optimism, do a transaction there, and then they bring the money back. In that case, there's a benefit to have a shared sequencer who runs on both systems, because then they can coordinate the transactions. I think personally, for me, that's a short-term solution until we have better bridges that connect the various rollups, and it can provide you asynchronous, or like hop protocol, I send the value over, I interact, and I bring it back. It's not immediately composable. Well, it is composable, but it's not synchronous. It's async. It may take 2 minutes versus a very nice promise that'll be done atomically, or as close to atomically as possible. And then I think when you think of the sequencer set, the goal is really just to make sure that you can make sure that the fast path is always available to anyone in the world, or to most people in the world. And that's really the goal there, is to make sure people can actually transact on the system that is credibly neutral.
Thank you, Patrick. I think we're running out of time, so we'll take one last question. So there's a question about what the future would be, or what you think or hope the future should be. So what are your predictions, or what are you hoping for the rollup space to achieve in the next 2 or 3 years? Stephanie, you want to go first?
Yeah. Wow. Sometimes it's so hard to envision what's going to happen even in a month from now. Everything moves so quickly. But I'm really excited to see a lot of these projects launch on mainnet. So I think, Celestia being a huge project that we're all expecting. And then, all of the shared sequencer networks that are going to come online as well. And just, with the growth of Rollups-as-a-Service, which are, getting also a lot more established, just all the different plethora of rollups we might see. In 2 to 3 years, to be honest with you, I can't exactly tell you exactly how it's going to look, but I feel like there's going to be a lot of lessons learned We're going to discover some issues, things that didn't quite work the way that we thought that they would in theory, and we're going to correct them. And I'm just excited to, be a part of this journey and, documenting and seeing, where we all go. It's just super exciting.
Medha? What are you?
Yeah, I have a couple. I guess for one, I'd love to see, I kind of mentioned this, but a bigger focus on value capture. So if we're right about the rollup-centric future, rollups are going to be in the flow of so much value. And so how are they going to be able to capture that value? So that kind of requires effort done both around shared/decentralized sequencing, around like thinking about like incentive structures, etc. So I'm excited about that. And then the ZK space is moving way faster than I think any of us really expected. So I'm really excited to see a lot of those kind of come on mainnet in the next year or so. And then I'd love to see more out of the box models for specific use cases. I think a lot of the Rollup-as-a-Service companies are going to be driving this. But let's say I'm a game, like I want something like so easy to use that it's like specifically built for like high throughput, high take rates, etc. And it's just built for this use case. I think you can do that for a lot of different use cases. So I'd love to just see like developer experience getting better around rollups. And then the last one I'll say is around kind of greater emphasis around like bridging UX, kind of like what Patrick was talking about, like how can we get atomic interoperability between all of these connected rollups. But yeah, I'm really excited about all of this. I feel like the rollup space specifically has a lot of engineering bandwidth behind it right now. Some of the top projects working on it, which is great. I think it's proliferating a lot faster than any of us thought.
Patrick?
Yeah, maybe some concluding thoughts. So I think what's important is that we can see the results today of how rollups are going to sort of look in the future. But it's important to remember this has been a very long journey. It sort of started in 2014 with the original sidechain paper for Blockstream. They don't use the word bridge in the paper, but they were basically trying to build a bridge where I could take my Bitcoin, lock it up, put it on a sidechain, transact there, and then bring my funds back. And it's taken a very long time to solve a lot of theoretical issues and, of course, practical issues of deploying these systems. They get to where we are today, where there's maybe 4 to 5 big rollups, you could say, or 6. I mean, let's say 5 now that are probably live, So then the question is, where do we go from here? And I'm really cautious that, like, this sort of resembles the beginning of, computing in the 1940s. There's a really famous quote by Thomas Watson from IBM, where he basically says, you can't foresee a world where you need more than 5 computers. And today we have about 5 rollups. It's very, very similar dynamic here, isn't there? And to me, I definitely foresee the idea that rollups can just be an SDK that anyone can deploy, and it will protect the users of that system. I mean, what you're really doing is that you're removing this power balance between the user and the operator. Today, the operator holds all the power. And because of that, and that the requirement of trust in the operator, it creates a lot of friction for people to interact and to transact and work together. But once you remove that power dynamic where the user is equal to the operator, and there's no longer this power dynamic that you don't have to trust the operator of a system, you just have to trust the platform itself. Then it's very easy for people to just transact on the internet. For example, I could lock my funds into this Chinese website that I can't read. I could then play their horse racing game. Maybe they rigged the horse racing game and they beat me, but at least I know if they go offline, I can always get my funds back out. Where today, there's no way I would send my money to a Chinese website because I just don't know the operator. I have to trust them. So once we can remove that power dynamic, then yeah, this is going to flourish. It's going to be hundreds of thousands of deployments of rollups because it's just a better way to build an open database and protect users. And if anything, when you think of the regulatory sort of environment now that the US finds itself in, sometimes you sit there and think, are we the bad guys? Are we actually doing something really wrong and the regulators are correct? But it's wrong. It's the opposite. It's sort of, we're building systems that is a regulator's wet dream. They're so transparent that there's the financial information is all there on the blockchain. And we're building systems that protect users. At the very heart of it is just to protect the user when they transact. So yeah, I'm very, very bullish on the field, obviously, and hopefully for the right reasons. But yeah, there's one of my views for the future.
Of course, of course. Well, with this, we will end this panel. Thank you very much, Stephanie, Patrick, and Medha for your time. It was great having you all talk about rollups, rollups as service providers, and other related topics. Hope you all enjoyed this conversation as well. Thank you very much.
Thanks, everyone.
Yeah.
Everyone, thanks for having me today. So today I'm going to be telling you about permissionless interoperability, why I believe it is the key to realizing the potential of modular blockchains, and why the potential of these two can combine to allow blockchains to finally scale to be able to support a global audience. Now in doing so, I'm going to have to tell you about Hyperlane, the first permissionless interoperability layer. And in doing so, we will examine it as an overview first and then dive into the specifics. And before we get into that, a little bit here, Hyperlane would like to talk about this concept of the interchain highway. What is the interchain highway? Think about a path connecting between the increasing array of these chains that are just kind of otherwise floating through space. The interchain highway is a way to put on and off ramps, right? A way to connect between these, between this increasing set of chains. And like regular highways, making it easy, making it accessible, making it relatively safe, and certainly making it fast. So today we'll cover how permissionless interoperability and modular security combine to give us something like the interchain highway, which is, of course, enabled by Hyperlane. So where are we today? Today, we have these internet computers. And these internet computers are really cool. They're amazing. They can do a lot of things, all the way from giving us sovereign money to giving us permissionless access to computation. And that's all really cool. And a primary way that these internet computers are able to do this is due to the fact that for the first time, they have both created an environment in which we impose and also materialize scarcity and visual resources. I really like this visualization here. What we see here are Bitcoin and Ethereum blocks visualized as buses. And I think it's really great at illustrating this point of materializing digital scarcity. Because if you think of it, a bus has a certain amount of seats, and that amount of seats is kind of fixed through time. You can get another bus with more seats, but a single bus has that same amount of seats. And think of that like the amount of space in a block. The fact that more passengers want to get on the bus does not change the amount of seats. The fact that more transactions want to get into a block does not change the amount of space in a block. And this is both the most interesting, but also perhaps the most problematic thing about these internet computers. Because, think about all of us here today. If you're listening to this, how you presumably care about blockchains very much. You want to advance them. You want them to have more adoption globally. You maybe even have, like myself, ambitions of creating an alternative financial system, a global one that is built on these blockchains. But we only have so many buses and so many seats on the bus. So if all of us here are working to increase demand, we know what's going to happen, right? There's the same problem, the same scaling issue is going to hit us every single time. And it's, of course, the issue of congestion. And what happens with these scarce digital resources when demand increases? Well, we can't produce on demand more seats. We don't have, the amount of seats on the bus don't change dynamically in response to the amount of demand for those seats. And so we end up with surge pricing, and the gas is just too damn high. So what do you do about it? Right? If you're here today, it's presumably because you believe that the most promising, or at least one of the more promising solutions to this problem is the modular vision for blockchains, the modular future for blockchains. If nothing else, it seems like the most promising path for Ethereum. The rollup roadmap for Ethereum is certainly something we're all working towards here. And I'm not going to go into the details of what this means, because presumably, again, if you're here, you know enough about it, but separating the different services that are provided by a single chain into different layers in a stack, and those being provisioned by different providers, this is really what we mean by the modular vision for blockchains. And in particular, one consequence of it is that you're going to see not just a few very large, very capable internet computers, but rather an increasing number of smaller internet computers that are all working off of larger ones and settling to larger ones. But so there are tremendous efforts by a lot of the people who are here today to make it increasingly easier for someone to launch their own modular chain, to launch their rollup. Whether it's rollup frameworks like the OP stack, whether it's data availability solutions like Celestia, and whether it's Rollups-as-a-Service providers like AltLayer that brings us here today. All of these make it increasingly easier for you to spin up your own chain or rollup. In fact, it's not unfeasible to say that already today, within a number of hours, you can go from nothing to having your rollup live. And so think about this world where we're going to have an increasing amount of chains, because again, it's increasingly easier to create your own modular chain. Have all these chains coming up and floating through space. Each one, you can think of it as like a new island in the ocean. But how does it connect to the others? How does it connect to the mainland? How does it connect to the other continents and countries that exist in this world of blockchains, right? Sure, you can use an optimistic route to go between your rollup and the mainland, but that's a cop-out, right? That barely suffices. What do we do when there are thousands, maybe even hundreds of thousands of these chains? How do we connect them all? Enter Hyperlane. And with Hyperlane, we have the first permissionless interoperability layer, as I mentioned before, the tool that lets anyone connect any chain, a solution that fits this modular world of blockchains, where we're going to end up with an increasing number of chains. And this little visualization here, think of it as that interchain highway that we described before, the pathway that will connect between these new chains as they begin floating through space, and providing a safe and secure and easily accessible path for folks to traverse on. So why is permissionless interoperability really necessary? Well, blockchains historically have had an issue of connectivity, but by 2023 today, there are modes to connect between blockchains. The issue with those is that they are entirely permissioned. And what does it really mean to be permissioned? It means that you need to ask someone to allow you to use that service. Right? If you create a new rollup today, you can't just have one of the major interoperability protocols supporting you just because. It does not work that way. Enter Hyperlane. Hyperlane, as said before, is the permissionless interoperability layer, a tool that lets anyone connect any chain. Hyperlane means that for interoperability, you don't have to depend on anyone. You really can get sovereignty in your interoperability. And if you look at this visualization here, this is something that I put together using Midjourney to try and illustrate that concept of the interchain highway that I mentioned before. Think about our modular vision for blockchains materializing. It really does mean that ultimately we're going to be ending with thousands, then hundreds of thousands, maybe even millions of little modular chains. And a permissioned interoperability solution is simply not going to work. It's not going to fit this world. So we need something permissionless, something that can be served and owned ultimately by the chains that want to use it. And this is where Hyperlane comes in to solve what has been the major issue in blockchain connectivity today, which is not just the issue of connectivity in general, which was a problem leading into the last few years, but today we have solutions in 2023. The issue with them is their permissioned nature. Now, how does this happen? Why is this even a problem? Well, primarily it's a problem because the current landscape of interoperability solutions has these one-size-fits-all security modules. Primarily this is the case because they have tightly coupled the product of connecting between chains, the interface for connecting between chains, as in this illustration here, the messaging interface. They've tightly coupled it with a security model, and you can't blame them for it, right? Crypto is the most adversarial environment that's really ever existed for computation, or at least one of the most adversarial environments. And in it, security is paramount. We know what happens when security goes wrong. And so it probably felt very prudent and sensible to tightly couple these things. But certainly, they don't have to be tightly coupled. And security can be interfaced in modules. Now, as long as it is the case that they are tightly coupled, if you want to use that messaging interface, you are going to need to receive access or receive permission from the operator of the security model for you to be able to use their messaging interface. And this leads us into the concept of modular security being a solution for the problem of permissioned interoperability. So all of this leads us into modular security being a solution to the problem of permissioned interoperability. We're going to get into the concept of modular security in further depth as we start talking about how Hyperlane works, but at a high level, what you should take away from this is that modular security decouples the messaging interface from the security module at hand, and most importantly, it allows for customization and configuration on behalf of the connecting application, the connecting rollup, such that you can choose from an array of different security modules, and I think most interestingly, use different models based on what your users are doing, right? So if you think about, you go to the bank and you're trying to take out $100, well, they're really only going to ask for your PIN number, but you try to wire out $50,000, and now they start asking more questions, right? They want you to come to the branch. They want you to speak to a banker and answer 5 or 6 questions about recent transactions, the type of the account, some different security measures. What is the bank doing? The bank is using a different type of security protocol or security module, in this case, based on your action. And this is something that becomes available for us with the concept of modular security. And again, Hyperlane, we believe that modular chains deserve modular security as opposed to being stuck with the form of permissioned interoperability. As we advance the conversation, it's probably worth getting into different flavors of interoperability so that we can better understand how modular security stands out. Now, to do that, we'll start with perhaps the ideal form, the form that many of us would opt to use wherever it is applicable, and that is native verification. What does native verification really mean? At a high level, it just means that you're leveraging the existing consensus that exists between the chains that you're connecting. And most importantly, you're just not trusting any other thing or party other than chain A and chain B. Now first, let me say native verification is not magic, right? It does not mean you're going to have a secure interaction. It just means that if you're connecting A and B, as long as you are comfortable with the security on both A and B, what you're getting has no additional trust assumptions. But if something wonky is coming from A going to B, native verification just passes that along, and that's okay. Now, ideally, we in crypto, we want to minimize the trust assumptions that we have to take. So native verification, wherever applicable, is really great. The problem with it is that in certain environments, it is not quite applicable, because unless the environment was constructed to be able to support native verification, what does it really mean? It means replicating the consensus of the chains you're connecting on each other. So you would need to replicate A on B, you would need to replicate B on A. This is where like-client verification comes in quite handy. But what do we do where we don't have like-client verification? Well, replicating consensus without it is incredibly, incredibly costly to the point of being infeasible. So while native verification is something we'd love to use wherever we can, unfortunately, we can't use it everywhere, at least not yet. Now, not all hope is lost. There are advancements right now, things like zero-knowledge proofs that ideally should make the cost of replicating consensus and being able to have native verification in more locations, notably in the EVM, much more feasible. So it's going to happen eventually. We're not totally there yet, but again, do not despair. So if native verification is one flavor, what is another? Well, it's external verification. If in native we only trusted the chains connected, with external verification, we're now introducing a new validation mechanism separate from that of the chains connected. A third party. So we were trusting A, we were trusting B, and now we're trusting some C, right? Some external party. And if you're taking a look at this and you're like, whoa, I've seen something like this before, I know what this looks like. And you're thinking about oracles, yeah, you're right. Like external verification boils down to being no different from the oracle problem. If you think about the issue of connectivity with blockchains in general, the fact that they don't know anything about information and data that's not endemic to them, well, again, that is the core issue at the oracle problem. But whereas generalized oracles are trying to solve a general problem, being able to fit any data regardless of source, in an interoperability, we have a much more narrowly focused oracle problem where we just want to sort of oracleize data and state coming from other chains. So there are many possible configurations in an external verification realm. The external verified system could just look like some type of proof of authority or a multisig, where we have an actor or group of actors that we trust and we are comfortable with them and their validation results. It could look something more like a proof of stake system. And here it's important to note that these proof of stake systems are very different than proof of stake consensus and say like in Ethereum, where we use proof of stake to decide on processing of blocks. Proof of stake in an external verification system is very, very different and very important because it can actually have devastating results if collusion or malicious activity is happening, because the other end, if you're connecting between A and B and you're doing it through external verification using proof of stake, whatever B receives from A is completely dependent on the external verification system. So if you use proof of stake and those validators are telling you that the sky is blue, even though you think that the sky is red, like it's blue from all intents and purposes, right? So if they are misleading you about the state, then that is all you know. There is no way for you on B to be able to verify that that state is incorrect. And there are some very interesting implications to it, and this is why, generally speaking, there are two modes for proof of stake in an external verification system. One where the stake is concentrated in a single chain, and then that value is put at risk for every other chain that's connected, and another where the stake lives on each chain, and there are different benefits to each one of these configurations. In the first configuration, again, the stake all lives in the same place, so you get the benefit from some economies of scale, from some concentration. But what happens when a punishment is needed to be issued, right? When slashing needs to happen to one of the validators, their stake lives somewhere else than where the offending incident happened, right? So say they're connecting between A and B, the stake lives on a chain that is C, and we need to communicate back to C about this incident that warrants some slashing. Well, how could we do that? Unfortunately, the only way that we could do that is through the same system. And so in a case where just one, you have one bad apple, presumably the other actors, the other validators would want to weed them out. And so staking would be ensued. In this case, staking cannot be executed permissionlessly. But what do you do if all the validators, or a majority of them, are colluding? Well, why? They're not going to rat themselves out, right? So punishment really can't be issued through slashing in a system where the majority of validators are colluding. And in that case, there is a complete breakdown of security. Now, to the defense of these systems, this has never happened before, but certainly it's a theoretical concern that is worth worrying about. Now, in the other case, you do get permissionless slashing. You're always able to prove, and you're always able to punish an offending validator, and you can do it again permissionlessly. You don't have to depend on any kindness from the validators, nor do you have to have some type of honest majority assumption, as you do in the case where the stake lives on a different chain. But what's the drawback, right? Like, you now separate the stake, and it is no longer concentrated, and you lose out on some economies of scale. Another configuration that you get in external verification systems is an optimistic instruction. Think of this as being somewhat similar to the optimistic bridges that power things like optimism and Arbitrum, but the key insight here is you put some type of delay on the processing time, and any message that is received is not going to get processed until that time has surpassed. And during that time, anyone can run a watcher or some type of software to check the validity of the transaction, and if something looks invalid, submit a fraud proof. Of course, with external verification, there's a lot more configurations that you could get. We are probably going to see more in the future, but for now, I think we've summarized all the major ones. So now let's get back to this world of modular blockchains. So with modular blockchains, we're going to end up with a lot of hubs. What does it really mean to be a hub? I think of hubs as places that entice the formation of new rollups, and where those rollups are settling back or sending back something to them. It might be using them as data availability, as in the case of Celestia. It might be settlement and sometimes even different forms of execution, as is in the case of Ethereum. But ultimately, in my view, a hub for modular blockchains is something beyond which activity concentrates and leads to the creation of more and more rollups. So why do they need permissionless interoperability? Because as we touched on before, these hubs are going to lead to the creation of more and more and more and more and more rollups. And again, the creation of these rollups is going to happen seamlessly. It's going to happen with decreasing amount of clicks and decreasing amount of time on the account of their operators, of their deployers. And so it seems completely infeasible that permission solutions will ever be able to cater to this world of modular blockchains, where we are probably going to end up with, on the lower end, if we're successful, thousands of rollups. So permission interoperability is not going to work, right? We covered that. Hopefully by now it's pretty clear why modular blockchains and permission interoperability are like oil and water. They're just not going to feasibly mix with each other. Permissionless interoperability, we only covered that. We covered the concept. We didn't really tell you how is it going to work. So with that, let's get into Hyperlane. I promised before, we'll tell you how it works. Now it's time to do that. So in this visual, you can see the entire Hyperlane system as it connects between two chains. Here, we're actually seeing the life cycle of a message as it progresses through Hyperlane, and going from its origin all the way to its destination. We're going to walk through this. Before we do that, you should understand that for Hyperlane to be supportive of a new environment, three things need to happen, or really you could say there are three layers or three levels to a Hyperlane connection. The first is the mailbox. The mailbox does exactly what it sounds like. It is a contract that sends and receives information between chains. The second are the security modules. You need to configure the security, and there needs to be something in place that allows for the state being reviewed and sent from chain A to chain B to be secured. Really, all a security module is some wrapper on something that makes you comfortable with the state that you're receiving from another chain. So that's the second level of security. The third is the relayer. The relayer is a permissionless agent. Anyone can run a relayer for their messages, but a relayer is like this off-chain bot that observes the mailbox, and if it sees that everything looks fine and the transactions look okay and valid, it will take those and process them on the destination chain. So now that we covered kind of the high level, let's get into the life cycle of a Hyperlane message, and it'll help us understand how Hyperlane works. So we have some contract that wants to send something to another chain. It constructs the message and it sends it to the mailbox where it encounters dispatch. Dispatch is the primary function that you'll be using to send information from Hyperlane to another chain. Dispatch takes in the message body, right, the bytes that you want to transfer over. These bytes can have something as interesting as an interchain function call, a extension or sending of assets, to something as not interesting as a message to say something like, "Hey John, how are you doing?" I would advise you to do that, but certainly you can. It also takes in the domain ID, that is the destination chain that you're sending it to, and the receiving address. Now, once that message is received in the mailbox, it needs to be reviewed in some way. It needs to be signed for it to become valid for it to be sent off. So in this case, we could have some type of validators, as we talked before, and we might have a module that uses validators that might be either a multi-sig type of situation, it might be a proof of stake situation, or we could have an optimistic situation, again, as we talked about in the external validation case. And so all of these combine to basically provide something that then creates some type of validation for this message being acceptable and ready for processing. After that's happened, we now move to chain B, the destination chain, where again, the interchain security module, or the ISM, this is in Hyperlane lingo, this links back to either those validators or those watchers, again in the optimistic case. And before that message can be processed, it needs to be relayed. So a relayer looks at that original mailbox, and if it sees that it's been validated by some validators, or that the amount of time, say on the optimistic case, has passed and that message is ready for processing, the relayer will then take that over to the mailbox on the destination chain, where it will initiate the process function. As it does that, now the final logic tests that come in from the interchain security module are tested against, and if everything clears, right, if there is a valid signature from a validator, or we find that there has been no fraud proof submitted, right, the integrator of Hyperlane decides which security modules to use and how to define their logic, and as long as those tests pass, the message can be ultimately sent off to its destination. Importantly about Hyperlane, you can totally have a case where the message is included in a block on the destination chain, but never arrives to its ultimate destination. Why is that? Well, the relayer doesn't know yet whether the message being sent will actually pass all the logic tests of the security module. It is totally feasible that the relayer takes something, begins its processing, but then because of the security measures put in place by the integrator, it just doesn't pass. That is by design. And so certainly we can end up with a case where that message is, again, it is a transaction, it lands, and it is included in a block on the destination chain, but never reaches the receiving contract, again, because it fails the logic tests through the security modules. Okay, so now that we've covered that, let's take the next step and do a deeper dive into the concept of modular security. So I told you before, Hyperlane, we believe that modular blockchains deserve modular security. We touched a little bit on what modular security means in the context of Hyperlane. And I think, if you want to have some fun with it, I think an explanation that works for kind of like a smooth brain like myself is think of a security module, or in Hyperlane parlance, an interchain security module, an ISM, is really just some type of wrapper that wraps logic that helps you get comfortable with the state that you're receiving from a chain you're connected to. And this can take many, many, many different forms. It can take the form of some type of economic security where the logic is, hey, I'm putting this amount of money at risk, and if I misbehave, you can take that money away from me, you can slash me. That's one form of an economic ISM. It can take the form of optimistic logic, where you will accept that message only after a certain amount of time has passed. During that time, anyone could have observed that transaction and see, like, does it look okay? Is this a valid state transition? Optimistic systems could even go past just valid state transitions, because if you think about it, majority of exploits in the category of interoperability, they all look like valid state transitions. So an optimistic system actually could go one step further and not just be limited to fraud proofs and valid state transitions. Rather, it could just be sort of like a veto system. In MakerDAO, we have this concept of the emergency shutoff, or at least that's what it used to be called. Maybe it still has that name, where maker governors can kind of unwind the system in the event that they think something malicious is happening. That's never really been an issue so far, even though existing for multiple years. It's perhaps only been an issue on governance forums, but in practice it has not been abused, and it could be a really great defensive mechanism for MakerDAO. So why shouldn't there be optimistic systems that allow their operators to veto certain transactions if they feel that they are malicious or in some way are going to hurt the protocol that's integrating them? What does this really look like in practice? Imagine now there's an exploit trying to drain funds from a protocol on one chain and send those to another. Well, that transaction then would not get processed because it would go through the optimistic module. And during that time, there would be the option for people involved in the operation of that security module to veto it, to basically block it, prevent it from ever happening. While this could certainly go against the ethos of certain people, feeling that you should not be able to censor these transactions, but realistically speaking, wouldn't we want to censor exploits, right? And so an optimistic module could also allow for that. And then we also have something that could look more like a multi-sig module, right? Like where we trust a certain set of actors, right? Imagine if you're going to be using something like Circle's CCTP. In effect, what you're doing there, think of CCTP as a system in which the security module really is a Circle multi-sig. You are trusting that Circle is going to do this correctly. And of course you are. You're using CCTP to use USDC. So it's inherent. It is, at minimum, it's implicit that you're trusting Circle when you use that interaction. Now, if an ISM, an interchain security module, really, if all it is a wrapper on some logic, then the beauty of it is that while this looks like an external verification system, it can actually just be narrowed down to a native verification system where it exists because all it is, again, it's wrapping some logic. So certainly it could wrap the type of light-line verification that has been used for protocols like IVC. It can wrap some type of zero-knowledge proof. Really, you can use it, again, for any type of arbitrary logic that makes you comfortable with receiving state from another chain. And this is why we believe that modular security is the path forward for modular blockchains and when it comes to their interoperability. Most importantly, is what enables them to operate permissionlessly. So with that said, let's talk about the differences in bridging normally and bridging with a protocol like Hyperlane. So first things first, you can definitely use a regular bridging mechanic with Hyperlane. And what does regular bridging mechanics look like? Generally, they look like an omnibus bridge, a single contract where all the assets are deposited. And that contract creates wrapped assets that then go to the destination chains. So what's it look like? Well, you get all of the assets deposited into a single contract, ends up kind of looking like a honeypot, and all of them have the same security module. Now, if you did construct a regular bridging paradigm using Hyperlane, one key difference you'd have is you'd be able to utilize different security modules for your omnibus bridge. But is that really interesting? With Hyperlane, we would recommend a modular bridging approach. And in our lingo, we call these warp routes. And warp routes are unique because warp routes are unique per asset. So each asset gets its own warp route, and warp routes get to benefit from the modular security features and from the permissionless features of Hyperlane. So anyone can create a warp route permissionlessly and then assign the different security modules they'd like for that warp route. And now the assets can traverse to any chain that they would like. The tokens that are minted by a warp route are what we call in Hyperlane interchain tokens. Now, an interchain token is interesting because it does not have a canonical home. It's not an ERC20 that only lives on Ethereum and then is represented elsewhere. Rather, its home are all the chains that you configure it for. And at the moment of transfer, it's not another wrapper that's being created. Rather, it is being burned on the origin chain and it's being minted on the destination chain. So that's that for with the limited amount of time that we have. We don't want to spend too much more time on this concept of modular bridging. If you want to learn more, at the end of the talk, I'll leave information for how you can contact us and learn more about all these things. But certainly just look up Hyperlane work routes and you'll be available to learn all the information that you need. Now let's get into some other use cases that you can affect with Hyperlane. I actually should have probably spent more time on this because I find these much more interesting than just bridging, but bridging is usually the first use case that modular chains have because they need to be able to import economic activity, assets, people from other chains. So that's what we cover at first. But what are some other cool things you could do with a protocol like Hyperlane? Again, because you have generalized message passing, you're able to affect any type of interchain activity. You can go ahead and create interchain swaps where you can imagine pools of assets living on each chain and the assets being swapped without ever having to be bridged or wrapped. Hyperlane also supports the concept of interchain accounts. Imported over from the realm of IBC, or I should say inspired from the IBC realm, interchain accounts are really cool because they allow you to have a contract on one chain, be the ultimate owner and controller of contracts on other chains. You could think of this really as like a smart wallet, or we used to call them remote identity proxies. But with interchain accounts, something like a DAO on Ethereum can own all the sub-DAOs. It could be like a parent of the different child DAOs, and thus when there's a governance update, it can be pushed into all those accounts. An individual user's smart wallet can be an interchain account, and really there's no end to how you can use interchain accounts. Perhaps these last two really are my favorite use cases, but with a system like Hyperlane, if you think of what are some of the things that are immediately necessary when you launch a new chain, well, first you need to be able to bring in assets. Well, the modular bridging we talked about solves that for you. Second, you might need to have access to some data feeds. You need to oracleize some data from somewhere else. And so with a system like Hyperlane, you can create a stream of oracleized information from any major chain where you trust the validity of that information. So you could import Chainlink feeds, you could import Uni TWAP feeds, whatever type of information you need to oracleize. You can do that via a system like Hyperlane. And last but not least, my favorite use case, interchain margin. If you're building a derivatives protocol, take this into account. What are your objectives? Your main objective is to have more healthy trading volume. Well, that is a function of assets that you have collateralized, the amount of traders, and their willingness to trade. With the concept of interchain margin, you can increase the amount of assets you have collateralized, because now, for the first time, traders don't actually need to bridge over into your chain. Rather, they can leave the collateral at home, deposit it into a contract of yours on its origin chain. So say you have ETH, the ETH can stay on Ethereum. You have AVAX, the AVAX can stay on Avalanche. Atoms to stay on Cosmos, etc. Because as a derivatives protocol, what matters to you is simply the ability to liquidate and take control of that collateral once it's been margin called. And so you can do that with a system like Hyperlane. And so I'm very excited to see some derivatives protocol coming up and building with Hyperlane to create for the first time this concept of interchain margin. What's the end game for Hyperlane? Well, it comes down to these four things. I think it's all about inter-rollup networking. So being able to switch between, not only between different individual rollups, but between different rollup networks. I think of those hubs that I talked about before, each hub existing as a sort of rollup network. Well, we need to communicate between those as much as we do within each one of those. And others, relaying services. Today, when people use Hyperlane's permissionless interoperability, they're primarily running their own relayers. I'd like for that to remain the case indefinitely, and certainly the entire Hyperlane community is supportive of relayers always remaining permissionless. This is part of our grand vision. However, being able to offer relayer services for those who do not want to relay their own transaction is quite important, and for that to be a seamless process is something that should be coming sometime in the near future. Additionally, as Hyperlane matures, we believe we'll see a security module marketplace. We're already seeing new operators of ISMs come online. Most interestingly, right now we're seeing some zero-knowledge proof operators beginning to build systems with Hyperlane to create security modules that are secured by their zero-knowledge logic. And lastly, Hyperlane is a wonderful system to express and execute on interchain intents. And so right now, several things are being built to allow for that. And that's something that we are very excited about. So that really was all I had, all the time I got. And I'd love to tell you more about Hyperlane if you want to learn more. You can go to our docs at docs.hyperlane.xyz. You should join our Discord. It's just discord.gg/hyperlane. You should feel free to follow us on Twitter at hyperlane_xyz. And you can always reach out to me on Telegram at PaleNimbus or my email at john@hyperlane.xyz. So thank you, everyone. I had a wonderful time speaking to you today. And again, don't hesitate to reach out.
My name is Neel, and I'm the founder of Eclipse. So for this presentation, I'm going to just go through one slide deck, which basically explains some of the technical things that we think about at Eclipse and how we're approaching them. And then we're also going to get into what we think are ideal use cases for app-specific persistent rollups, such as what we're building at Eclipse. So I'm going to go ahead and pull up this deck here. All right, so this is a technical explainer, so it assumes some knowledge of what rollups are and things like that. So this gives a little bit of context on what were the scaling solutions that historically existed. One being you have alt L1s like Solana, you have what was previously Terra, you have a bunch of Near, Aptos. So these are all basically new layer 1 blockchains that do their own consensus, and they also handle execution and the other functions that a blockchain typically does. And then you have, in that same vein, in the sense that they're trying to find a scalability solution that provides a general purpose chain for everyone, you also have rollups or traditional rollups. That's like Arbitrum, which is anchored directly to Ethereum. They have a canonical bridge contract, and then they do a bunch of execution off-chain and eventually commit that result back to Ethereum. So these are shared chains, and I grouped them together because you might think that it makes more sense to group the alt L1s with app chains, which I'll get into next, and then rollups would be its own category. But in our opinion, the way that these are grouped and the reason why we've grouped them this way is because you have a shared chain, which is inherently non-customizable, but it's highly convenient. And on the other hand, you have an app chain, which is extremely customized. But in order to spin up like a Cosmos app chain or a Polkadot parachain, you have to typically, in the case of Cosmos, you have to bootstrap security, meaning that you have to get a validator set, you have to put up stake. And in the end of the day, your fixed cost for running this chain ends up being 7 figures or more, as opposed to using something like Solana or one of these shared chains where your fixed cost is basically 0. You don't have to run any activity if you don't want to. But now you have this marginal cost, which is whenever a user runs a transaction, they have to pay some amount in rent. So you're basically paying rent to this shared chain, or you're trying to roll it your own and be a homeowner. So the question is, given that app chains give so much more customizability, they give a lot of dedicated throughput, why did they not take off? And our answer is that it really comes down to convenience. And it's really difficult to spin up an app chain as it exists right now. The other part of it is that you end up with security fragmentation. And we'll get into that. So these are the properties of rollups that we really like, and we want to borrow that. So that's what we're offering with Eclipse. In the same way that AltLayer offers these temporary rollups, which are intended as burst capacity, Eclipse offers a permanent rollup. And this is intended to be app specific. We support some chains that are not app specific, such as what we're doing for Injective or Polygon. But a lot of our chains, probably over like 90% of them, are dedicated to a single app, and they build in customizations that make sense for their application. So this is just a thesis on what this will do to value accrual. Once a bunch of apps are on their own layer 3s, and layer 3 is kind of a term that's a little bit fraught because typically like L2 implies that you're using Ethereum for a DA and you have a bridge contract there, which is not what an Eclipse rollup looks like. So instead, we'd want to separate it a bit and we'd say its own execution layer. So when you have an app that's on its own execution layer and it's free to switch a DA layer, then that basically forces the data availability layers into competition with each other, whether it's Ethereum or some other DA layer. And that's good for the app because it means that the layer one doesn't have as much pricing power. So historically, the FAT protocol thesis was basically that if you're an app on a layer one blockchain, people will speculate on the layer one blockchain if your app succeeds. And therefore, the layer one blockchain will get a lot of the upside, even if you're an app that's very successful. Whereas when you're on your own chain, you can capture a lot of that value yourself. So that's one of the big values of being on your own chain, in our view. So these are some of the design trade-offs, because what we want to do is offer customized rollups where you can pick a virtual machine, you can pick a base layer, and sometimes you can pick some other features such as a customized gas token or custom block times that are suited to your type of app. So how can we provide that in a way so that we don't have to do everything in a one-off manner? We don't have to do something that doesn't scale. So the first question is, how do you offer multiple bytecodes? We want to offer EVM and we want to offer SVM. In the future, we want to offer MoveVM bytecode or possibly something else. So there's a few different ways we could do that. One is we take an existing rollup framework and we basically implement an entire virtual machine within it. And that's actually something we might do with Sovereign Labs, where we take the Sovereign SDK and add in, Solana has the virtual machine implemented as Solana RBPF. Of course, then you lose that's more of like a bytecode interpreter rather than a highly parallelized virtual machine. But my point is that you basically have to take this for every bytecode. You take the rollup SDK, you implement the new bytecode, and you get it working with the rest of your systems. Hopefully, the settlement for whatever rollup framework you use is built generically so that you can support arbitrary VMs like that. Hopefully, your bridging doesn't need to be rebuilt substantially, but this ends up not really having a lot of. There's no like wave that you can ride. There's no one else who's going to be doing this work for you. You're going to basically have to re-implement all of this yourself. Similar in that same vein is ZK Sync and what they did with the LLVM intermediate representation, where they basically compile everything down to this IR. So they did this with Solidity, with Yule, with a bunch of other languages. And that's nice because it's one general intermediate representation that you can build all of your infrastructure around. But the downside is, again, you have to kind of do this all in like a one-off way. You have to compile everything to this IR. So what we did was we basically picked the Solana VM largely for this purpose, which is that, one, it's highly parallelized, so you get a lot of throughput. But two, it's already on the path to supporting multiple bytecodes. And most of our chains are actually EVM, and we support that by using a project called Neon on Solana. Solana obviously supports its own bytecode, which is sometimes called SBF, Solana bytecode format. And then we have other bytecodes that are on the way, like MoveVM. So this is a huge advantage in the sense that we get local fee markets, we get all the tooling that's built for the Solana VM. It's a very powerful execution layer, but the downside is it's really not built to be a rollup. So we have to do things like insert a sparse Merkle tree. We have to sometimes change some things about how in the future, we might have to change the mempool in order for it to work with shared sequencers. So these are all things that we have to make, like we have to roll on our own. All right, so now the next question is, how do we do settlement? Should we do a typical smart contract rollup, which would be on Ethereum, and that would be the smart contract that determines the canonical chain? Another option is you make it do sovereign settlement. So somehow you pass proofs directly to like clients. And one big advantage here is verifiability. The advantage of being on a smart contract on Ethereum is that people say it's trust minimized in the sense that if you run an Ethereum full node, then you know that whatever state that Ethereum full node contains is a correct state for the rollup as well. But that only works because running a full node on Ethereum is essentially running a light client for every single rollup on Ethereum, because that smart contract bridge is a light client. So alternatively, you can just write like a settlement. You can run a rollup that directly passes those fault proofs to a light client that your community or your users run, and they can directly verify the correctness of the rollup. And then the last option is actually what we ended up going with, which is we have everything deploy as a one event trust assumption smart contract rollup onto a shared settlement layer. So that's nice because you get that trust minimization with respect to the settlement layer, where anyone can submit a fault proof. In the case of it being a ZK rollup, then you can just validate the ZK proof within the settlement layer. But then the settlement layer itself is a sovereign rollup. So the settlement layer passes fault proofs directly to light clients, and in the future, the settlement layer will be a ZK rollup. So that's the design that we ended up going with. And it also gives us a lot more ways to build in convenience features for our rollups. For example, you can imagine a world where you don't want to move your liquidity between every single Eclipse chain. So instead, you just leave all your money on the Eclipse settlement layer, and you have you use account abstraction or something to sign transactions for these different chains. And then someone relays those transactions and they get compensated on the settlement layer. Or you could use a settlement layer as a sequencer set. So that's the idea behind why we have the settlement layer. You don't have to use it. You could theoretically run your own Eclipse chain, run the sequencer yourself, but then you're lacking a lot of these network effects. The next question is, how are we going to get from an optimistic rollup to a ZK rollup? We built the fault proof ourselves in-house, but we really didn't want to build a full ZK VM in-house because it's a lot of work and it's kind of an arms race in the sense that we'd have to continually update this virtual machine. So we really didn't want to build our own in-house one. So we looked at a bunch of existing ZK VMs or ZK proof systems as a service, and that's things like RISC-0, that's like Axiom, Neel Foundation. Ultimately, we picked RISC-0 for the reason that it's highly portable. RISC-V bytecode is pretty generic, and we could probably switch to something else down the line if we really needed to. But the RISC-0 team is also interested in working with us. And we found through our cost benchmarking that it ends up costing about 10 cents to prove a non-trivial transaction. And that's without any additional optimizations. It's just using straight RISC-V bytecode. And what I mean by that is we take a Solana program, and rather than compiling it to Berkeley packet filter bytecode, which is the normal bytecode for Solana, we compile it to RISC-V bytecode instead, and we run that within the RISC-0 virtual machine. So that's a high-level implementation. In the future, let's say we wanted to cut down that cost even more, we might natively implement the BPF circuit, and we can still reuse RISC-0's proof system. So this is just summarizing what I just went through. This is on decentralizing the sequencer. This is enough of an open question that I won't go into, and I want to start getting into the applications that that we're able to support. So I'm going to just gloss over this. This is stuff on wallets, bridging, and this is the application part. So this is a case study on Worlds. Worlds is a game that's building on Eclipse, and they basically use the blockchain as an open API. So they write a bunch of read-only data onto the blockchain. These guys built Unreal Engine 5 previously, so they're really hardcore game developers, but they see the purpose of the blockchain as a highly composable API where players in the community can build things like financialization on top. They can build their own primitives. They can build their own user-generated content. But you also have this like base read-only primitive, which people can use and compose on top of. So that's what they're doing. And if you think about it, they're already conceding that to some degree, this is centralized because the company themselves is acting as the oracle. They're signing off on the data that's being posted to the chain. So they don't really care about the base layer being decentralized. Right here, I have Celestia written as the DA layer. But actually, in practice right now, we just have them on centralized DA because it's a very high volume of transactions and they're very low value on average. So that doesn't make a lot of sense for them to be posting and paying money to an actual decentralized DA layer, at least in these early stages. So that's what the base layer looks like. The sequencer itself is centralized because they don't really need to have a sophisticated decentralized sequencer setup. And this is a very consumer-oriented chain. So they even take USDC for gas. So that's the setup of a consumer chain on Eclipse. This is what we're doing for Worlds. We're doing this for a handful of other projects like Gridiron, Bullaverse, Ether Games. We have Social Future on the social side. So it's basically like a highly centralized chain that supports extremely high throughput, but it can compose with a bunch of decentralized chains on the side. You can build your own primitives on top of it as a community, and that's how they use the blockchain. And this is just a way that we think about different types of applications. This gaming template is more like a general consumer template at this point. And as you can see, it's running the SVM, but it's actually running EVM bytecode within the SVM. This is not actually what our DeFi template looks like, but we're still hammering that out with some of our DeFi design partners. We do a lot of SVM rollups for layer 1 blockchains. So this, we're still thinking about how we're going to incorporate into our self-service offering. But basically, you spin up a chain that has a custom data availability layer. So it posts blocks somewhere, and then Eclipse needs to also know how to read those blocks as well. So this might require, in the future, maybe teams would make a PR against the Eclipse code base. They'd show how to post and read from some new DA layer, and then they can spin up an Eclipse chain that does that. And then we do a bunch of DePIN projects, or decentralized physical infrastructure networks. So that's like a React, Wave, Wind, IoTex. These guys are taking real-world things and they're doing some work off chain, and they're able to prove that it happened on chain. And then they can incentivize people to participate in the network via some tokens, such as what Helium did. They can take that data, they can optimize it so that they can save you money in the real world. They can sell the data. There's a bunch of different business models that you can do once you have that all on chain. So this is just a bunch of other more fringe use cases. And that's pretty much the stack. So that's the first presentation that I wanted to get through. And I think we have a little bit of extra time. So I'm going to go through some more detailed case studies. So I'll go ahead and pull up this case study, which is just a deeper dive into worlds. And what I want to drive home here is that for a consumer chain like a game that's posted, if it's fully on chain, posting something on the order of hundreds of thousands or millions of transactions on chain, then even if they're paying something like 10 cents a transaction, that's probably prohibitively expensive for them. And why would I even say 10 cents? It's because if you look at the Ethereum DA cost, which is a fee market, it ends up being about 10 cents to post 200 bytes to Ethereum. And then maybe you'd want to charge a little bit of a markup on that because you have a fixed cost associated with running the sequencer for your rollup. So maybe you charge like an additional 2 or 3 cents per transaction. So you'd end up paying something like 15 cents per transaction. So you'd have to ask whether users are really comfortable with paying 15 cents per transaction and whether it's worth it for them to post millions of transactions on chain, given that the value of these transactions is pretty low. So given that structure and given the economics of it, it doesn't really make sense. And we'll see what the fee market on Celestia ends up looking like. But in practice, this kind of chain should use some sort of centralized DA. And in the future, once this is a ZK rollup, it's probably not that big of a deal either. It's essentially a Validium construction. And by centralized, you could do a DAC, like a data availability committee. You can make it quite affordable to have data that theoretically could be withheld, but at least you get guaranteed correctness by virtue of the validity proof. So that's what we have as far as how we've been thinking about gaming and why our setup makes a lot of sense for games. We let people pick the DA solution. So if you do have higher value transactions, then of course you could use a decentralized DA. It's EVM because they wanted that portability. They don't mind a centralized sequencer, and then they want to use something like USDC for gas. So they've demoed their game at a couple of our game nights. We had one over in Denver. We had one over in San Francisco at GDC. And if you're building a game, then we'd love to chat with you because we can likely arrange some similar setups with you. Okay, so that's Worlds. And then let me go ahead and pull one up for Injective, since this is another one that we're pretty public about. So Injective's chain is called Cascade, and this is a Solana virtual machine chain that Injective runs. So they're a layer 1 blockchain. Injective supports WebAssembly programs. So it's Rust as well. But let's say a Solana program wanted to deploy to the Injective ecosystem. They'd basically have to rewrite a lot of their logic. So by having an SVM chain, Injective can basically promote these projects or they can encourage them to deploy to this SVM rollup. They can easily deploy and they don't have to rewrite any smart contract logic. And then that chain charges Injective's native token for gas. So that's like the high level on how the value accrues back to Injective. Of course, they also have an IBC connection back to Injective. We're working around some other stuff they want to do with the sequencer, whether it's by adjusting the block time. They might want to use a shared sequencer, such as Espresso. But this is the high level setup of what these rollups for L1s typically look like. It's bringing them a new execution layer, and it's charging gas to their native token. So soon we're going to be actually deploying an EVM chain for Injective as well, because they want EVM compatibility. So this setup is pretty general. So there's probably not as much to cover on this one. We gave a couple of options for them initially, because this was one of the earlier L1s that we ended up working with. Since then, we've engaged with BNB Chain, Polygon, Near. We are spinning something up for Nibiru. There's a few other Cosmos chains which we're still in the works with, and we haven't quite finalized what that would look like. But we've basically done this a handful of times. So that's what we've been doing. Been doing rollups for L1s, been doing games and consumer, and more recently we've been entering DeFi. That's the high level on what Eclipse has been doing, and feel free to reach out if you have any questions.
Hello, hello. My name is Evan Forbes. I'm with Celestia, which is the first blockchain network. And on Celestia, you can build whatever. So if you're interested in anything that I talk about in this talk or in my work in general, you can find me on Twitter. I'm Evan S. Forbes on Twitter, or on GitHub, I'm just Evan-Forbes. And today I'm going to talk about trust minimized and impact maximized rollups as a service. And the thing, I might get a little opinionated here, a little political maybe even, but I hope that adds to the spiciness and like maybe just the general entertainment that we can get from this talk. And the entire thesis is, with this trust minimized portion, is that sovereignty, not just sovereign rollups, but sovereign blockchains in general, are actually the difference between what has come before us with like banks, governments, Web 2, and crypto. I know that's a little spicy, but I do think that there is some truth there and there's some value there. And I think if we critically think about it, we can design rollups as a service. We can design these services that help build these rollups and do so in a trust minimized way. We can preserve that property and perhaps unlock something really, truly special and get to some insane, crazy properties that I don't really think have ever existed before. That's really exciting. So anyway, the first start answering that question is we can get to what actually makes blockchains compelling. What actually makes blockchains special? Not necessarily the protocols built on top of the blockchains, but the blockchains themselves. Why is Bitcoin special? Why is Ethereum special? And I think it comes down to sovereignty, where the ability to verify, right? Don't trust, verify. The ability to verify these chains. I can verify Ethereum on a laptop. On Bitcoin, it's probably something even significantly smaller. I can choose the rules that I follow. I'm not trusting another committee, right? We're building a network from the ground up, and we have this like sort of crypto anarchic promise and this like property that is to build a network, to build a structure that is resistant against abuses of power and hierarchical structures. That's crazy. That's a really special property. And right, and the title of this talk, Impact Maximized. We don't want to just do the same things that we did before. We don't just want to have the banks, but faster and a little bit more decentralized and a little bit more permissionless. That's good. Having these permissionless, decentralized systems is really good. But if we're still trusting committees, if we're not actually verifying, then we're not the ones who are choosing the rules, right? We choose the rules that there's only 21 million Bitcoin. We choose the rules and we enforce them for Dogecoin and for Ethereum and for all of these other blockchains. We enforce the rules. And I think that's what makes things special. So when we're designing rollups as a service, how can we even capture that? How can we amplify that? And so to get to more of like this sovereignty portion, I think Mustafa Al-Bassam, he's the CEO of Celestia Labs, co-founder of Celestia Labs. He's done a lot of work. There's a paper published, Data Availability and Fraud Proofs, and of course, Lazy Ledger, which is now Celestia. And he framed this, I think, summarized it perfectly. Sovereign blockchains, not just rollups, not just modular blockchains, sovereign blockchains allow people to create social contracts and enforce them directly without going through any intermediary. Top-level social contracts, right? This is a crazy thing. This hasn't existed before. This is the new thing of blockchains. This is the thing that makes them different from what came before. We should amplify this to really create compelling services for rollups. And being able to verify the chain choosing the rules ourselves, sovereignty, being able to hard fork. This puts people over tokens, people over validators, people over governance, right? This property is really something truly special. It's not just token holders who get to make a decision. It's node operators, people who are verifying the chain. And to better answer this question, we can even ask, like, why do banks and governments suck? Why does BlackRock suck that BlackRock owns everything? And this funny cartoon of this Futurama representation of Richard Nixon, who is known to abuse powers, right? Why do blockchains suck? Or why, sorry, not blockchains, why do governments and banks suck? And it's mainly because we can't really pick the rules. And these banks and these governments, they have monopolies. They get to decide what actually occurs. Now, in theory, it's like a democracy and people get to decide, right? But in actuality, things start to get messy really quick. I mean, just like go look outside. A lot of the reasons why a lot of people are attracted to the space is because they are so easily disillusioned with how the current system works. Right? I don't really need to explain it. Satoshi didn't, when they made Bitcoin, their whole idea was to make a currency that was controlled by people, right? This crypto anarchic property. And their social contract is 21 million. It's only ever going to be 21 million, right? This means in the world, right? The Fed has this infinite amount of money. Can I pause this now? Oh no. The Fed has this infinite amount of money, right? They can do whatever they want. They can enrich themselves in theory if they want, or they can design whatever type of society they want, and we don't really have a say. So then this is this whole meme of like this money printer and everything. That's what Satoshi was going against, at least I think. And I think it just reset the talk. No, I think I just had duplicate slides. Sorry about that. Okay, so what actually makes blockchains compelling? That meme, I think, summarizes it up sort of, is that we can go against that. We can design our own money. If we want to print money, though, we can. That's the crazy thing. It's like the rules are arbitrary. They're programmatic. We get to pick them by verifying the chain. So this is where modular blockchains come in. This is where rollups come in. Is rollups make it orders of magnitude easier to verify the chain. Orders of magnitude. This is what DA and rollup solve. And they do this in a trust minimized way. And right, this enables two things. This enables sovereignty, which is fundamentally derived from verifying the chain, right? Sovereignty, the ability to hard fork. We pick rules, node operators, and in this case, with modular blockchains, light clients pick the rules, right? I can run a light client on my phone. I can verify the chain. I can pick the rules and the result of those rules, right? Not just the rules, the result of those rules from my phone. And people all over the world can do that. That's the crazy thing. That's sovereignty. And security, right? Normally, when we think about proof-of-stake blockchains, we think about committees of validators. Well, guess what? Getting committees of validators to operate in an honest way is very difficult because you have to stick enough capital in there in the blockchain and lock them up and have it socially slashable. It's still secured by social consensus, but it's socially slashable funds. Those funds have to be larger than the funds that are in the blockchain, kind of, because otherwise, if it's more profitable to attack the blockchain, it's like, ooh, that might actually happen. So that's why it's like, this is a really difficult property to get committees to actually behave honestly. That's why we use proofs instead. With modular blockchains, we use proofs. Committees are expensive. Proofs are cheap. They're also sovereign, and they're also extremely secure, right? Validators are cucks. The security of the chain comes from proofs. That's the beauty of like modular blockchains and rollups as a service, right? Rollups and modular blockchains are this powerful thing, but they're still missing a lot of pieces. That's where this Rollups-as-a-Service comes in, is this sovereignty, the security without compromises. We can, because the systems and how they work now, there's still like a lot of gaps. Like, how do I have decentralized sequencing, for example? Like there's just a lot of gaps still. And we can develop these services that still preserve the fundamental things that make rollups so special. And when we do this, we always have to think about things from proving from a light client perspective, right? All of this comes from the ability to verify the chain, in theory, from your phone, using some sort of light client. Just a light computer, really. But anyway, the point being to be able to verify the chain, okay? That means that everything that we think about, everything that we design has to be in those terms. How can I verify this using a light client? Honest majority assumptions are icky. Light clients, if they have to make an honest majority assumption, lose their security. They lose their sovereignty, because now it's not trust, don't trust, verify. Now it's don't verify, trust. It's backwards. That's what happens when light clients have to make an honest majority assumption. We don't want that. We want validators to be cucks. Okay, trust, minimize DA. This is harder than it sounds. I work at Celestia. I'm one of the core developers at Celestia, so I have a little bit of experience in building some of these systems. And trust minimize DA is harder than it sounds. For one, we have to have DA sampling. Okay, that's cool. I think most of us have a general idea of how that works. And then you have to have enough samplers, so you have to have enough network effects. You have to be convinced that there are enough other light clients sampling that you can reconstruct the block only using light clients if need be. Okay? Then you have to be convinced that the erasure encoding is done correctly. Okay, so we use fraud proofs for that at Celestia, but other chains you can use KZG commitments. You could just prove it in a ZK way. And it's not that, to be clear, Celestia could use those other mechanisms as well. Right now, fraud proofs, they're very simple, they're very easy, they're extremely easy to audit. They use normal cryptography that we've been using for 20 years, and they're extremely scalable. We can have very, very large blocks, unlike those other mechanisms, unlike the other ZK mechanisms, but not to get too distracted with that. There's also this thing that I'm pretty sure no other blockchain has, which is cheap inclusion checks. So it's great that, okay, as a light client, I sampled the block. That's great. I'm convinced it's available. I'm convinced the erasure encoding was done correctly. I'm convinced that there's enough light client sampling that we can reconstruct the block if we need to. But what happens if, now I still have to be convinced that the data that I care about, the rollup header, it has a hash, it has a commitment over some block data. How do I know that that block data is actually included in the DA block? That's kind of an important thing, right? Otherwise, none of that other stuff matters. None of it matters. It only matters if the data that I care about has been included in the block. How do you prove that? Well, typically, that's done using a Merkle inclusion proof. Okay, well, if we use Merkle inclusion proofs, what's the problem there? That requires you to download the entire block. Like, the entire point of a light client is that it doesn't have to do that. So you have to have significantly cheaper ways. And we actually do that in Celestia. So in Celestia, we instead of having to prove inclusion to the entire block, we prove inclusion to just the transaction that pays for that block. So apologies, I didn't really have a lot of time to put together these slides or a lot of visual aids, but you can see this is sort of how we organize the original data square in Celestia. At the top bit, we have this transaction portion. That's where all these transactions go. It's very small. I can prove just a single transaction was included. And that is good enough to convince me that the blob, the message, the rollup block for that transaction was also included in the same block. And we do that by getting a little bit clever. There's more information on this in our specs in the data square layout. I think like the rationale for this, of how we actually do this, but effectively, that commitment in the rollup header, we changed the way that we create that. Instead of just using a normal Merkle root, we use a Merkle root over subtree roots in Celestia. Because now, if you can find those subtree roots and you prove inclusion to those subtree roots, that's just the same thing. Because as a rollup light client, you don't care what the actual data looks like. You only care that the commitment that is in the rollup header has been included in Celestia. And because we have this, we have a special type of fraud proof that proves that some given transaction was included that pays for a block versus the actual blob in the block. We prove that if one is there, the other also has to be there. I won't go too much into how that fraud proof actually works. Again, hopefully by the time this video is published, our specs have been updated and all that information is there. You can find that if you just go to the Celestia GitHub, go to Celestia app, and then go to the specs. Sorry, again, I kind of had to throw these slides together rather quickly. And so we have trust minimized DA. Another thing that we need is that for rollups to be this magical dream of rollups as a service where I can just in one click deploy my own sovereign rollup, is I also probably want it to be decentralized. I want it to be censorship resistant. And shared sequencers are a way to do that. They're a way to scale that property. Because if we think about it, like if we have like the normal sequencers, we have to have a committee create the blocks if we want it to be censorship resistant. Or we can have backup mechanisms too, where I can force inclusion using the DA layer. That's a very good option as well. But if we want like the aliveness properties, if we always want our rollup to be alive, then we also have to have some sort of committee. So, but the idea behind shared sequencers is what if we can share that committee, right? So I've been thinking about how do you decentralize this? How do you decentralize the liveness properties, the sequencing of rollups since about last summer? Went through a few iterations, spoke with a lot of folks at Celestia, and eventually on winter break, I finally had time to write it up. And I wrote up this forum post. It's called sharing a sequencer set by separating execution and aggregation. If you're super interested in that thing, I would highly recommend, well, I guess that's tooting my own horn. Just go. It's a kind of hopefully okay description of this thing. It's not formally defined. Espresso Systems has also since published a, I think, more thorough explanation of these things. So you can also go and find their documentation as well. But again, the idea of this is rather simple. It's like we have the sequencing, we do that all combined, and then we actually do the execution later. So in my forum post, I referred to this lazy execution, right? We agree upon the transactions first, which transactions have to be included. No, not their order, just the transactions that have to be included. And then we execute them later, and then we actually do the proving. So this changes the proving a little bit. And I haven't, again, we're shipping mainnet. We've been really busy, so I haven't really had a chance to write up how this actually changes proving. But there's other people at Celestia, well, notably Gabriel, who has been helping me like sort of ideate around what can you actually do now that with like this lazy proving, right? So to get like a slightly better view of what a shared sequencer can do, the users, they submit their transactions or bundles of transactions directly to the shared sequencer layer. The shared sequencer layer can produce blocks as fast as they want. They don't have to wait on the DA. They don't have to wait like that 15 seconds or so for the DA. They can get this soft finality. So it's obviously not as good as firm finality, but it's pretty good. It's sort of like this gradient of trust. Like whenever the shared sequencer network gives you the soft confirmation. You sort of just treat it as a soft confirmation, and you can it's enough to at least update the UX very quickly. So you can have these soft, very fast confirmations. I don't really have to deploy my own sequencer set. This is incredibly easy. Like, I just define a state machine and like define a chain ID. My users just start using that chain. And then this is an important bit, the shared sequencer part, the shared sequencer network will post the entire block data to the DA layer. And this is sort of how this is the key factor of how they actually maintain trust minimization. Everything works the same as if a singular rollup was posting their block data to the DA layer. Everything's the same there because the shared sequencer is posting all of the block data at once to the DA layer. They're the ones paying for it. How you actually pay for gas for that can be kind of arbitrary. Ideally, it's done in the native DA token, but I think I'm getting distracted. So to elaborate more on this lazy execution, again, users can submit transactions. They get these fast, soft confirmations. They don't finalize the state yet, but it's usually good enough to update a UX, at least get that green check mark, get that dopamine hit, and then we actually post the DA layer. And then as soon as the DA layer has confirmation, as soon as we have that light client verification that I was talking about earlier, where the data was actually included, on Celestia or on the DA layer, now we have firm finality, which is kind of cool. Another really cool thing about shared sequencers is they have these validity rules that unlock powerful cross-chain MEV primitives. So this thing is like, I've kind of always thought about shared sequencers as this way for MEV searchers to use as tools to sort of build blocks in more or less a decentralized way. Now, I'll touch on that more later. That full picture is not painted yet. There's still like a lot of work to be done there, but I do actually think that it's possible. So stay tuned for that. But essentially, right now, all you really have is proofs of inclusion. So you do not have atomic execution. You only have atomic proofs of inclusion, meaning I'm only guaranteed that if I have a transaction included on rollup A, I also get a transaction included, not executed, included on rollup B. That's it. It's only proof of inclusion. But you can get more creative with this. This is by block validity rules. I can say on the shared sequencer layer, I can define as a block validity rule that these specific transactions only get included if they're included at both the top of the block, or one is at the top of the block, right? And that's sort of like a really powerful, again, these block validity rules that you can include with shared sequencers help. They're tools for building out more and more decentralized block building. At least that's my hope. But anyway, that's shared sequencers. And from like a rollup-as-a-service mechanism, I think that they're very, very powerful because they sort of give us this opportunity to think about like the services that we provide. Rollups can pretty much do everything on their own. And we want them to do that. We want rollup developers to be able to encode their own rules. However, we can start to add committee-based services to the shared sequencer. So things such as committee-based IBC, you could have a settlement layer. Committee-based IBC, you can have threshold encryption. So Fairblock just posted a forum post on Celestia that was really interesting, and they effectively do the same thing, right? You have a committee that uses threshold encryption that is also a shared sequencer to provide these trust minimized services to a rollup. And oracles, you can have socially slashable oracles. Hopefully I'll have time to talk about that later, but maybe not. And then what we're going to talk about next is censorship resistance per block. So I kind of hinted at this before with shared sequencers, but with MEV, it's effectively like you end up with one block builder. So you have a shared sequencer, that's great, and you have and that shared sequencer provides all the inclusion guarantees for all of these different rollups. But the problem is the number of rollups that can go on a shared sequencer is technically unbounded. Ooh, and that means that like a block builder for that shared sequencer is going to have run rollup full nodes for all of those full nodes. Unbounded is, ooh, that's a bad thing. It's not good. And effectively, like, that's a very centralizing force of having to run all of these full nodes, and like having one giant block builder, it's not very decentralized. It's not very good. So what are some things that we can do around that? So again, we're designing these services for rollups. What can we actually do? So again, like one of the underlying issues here is that I have a politician here, but you can think of a politician and a validator basically like the same thing. They're analogous at the very least. And these politicians and these validators, they have monopolies over specific things. In the case of a validator, when it's your turn to create a block for most consensus protocols, most consensus protocols in use today, that is, you get to pick everything that occurs in that block. And you can abuse that power by taking a bribe to include other things, right? We, as delegators, delegate to you, a validator, and then now that power that we gave you, you can abuse by enriching yourself, by like taking these bribes to sort of order transactions in a favorable way or censor different rollup blocks. And that's incredibly problematic when with rollups, we just want to be able to define these simple fork choice rules. But before I get into fork choice rules, we'll go to the next slide, which again, this is showing the point with these modern systems, these modern blockchain systems, a lot of the times so far, the validators, the politicians, they're the ones who are getting rich. They're the ones who are taking all of this money. And then the users of the chain, that's a downslope, right? And the network isn't making money in most of these cases. For Ethereum with EIP 1559, arguably you're getting some increased burn rate, which in that case, the network is going up quite a bit. But anyway, without breaking this proposer monopoly, right? Without breaking this proposer monopoly, we're kind of stuck in this boat. We're stuck in not being able to define where the profits of a system get captured. So thankfully, earlier this year, Duality, the folks at Duality, including Elijah, who wrote this paper, and this is a screenshot of a forum post on Celestia, describing exactly how you actually could do this. And this is the key thing for not solving MEV, but being able to programmatically define where the profits of an entire system go. And they do that by breaking the proposer monopoly. So I'm quoting Elijah here. I thought this meme was absolutely hilarious and so perfect because it's like people protesting and the proposer monopoly. And it's true. It's really true. So I'm running out of time here. I'm going to have to rush through some things. Fork choice rules. Rollups can define their own fork choice rules. If you can define your own fork choice rule, that means that you can define things really simply and elegantly, like I want my rollup to, the block that wins is the one that brings the most values to LPs or burns the most of my rollup token. I can define those simply if and only if the proposer does not have a monopoly. Because if the proposer has a monopoly, they're just going to be able to pick the correct block that gets in, the block that they want, the block that they get bribed to most. We don't want that. That ruins the property that we want, right? We want to programmatically capture the entire profits of a system. I think I only have 30 seconds left, so I'll touch that we have decentralized block building. Stay tuned for that. I think there's some exciting things. Lots of work. None of it's set in stone. This is just me writing things. I do think with shared sequencers we have a potential like awesome thing. And with oracles, the there's some things with ABCI++. You can have trust minimize, or you can have socially slashable oracles, which is really cool. And that's my talk: trust minimized and impact maximized rollups as a service. When we build these systems, try to consider these things. Validators are cucks. Sovereignty is the difference between crypto and everything else that came before it. Let's build cool shit.
Hello, this is Amrit and Yaoqi again. Hope you enjoyed the talks. In case you missed any, the entire video will be available on YouTube, and we'll also be segmenting it so that you can jump directly to the talk that you may have missed. Now we are towards the end of this virtual event. This segment will be the last bit on our agenda today, and therefore we'll keep this segment as a Q&A session. We have received several questions from the committee beforehand. We'll start with those, but please post your questions in the YouTube chat box, and we'll try to pick as many as we can. But before we start, I would like to ask Yaoqi to give us a quick demo of our Rollup Launchpad. We have been building this for quite a while now, and we did a couple of campaigns around this as well. And so let's go through that first, and then we'll open the floor for a broader Q&A. Yaoqi, over to you.
Yeah, so I believe like most of the audience already know we have this Rollups-as-a-Service dashboard platform, right? So easily you can just log in to this dashboard.alt.technology, and once you enter this page with a single sign-on, typically your Google account, you can see roughly the same like sort of structure and setup as I'm showing to you. So here, I will just show you how to quickly set up a rollup or flash layer in our context. So there are two ways. Actually, the fastest way is to use the Flash GPT. So we integrate like GPT with our dashboard. So in that case, as you can see, right, you can just describe what kind of flash layer you want. And then within a few seconds, it will generate the configuration file for you. And since it's chatbot, right? So you can just tap what kind of configuration parameter you want to change. For example, we want to change the name to RaaS day and token symbol to RaaS. So after that, it will directly change the corresponding parameters. And yeah, after that, so this is, so you can change the token symbol again to RaaS2. So after that, right, you can basically later deploy the flash layer where the generated configuration file. Or we can just use the default one here. You just click the deploy the flash layer. It will just deploy within 2 minutes. And there's an alternative way. If you are a developer, right, you want to choose the parameters sort of with some precision, right? So you can go to this second tab called Create Flash Layer. And then by default, there are two modes for you. One is first come, first serve. The second one is the typical gas mechanism. And then you can just input your flash layer name, for example, RaaS again. And then you can configure the gas limit and also the block time. After that, you can also define your token symbol and also the currency name. After that, you define the Genesis account you want it. And by default, we have this block explorer and also token foresight for your rollup, or we call flash layer. After that, you can just click create. Typically, it just like take 2 minutes to generate the sort of the flash layer. As you can see, right, it's already generated one, and basically you can look at the block explorer. All the blocks are generated, and also you can go to the token foresight and claim the tokens you sort of have. Beyond that, right, as we can see, there are also IDE, so you can deploy your contract to the flash layer or the rollup you just deployed. And by default, we already have some token contract template. You can basically go to the first tab. There's a contract generator. You can just choose what kind of ERC20, ERC721 contract you want to use. And beyond that, if you launch multiple rollups, right, you can manage your rollup where this tab called Manage tab, and then you can decide what kind of operations you want to apply on these flash layers or rollups. And as Amrit mentioned at the beginning of this conference, right, we have a very special feature called flash layer settlement. So that means when you do anti-mint or some events, right, so you can deploy a contract on the L2, but once the event is done, you can leverage this tab we call rollup tab, and then select the contract on the L2, and then in one shot, the product can automatically roll up all the NFTs and also assets within this contract back to the selected L1. Yeah, this is roughly the sort of the Rollup-as-a-Service platform can provide for you. And later, as I just mentioned at the beginning, right, we provide more services. And for example, the dev tier with the persistent rollup with fraud-proof and multi-sequencer. And meanwhile, we are also integrating the Arbitrum orbit. So later on, you can have more choices to launch for your dedicated rollup. Yeah.
Thank you, Yaoqi. Let's open. So, by the way, a gentle reminder: if you have any questions that you want us to answer, you can post them on the YouTube chat box, and we are monitoring that chat box, and we pick questions from there directly as well. In the meantime, we have received questions, I think from Twitter, and I would like to take one question, and I'll pass it to Yaoqi first, and I'll take another one myself. So let's start with this question. So this is maybe I will start with this one, and then I'll pass the second one to Yaoqi. So the question is, can you explain the advantages of your technology in comparison to other competitors out there in the crypto space? Right. This is something that I addressed in my first talk. So basically, there are different types of providers out there. So in particular, RaaS providers that are building similar solutions. And by the way, when we started building this, I don't think there was anyone, or even the term Rollup-as-a-Service wasn't quite there, used in the space. But yeah, since then, there have been a couple of at least 4 or 5 similar vendors or people building similar solutions. So here is the comparison. So the first thing is we are the only ones that has fraud-proof enabled at the moment using our own tech stack. So this is currently on the testnet, but we'll hopefully go mainnet very soon after that, once we're happy with the results from the testnet. The second thing is that we support decentralized sequencing from the get-go. So again, people are, and you heard talks about decentralized sequencing from several speakers today, but decentralized sequencing is still not enabled in any platform as far as we know. And in fact, the rollups that you launch from through dashboard could have multiple sequencers if you wanted to. And we already have a multiple sequencer testnet already live that you transact with already. And there's other thing which is mostly around different kind of like a WASM based, because the entire stack is based in WASM, it kind of gives you a multi-chain, multi-VM support from the get-go, right? It allows people to kind of have different choices in terms of EVM that they can have. And finally, which is we are the only ones that provide this unique type of execution layer that we call flash layer. So this disposable layer where you spin up the flash layer, you use it for as long as you want, and when you feel like you're done with it, you don't need that anymore, you can take the entire network down. All the infrastructure that was supporting it will be taken down as well. So it's very resource optimized, and we're the only ones to offer this. Let me pass the second question to Yaoqi. This is more of a experience question, which is someone asks, could you share some unique challenges that you faced while developing rollups and modular blockchains at AltLayer, and how you overcame them?
Yeah, it's a great question. So as Amrit just mentioned, right? So at AltLayer side, we are providing a lot of unique and brand new features for this space. For example, this decentralized sequencing, multi-sequencers, and also this multi-VM. Apart from EVM support, we also support like WASM, and later on for different programming language, they can also compile into WASM for execution. And beyond that, regarding this disposable execution layer with proper proof system, and all these stuff, I would say are quite new to the entire sort of blockchain space. And today I also share about this insurance rollup interlayer, the beacon layer, right? And I believe this is also the first time for us to explain what's a beacon layer and how it can really benefit the entire rollup space. So to implement and actually to design these features in a comprehensive way, it takes a lot of time and a lot of efforts from the entire team to really make it possible. So the implementation side is already very tough. And beyond that, for the other challenges is really about the automation. Compared to some other public blockchains or a lot of these general purpose L1s, L2s, right? So you just need to build your tech stack, and you at most just need to run the infrastructure for your chain itself. But for us, we're building this Rollup-as-a-Service platform, which is quite similar to AWS in the Web2 space, right? So in that case, we need to handle tons of thousands of rollups. Give you one example, like for the current Flash layer spin-off, right? We already got over 12,000 free tier spin-off via the dashboard. So in that case, we really need to build a full automatic infrastructure to really launch these rollups, manage these rollups, and also coordinate these rollups. So that's also very challenging compared to for most of the general purpose L1s, L2, they just need to manage their own chain. For us, like we need a completely automatic system to handle all these automatically instead of like doing it in a manual way. And beyond that, right, as I just mentioned, because in the long run, we want to decentralize the entire infrastructure. So it's not like a pure AWS in Web3. We want to have a decentralized this kind of Rollup-as-a-Service platform. So that's why we come up with beacon layer. Try to manage, like for example, sequencing verification, staking, slashing, governance, and upgrading, right? So we only with beacon layer to basically help us to coordinate all the rollups and customers. So they spin the rollup via the beacon layer, and in the end, all the sort of the sequencers or verifiers are from the community. In that way, we can make it decentralized, and at the same time, everything is automatic. So that's why it's not a single challenge. Like for example, just to achieve a consensus protocol or some algorithm. It's like a systematic challenge in general. So from the design implementation for particular features, and then for the infrastructure design, the building, and then to the decentralization of the entire infrastructure. As you can see, we need to make a lot of these steps one by one to really make it work in the long run. So in the future, you can see a very decentralized Rollup-as-a-Service platform with the sequencers or verifiers from the community and powered by AltLayer.
Okay, let's take a question, and I will answer this. This is a question that came beforehand, I think, via Twitter, and I also saw a question. It's a very similar question on YouTube as well, which is basically the question around, can we expand beyond Ethereum? Or one is, can we expand to other EVM chains beyond Ethereum? And then the second question or follow-up question is, can we expand beyond EVM chains? So can we go to non-EVM chains? The answer is yes. So the first part about the EVM part, we already support EVM chains. So it's not just Ethereum. For example, we did an event, a paid mint event, where you could actually go and bridge assets from BNB chain, Polygon, and Ethereum, right? So non-EVM chains are already supported, and almost any of them can be easily supported because all you need is a basic bridge. For non-EVM chains, the answer is yes, it should also be possible. And the reason is that we have this stack that is built in WASM that allows us to basically support any chain. And I think Ed Felten was talking about something like this as well during his talk, that because you have a WASM base, anything that compiles down to WASM can be supported. So the answer to both questions is yes. The EVM part is already supported. So right now, if you want to have a flash layer, you can actually go and connect it to any chain you want, any EVM chain you want. Non-EVM chains, it's in the pipeline, but first we want to finish the EVM components completely. Let's take another question that I saw on I think YouTube somewhere, which is, there were talks around Eigenlayer. There were talks around with Espresso. Will it be possible to integrate Espresso and let's say Eigenlayer in Rollup-as-a-Service offering, given that AltLayer already has some of the big bits already built? Yaoqi, you want to take that?
Yeah, so for Eigenlayer, as Sreeram mentioned in this morning's talk, right? So the EigenDA is basically quite balanced DA. So it's sort of like it balances the cost and also the performance. So in that case, as RaaS platform, so later on, for the new version, we will have multiple options for the developers to choose regarding DA. So either you can use your own nodes as the off-chain DA system, or you can choose probably like Eigenlayer or even Celestia as your DA system, which are quite professional in building a DA network. Or if as a project, right, for example, as a DeFi project, you really feel that your data should be posted to Ethereum to make sure like all the data available at this Ethereum security level. Then we also provide the option that you can post your data to Ethereum. It's just like it's quite costly. And beyond that, it's also open to various like EVM chains and also some other decentralized storage projects. Regarding Espresso actually previously we had a bunch of conversation with Ben, and we feel that Espresso is really like this pre-execution DA. So it helps you to basically fetch and aggregate the transactions on the Espresso platform. And after that, it gives you an ordered like list of transactions for your rollup to execute. So in that case, it's also a non-intrusive platform for us to integrate to. Actually, for both of these projects, right, we already have some team members to look at their code base and documentation to look at how we can plug in Eigenlayer, use them as EigenDA at the beginning. And also for the Espresso, we can look at how to leverage Espresso network as this pre-execution DA to order these transactions and send to some of our rollups. If the rollups really choose Espresso as sort of the share sequencing layer at the beginning. Yeah.
Okay, let's take another question, which is around Arbitrum Orbit. So the question is, explain the integration with Arbitrum Orbit and the tech stack. What is its relevance and why facilitate L3? How it facilitates L3 app development. So let me take that question. For a little bit of context, and I think so those who listened to the talk from Ed Felten, he gave a talk on Arbitrum in general, but also had quite a few bits and pieces on Arbitrum Orbit. So Arbitrum Orbit is basically a tech stack that allows people to deploy application-specific instances of Arbitrum's code base, essentially, or Arbitrum's tech stack, essentially. And again, for context, Arbitrum is today the largest layer 2 or the largest rollup provider today in the market. It has a TVL about 5.8 billion in TVL. It has a market share about 60%. So Arbitrum One is one of the biggest providers in the market for rollup, or biggest rollup today. And so it's really interesting for us to kind of help people who are building on Arbitrum, to give them a choice to build the application-specific infrastructure that uses the same stack, the same tech stack that Arbitrum offers as a part of Arbitrum One, for example. So it's really relevant because there are people, and Ed Felten mentioned that as well. There are people who really want customizability. There are people who want their stack to be much more scalable, and that you can do that only if you have your own application-specific infrastructure. And that's why it's important for us to support Arbitrum Orbit. In terms of integration, it will look very similar to what Yaoqi demonstrated at the start of the Q&A. Basically, you will have the same kind of dashboard, you'll have the same experience, and you'll be able to just pick and say, okay, I want a Flash layer, or I want an Arbitrum Orbit, or I want a Flash layer connected to Arbitrum One. You would have all these different choices. You can pick the right kind of stack that makes sense, most sense for your business and an application use case. Hope that answers your question around Arbitrum Orbit and why it's important for us. And obviously, it will help anyone wanting to build on Arbitrum Orbit. And that will basically, we will provide the entire, let's say, managed service that would run behind Arbitrum Orbit. Let's take a follow-up question, and this is something around beacon layer. I think there was, I think Yaoqi gave a great talk on beacon layer and some of all the benefits that beacon layer provides you. But I think it's good to summarize, and this is a question that kind of pertains to that as well, which is, why do we refer beacon layer as an interlayer? Like, what's the significance of an interlayer, and why this interlayer is important? Yaoqi, you want to take this one?
Yeah. So why we need beacon layer? So from the system evolving perspective, right? So as we can see, so we can divide this rollup category into multiple stages. The first stage is we need basically a single sequencer and also the proof, either this fraud proof or validity proof. And this proof will just need to verify the execution of the transactions via this EVM, right? So in that case, the proof, they just need to verify the logic for the EVM and also the EVM instructions. And then in the stage 2, since there are a lot of requirements from the community or projects, they want this multi-sequencer to make it relatively decentralized to avoid single point failure and to mitigate MEV or some other issues, right? In that case, we need to have multiple sequencer. And once we have multiple sequencer, we need some sort of agreement protocol within this sequencer just to make sure like they agree on the same block of transaction to be executed and generated. So in that case, like for the proving system, they also need to take the agreement protocol into consideration beyond this execution of the instructions. And so then we need some extra implementation and logic for the proof system to support this extra agreement protocol among all the sequencers. And on top of that, so since we have multiple sequencers, we know who behaving wrongly and who are behaving in a good manner via the proof system, right? So we need staking and slashing, basically a penalty mechanism to basically punish some of the sequencers who behave maliciously. And that's sort of the stage 2. And stage 3 is sort of like why we are proposing this beacon layer. Because like right now we have probably 5 major rollups, but gradually when more games, social applications, DeFi applications who are capturing a lot of users, they will definitely spin off their own rollups or app chains. So in that case, we can foresee tons of thousands of rollups in the world. And in that case, we really need a sort of a decentralized layer to manage these rollups. that's something we are building at AltLayer, right? The first step, like we provide this no-code RaaS platform for developer to quickly spin off the rollups within 2 minutes. But after that, we want to make it decentralized. So that's why we need this insurance rollup interlayer between the rollup and also the Ethereum. So once we have this decentralized layer, right, it can help us to handle a bunch of things. First one is the decentralized sequencing. So as we just mentioned, right, rollup may want to have multiple sequencers. Where to find these sequencers within a decentralized network? And after that, we also want decentralized verification. Where to find these verifiers? We need this a network. And beyond that, how we do governance, how we do message passing across different rollups, how we do the upgrading, and even how we do this on-chain governance. All of these, we need a decentralized protocol. So in the ideal case, it should be Ethereum. That's why in my talk I mentioned about like the best case for insurance rollup is to light all the rollups in front to Ethereum. But we just create too much responsibility for Ethereum in that case. So that's why we need like something like this beacon layer to help to coordinate or orchestrate all these rollups at the same time provide this decentralized sequencing verification, staking, slashing, governance, upgrading, all of this stuff. In that case, like we can provide the entire decentralized RaaS platform for all the developers, especially game developers, NFT, or the social developers, which they are not familiar with how to spin up a rollup or blockchain, right? So they can just focus on their business logic. So that's why we need a beacon layer. Basically, it's sort of like we follow the evolution of the technology in the rollup space, but at the same time, it's definitely needed when we have more and more rollups in this ecosystem and space.
Thanks, Yaoqi. Let's take this question. I'll take this question, which came on YouTube just now. Any plans to have your Blocks Pro that look like Etherscan, but built on AltLayer? Block Scout Explorer Scan is somehow confusing. So the answer is, first of all, thank you for the feedback around Block Scout. And so the idea is, yes, we would love to support multiple different types of explorers, but at the moment we mostly focus on integrating those explorers that are kind of open source. It's easier for us to kind of integrate that quite easily with our rest of the stack. At some point, if we feel like it's not good enough for our clients, we'd be happy to go and build a separate Block Explorer. Hopefully, at that point, maybe someone else will build a much better Block Explorer, and that we could just use and integrate. But for those, and some people might, those people who are looking to have a persistent Block Explorer, persistent rollup, they might actually want to have a proper Etherscan like tool. So in that way, in that model, basically you have to contact Etherscan, and Etherscan can build a Block Explorer just for your specific use case. But as you can imagine, it's not, it comes with a cost, and it's may not be interesting for, let's say, short-term usage. That's kind of why we are using something which comes open sourced and free. But yeah, for those that are our clients that are looking for, let's say, a longer-term persistent rollup, then I think something like Etherscan could make sense. And yeah, at some point, once we have a little bit more time on hand, we might be able to, might be interested in kind of building our own Block Explorer as well. Let's take another question, which is so let's take a question more on the non-tech side this time. So this is for Yaoqi. What are some of the real-world use cases or applications where AltLayer solutions have been successfully implemented? Would you take that?
Yeah, there are a bunch of partners we've collaborated recently. I believe some of the quite successful examples we show for the past few months. One is this NFT mint. As we all know, right, we minted this OG badge and also this ORT NFT, and also this carriers cool. And for this NFT mint, right, typically it's quite straightforward for users to use, and basically all the NFT minted within a few seconds or a few minutes. So it's quite smooth, and in the end, like the protocol automatically settled all the NFT back to Ethereum, and people can easily trade over the OpenSea. And beyond that, we also have the partners who are organizing events using some NFT tickets, and we successfully like sort of run this NFT system for some of these events, like the football events recently in Malaysia, and with some smart wallet, we provide this really seamless user experience for the users. So they don't need to set up MetaMask. They can just click on the page to mint the NFT as the ticket, and everything is done automatically on the backend. On the other side, it's related to the big partnership announcement. And basically, some of the firms, we already set up the partnership, and they will start to use our layer, our RaaS platform to set up these different rollups for different famous game and game studios. So as you all know, right, for game and also social applications, the the latency is very important. So we got a lot of feedback from the game developers, either from the Web 2 or from Web 3. Of course, their requests are quite different. Some of them request for 15 billion gas limit. Some of them require for sub-second block time. And some of them want to be quite like sort of quite user friendly with zero gas. So in that case, it's like not possible for general purpose L1, L2 to achieve that. And so they seek the help and support from us. And then later for all these sort of parameter or configurations, you can just set it up via the dashboard yourself. So no need, this manual support anymore. And these are sort of the examples we've done for the past few months. And of course, we continuously receive the the demands from DeFi projects. For DeFi project, they want the security to be as high as possible. So in that case, they want the multi-sequencer, and meanwhile, proof system is a must. And also some other governance project, they want this multi-sequencer, basically as many sequencers as possible, because it's for governance. So it would be great to have a quite decentralized system compared to single sequencer, or it's relatively centralized rollup system. So as you can see, right, the requests and also the requirements from different projects are quite different. But in the end, we clearly see that there's a lot of demand for customization and a lot of demand for this dedicated rollup just for the applications. So it's a quite clear trend, at least for us, to provide this no-code RaaS platform for these projects, as they can just focus on their main business logic, and underlying infrastructure can just being requested via our layers platform.
Thank you, Yaoqi. Let's take a couple more questions. We are pretty close, running out of time. So let's take two more questions. So I'm seeing a question on YouTube. AltLayer team, thank you for such a great event. A lot of insights and deep dive into the rollup landscape and developments. Are you planning to onboard third-party validated companies in testnet? The answer is yes. We are at a stage where the nodes are still run by us, but so it will be kind of staged release. The next stage, we'll be opening up the testnet in a kind of whitelisted manner. So if you whitelist, then you'll be able to come and join the network. And the second stage would be a completely permissionless testnet where anyone could come and become a node operator. And it's something that if you go back to Yaoqi's presentation, he has a list of upcoming, I guess, milestones that he touches upon. There's another related question that I will pass to Yaoqi, which is what is the system requirements for running a validated node?
Yeah, the cool part that based on our experiments, like the specs for running either a sequencer for a rollup or running a validator for the beacon layer, it's a minimum. like typically, like for some of our internal machines is like a 2 CPU core and 4G RAM. But we recommend at least you have the machine with the laptop specs, right? But in general, it will be sort of the minimum machine requirement. And so that's why we always emphasize that we want to have this decentralized infrastructure as early as possible, so we can welcome as many community members to join the network to provide their like sort of machines for becoming sequencers or becoming the beacon validators. So in that case, as I just mentioned, right, it's no longer like the AWS in Web3. It's a real truly decentralized infrastructure system to provide a rollup as a system product for the rollup space.
I was on mute. So let's take one more question I will take one more question. I will leave the last question, which will be a simple question for Yaoqi to close off. So one last question for me, which I'm picking from YouTube, which is, how do these technologies address scalability, cost efficiency, and user experience challenges commonly faced in decentralized applications? The answer is actually when you have, imagine, for example, when you are interacting today with a Uniswap on Ethereum, you are basically, as a user, you're paying two fees. One fee is what you pay to Ethereum as gas fee. And the second fee is what you pay to the application itself, right? So there are two fees that you pay. And this is not great for user experience, right? And that's kind of why people are developing and building account abstraction, where you could say, okay, I don't want to pay, user doesn't have to pay the gas fee, user only pays the application fee, for example, the fee for trading, for example. And all of this could be very easily adjusted this is very hard to do on a base chain, and that's why you need layers and layers of abstraction on top to be built. But if you have something like an application-specific rollup, you could actually do and build all of this quite easily. For example, you could have a completely gasless experience, and not in the form of account abstraction, because someone else is paying a gas. But here, the model could be completely gasless, where there's no gas at all, even at the protocol level, and you could do that. And that's why that actually helps you in one way, at least, from user experience, in terms of user experience. So users don't have to worry about acquiring gas token and paying for gas. And the other things that you can do, for example, you could improve your latency and scalability, which obviously gives a lot more benefit to people interacting with the blockchain. One last question, and we'll close off as we are running out of time. Yaoqi, when mainnet?
So we are progressing step by step. So right now, if you look at the dashboard, right? So for a lot of these rollup services, they are sort of production ready. If you want to launch this NFT campaign or some gaming sessions, you can quickly launch via the dashboard. And so basically all the operations and activities can be done on the Flash layer. After that, you can settle on the selected L1 like Ethereum, Polygon, and Bitcoin chain. So that part is sort of like already production ready. But for the beacon layer side, right, that's why we are running a lot of campaigns on the testing the features for the beacon layer recently. Like for the past two, we already tested sort of like this multi-sequencer and also staking slashing mechanism. And later on, we will test this no joining and challenging mechanism. So gradually, we will roll out these features once this production ready. And meanwhile, as you can see, right, we want to build all this stuff ready before we launch a mainnet. And so in that case, I believe you will see a lot of good news and partnership along this way. And hope the community can basically join us, and together we witness the progress of the entire development. Yeah.
Well, thank you, Yaoqi. With this, we have reached the end of the RaaS day, the Rollup-as-a-Service day. Hope you enjoyed the talks from the amazing speakers and this Q&A in particular. For those who didn't notice, it was a live Q&A. So we're picking questions live from people, posting them on YouTube, and we're answering them in live. We also thank all the speakers for making time to prepare for the talk, given their busy schedules and time zone differences and whatnot. So yeah, that's the end of this RaaS Day. A gentle reminder that several of our team members will be in Paris for ECC. It's an event that will happen in mid-July this year. We'll also have a Rollup Day side event there. So if you will be in town, come and say hello. Until then, goodbye and have a very good day ahead. Thank you.
Thank you, everyone.